will be a Starfreelancer. Learn new skills. Set your goals. Increase your skills. Browse over 100 plus videos and ebooks. Jump to starfreelancer.eu.
So it's now time to talk about inner classes, because the thing is, in Java, it's actually possible to nest a class inside another class. So what I'm going to do is start by outlining the 4 types of nested classes, and then we'll go through some examples. So the 4 types of nested classes that you can use in Java are static nested classes. We can use a non-static nested class, and we call that an inner class. We can use a local class. Now that's an inner class that's defined inside a scope block, which is usually a method, and also an anonymous class, which is a nested class without a class name. Now the static nested class is mainly used to associate a class with its outer class. So in terms of behavior, you can think of it as being identical to a top level class, but the difference is that it's packaged in its outer class rather than in the package. Now that really means that it cannot access the non-static methods or members of its outer class without first creating an instance of that class. So I know that sounds like a mouthful, but I think what we'll do is we'll start with a non-static nested class, or the inner class, because these are quite useful. And the reason that they're useful is it's when it doesn't make sense to refer to a class without its outer class. So the example is, if we're actually modeling an engine, we might actually have a gearbox class and a gear class. So let's go ahead and actually create that to see how this actually works in practice. So I'm going to go and create a new class. I'm going to call the first one gearbox. And we're going to add a few things to the gearbox. We're going to have an array list for the gears, the number of gears, and also the gear number. So we'll create those fields. So private array list gear. We haven't created that class yet. We're going to do that. Gears. Private int max gears. And private int gear number. And we'll set that to 0. We'll create constructor. And the only parameter is going to be the max gears. Like so. We'll set that to max gears to max gears. And then we'll also do a this dot gears equals new array list. So we'll just initialize it. So, but we also want to do gear neutral, E-U-T-R-A-L, if I can spell it, gear neutral equals new gear 0.0.0, like so. And I think what I did there was I didn't actually specify the right level of Java for some reason. So to fix that, if you ever do get that problem, just right click this and go to open module settings. We want to make sure that we've got our project set to the right version. So if I change that to version 8, you can see diamonds were introduced in version 7. I have actually said that in an earlier video to make sure you're always using version 8 there, but do select that and that should fix that error. And what we need to do is we need to add the gear class, which will actually fix that shortly. So we're creating a new gear, as you can see there, and we're going to add that to the array. So this .gears.add neutral. So that's the base class, and what we'll actually do now is create an inner class. This is the inner class, which is sort of a class within a class. So to do that, making sure that you're actually in the public class definition. So we're in the final bracket in between any method, at the end of any method, but before the closing brace. That's where we can start typing. So we can type public class gear, just as you would normally do it. And then we can actually add some private fields, just as you would normally create a class. So int gear number, and let's say private double ratio. We can create a constructor, and you can see we were using a constructor in the gearbox constructor to create a new gear. So we'll do that. And the constructor will have 2 parameters, the gear number and the ratio, like so. That should fix that other error on the screen there now. And we'll just create a public method for drive speed, which will basically accept the number of revs as a parameter and multiply that by the ratio to get the drive speed. So to do that, so we normally do, we just actually create a method. So public double drive speed int revs. We could return revs multiplied by ratio. So there's a step, there's like a definition for an inner class. So it doesn't actually make sense to refer to a gear in this scenario, except when we're talking about a gearbox. So that's why we've modeled it like this. So the gear isn't something that sort of is useful in its own right. It's coupled with a gearbox that it makes it useful. So that's the idea of using an inner class. As I said, when it doesn't make sense to refer to something except within the context. So in this case, it doesn't make sense to talk about gears unless it's within the context of a gearbox. And that's why we've modeled the gears using an inner class of the gearbox class. Now, instances of the gear class have got access to all the methods and fields of the outer gearbox class, even those marked as private. So notice that the use of this in the inner class refers to the inner class and not the outer one. So in other words, this.gear number, this is actually talking about this actual class here, the public class. So it's the inner class, in other words, and it's not referring to gear number as in this one here, because that's actually in a different class. That's in the the top level class, the gearbox class. So keep that in mind, that when you're using this, particularly with inner classes, that you're actually dealing with the class that you're currently in. In this case, we're talking about the gear class. And that probably brings up an interesting point here, but using the same variable name for two different things like this is confusing. And of course, the reason why it's confusing is that inside the gear, both this.gear number and gear number refer to the gear number of the gear and not the gearbox itself. So if you want to refer to the gearbox's gear number from an instance of the gear class, you have to use gearbox.this.gear number. So, where a variable or parameter name is the same one as the one that's in the outer class, it's said to shadow the declaration of the outer class or in the outer class. So here, gear number in the gear class, this one here, we can actually say that that is shadowing gear number in the gearbox class, which is that one there. So that's not a good thing. So we're going to rename the gearbox variable to current gear to avoid confusion. And that's what I certainly recommend, because you're going to get into all sorts of problems otherwise. So what we're going to do is we're just going to right click that, refactor, rename. We'll actually change that to current gear. Current gear. Press enter. And that would actually make a lot more sense to do it that way, just to avoid any confusion, because obviously you want to make things as easy as possible when you're developing, and anything you can do to reduce this sort of confusion, particularly when you start dealing with inner classes, it's very, very important to do that. So make sure you do keep that in mind. Now, the gear class itself is a member of Gearbox, and it must be created with an instance of it. And probably the best way to show you what I mean by that is actually to show you an example. So we'll go back to our main class and create it so you can understand how that works. So go back to main. We're going to write some code here. So we're going to start with typing gearbox. So gearbox, we'll say McLaren, it's a nice car, equals new gearbox, 6. So 6 gears, in other words. Now, to actually create a gear class, we have to use gearbox box.gear, like so. First equals McLaren dot new gear 1, the ratio 12.3. And then we could do something like system.out.println first dot drive speed, and we can set that to say 1000 revs, like so. So it's important to understand the declaration there, because gear is an inner class to gearbox. We need to specify it like that. We need to specify the outer class, gearbox dot, then gear, and then actually also here, you notice that line there, we actually use the gearbox instance that we created, and we did a dot new there for the gear. So it's slightly different syntax when you're creating an inner class like that than you've probably seen in code before. So keep that in mind, because it's very important. You'll actually get an error if you try to create a gear object without actually having an instance of Gearbox to create it from. And just to show you what I mean by that, let's create a few more examples, and you can sort of see what the weird errors you sort of get. So we've got the first one there, McLaren equals new gear. That one worked fine. But if we try typing gearbox dot gear second equals new gearbox dot gear, notice the syntax is different to 15.4, we actually get this weird little error here. And the error is com.timberchalker.gearbox is not an enclosing class. So you can't actually do it that way. You basically need to use the .new, but referencing the outer class first, as you saw in the example above. We created the outer class, which was gearbox, created a new instance of that, and then we use the .new on there to get that to work. So that doesn't work like that. But also you can't do this. You can't do gearbox gear third equals new McLaren dot gear 317.8. That also doesn't work. So you get an error that you can't resolve the symbol gear, and that's because, again, we need to use the .new to create a new instance of it like that. So keep that in mind, that you probably would think that, particularly with the third gear, that it would actually work like that, but that, as you can see in the attempt to create the third gear, might look how you'd expect it to look like, but it actually doesn't work as well. And again, just confirmation that in the case of the second gear, it actually fails with that error which you saw, which gearbox is not an enclosing class, which is slightly confusing. So if you look at that, you're probably thinking, well, why is it doing that? Because gearbox does seem to be an enclosing class in as much as the outer class for gear. For that call new to work, gear would have to be a static nested class. So just really a matter of getting used to the syntax. The bottom line here is that this is the correct way to actually create the outer class, which you would normally do anyway. There's nothing new about that. But in terms of the inner class, you reference the outer class first, dot, then whatever the name of the inner class is, and then that's for declaration purposes, and when you're actually initializing it, the name of the object you've created, .new, then whatever the name of the inner class is, and then the normal parameters you would have in a constructor. And so if we just run that to see that it's actually working. Okay, and you can see that I've actually got some errors there. I'm not too good at picking up typos when I'm actually recording videos. Okay, now if we actually run it, now that I've actually fixed that other little typo, we should actually find that it works and it comes up as you would expect it to. So bottom line is that the correct syntax might be a bit clunky, but that's just how it's done. That's how the designers of Java have implemented this, and we obviously have to work with that. The other thing to keep in mind is that often, though, the inner class is going to be private anyway. So in other words, instances will only be created by the outer class. So in other words, you wouldn't normally, if you've got a gearbox here where it's the outer class, the inner class is probably, in this case gear, is probably something you don't want people to normally directly access anyway. So in other words, the instances will only be created by the outer class. The private, so making this class gear private makes sense here, because we're not actually interested in the individual gear objects when driving. We want to change the gear, but we do that by interacting with the gearbox, not with the individual gears. So in other words, your public interface that you're exposing to your program here would be gearbox. You wouldn't be exposing gear directly. You'd be exposing the fact that you can actually change gears, but not actually, you won't be interacting with the gears itself, if that makes sense. So what we could actually do is actually make some changes to that. So that's actually how it would actually work. And you saw, going back to the gearbox class anyway, let's close that down, that we did actually create a new gear anyway. In the constructor, we added a new gear for neutral anyway by default, and that's how we could access that. So if we actually change this now and change it so this is actually a private class, the inner class is now private, as you can see there. We've still got a constructor and the ratio, but we don't need to make any other changes to it. But that will mean, if you come back to here, we actually get errors now, and that's because we can't access that directly anymore, but we'll need to make some changes to the gearbox to actually do that. So what we're going to do is actually add a few functions. We're going to add a function for operating the clutch. We're going to add a method rather to actually add gears. So we can actually add gears to our gearbox object, which will be adding gears to the array list automatically, and just show you how to change gear as well, all done from the outer class, in this case gearbox. So this is going to be above the declaration for the private class gear now. So we'll start off by operating clutch, public void operate clutch, and we'll boolean in, as you can see there. And I haven't created that variable yet, but we'll do that shortly. So clutch is in equals in, whatever the status of that is. And we'll create a boolean here. So it'll be private boolean clutch is in, like so. So that's the ability to operate a clutch as a method. We'll also add the other method, which is the ability to add gears to our gearbox. So public void add gear, and we'll pass a number, which will be the gear number, and the ratio, which you saw us using before. Then we'll just do some basic checking here. We'll put if number is greater than 0 and number is less than or equal to max gears. Max gears was something we defined up above. Max gears, if that's the case, this .gears.add, creating a new gear class, which remember is now private, so only the outer class, the gearbox class, can directly talk with it now, and the number will be the gear number and also the ratio. So that's the add gear method. And then the other thing we want to do is we want the ability to change the gear as well, and to do that we use a change gear. We'll create a change gear method. So public void change gear int new gear. Then we want to make sure that it's valid, so we're going to put if new gear is greater than or equal to 0, remembering it can be 0 if it's neutral, and new gear is less than gears.size, so we're just validating that we actually have got a gear of that number. That's the case. And also check if the clutch is in, assuming it's a manual. So if this dot clutch is in, if all that is true, we can go this dot current gear is equal to new gear. And we can do something, we'll put just a message out to say gear plus new gear selected. Else, what we're going to do is print out a message grind, which would basically mean that there's a problem with you trying to change the gears and you're getting that weird sound you get from a manual when you try and do that. And we'll set this dot current gear to 0 because we weren't successful in actually setting or changing the gears essentially. And what we'll also do is we'll actually add a wheel speed method as well to determine the speed. So we're going to create one, public double wheel speed, and the parameter will be revs. If clutch is in, scream, like so, and we'll return 0.0. So we're not returning any calculation at this point in time. Otherwise, if the clutch isn't in other words, the car can move, we're going to return revs times gears.get current gear dot get ratio. And what we haven't done is we haven't actually exposed the get ratio. So we need to do that. That's a method of the inner class. So we're just going to, and that's just a getter. So we're going to do a getter for our ratio like so, and that should fix that other error up. So you can see how now we've written the class, the gearbox class, to do all the, to perform all the functionality it needs in the gear class itself. We're creating new instances of the gear and saving it in our array list up here. But we're also using various functions within the gear to get the ratio and for other sorts of calculations. And in this case here, you can see in the wheel speed, if the clutch is in, obviously we're not actually moving. There's going to be a problem. So we're screaming, we're returning 0. Otherwise though, it's the revs multiplied by the gear, the current gear that we've actually set in the change gear method. And then we're using the dot ratio, which is actually called from the inner class itself. So that's how you would actually go about doing it. So what I'm going to do, this video is getting a bit long. I'm going to stop here. And in the next video, we'll come back and we'll actually put some of this code into the main method and start seeing how this actually works. So I'll see you in that next video. In the previous video, we started our inner classes discussion. So we've created the gearbox class. So let's now go back to the main class and our main method and actually add some code to actually test some of this functionality that we've actually added. So now that we've actually made those changes, we need to delete some of the way that we've done things in the past and change that. So I'm going to delete that. And we're going to come up now and start entering some code. So the first line's still correct. We're going to actually add a set of gearbox, or add a gearbox to a McLaren car. So it's got 6 gears. So let's now add 3 to it. So we type McLaren dot add gear, and the first one's going to be 1. The ratio is going to be 5.3. Second one, 10.6, and the third one, we're going to make that 15.9. Let's now operate the clutch. So we'll do McLaren dot operate clutch, true, like so. So we can, in other words, we can change gears and get a printout of how fast the wheels are actually spinning. So we'll do that first, and then we're going to do an example of not changing the gears to see what happens to make sure the code's working. So we'll change the gears now that we've operated the clutch. So McLaren dot change gear 1. So change into first gear. But now if we actually set the clutch to false, so McLaren dot change gear, sorry, operate clutch I should say, operate clutch to false, and try and change into second gear. But what we'll do after the operate clutch, we'll actually print out wheel speed 1000 at 100,000 revs, and then we'll do that afterwards as well, after we've changed the gear into second at 3000. We'll then set the clutch. Well, let's actually try running that first to see that it's actually working. So So you can see with gear 1 is selected. We've got 5,300 as the wheel speed, and of course the calculation there is the 1,000 times the ratio. 1,000 times 5.3 is 5,300. We got a grind, and that's because we weren't operating the clutch. We set that to false, so therefore the actual wheels, the wheel speed is actually 0 at that point. So we actually changed it again now to McLaren.operate clutch to true again. Go to third gear, third like so, and McLaren.operate clutch false, and we do a printout of the wheel speed again, McLaren.wheel speed 6,000. If you run that, so let's do it up here. So again, you can see gear 3 was actually selected successfully, and operating clutch is false, but we haven't actually tried to change the gear, so therefore the speed is still correct, which is now 95,400, which is 6,000 times 15.9. So basically, as you can see there, we added gears to our gearbox. We can change the gear. We can get a printout of how fast the wheels are spinning. And if we forgot to operate the clutch when changing gears, it'll either grind the gears or cause the engine to scream as it hits the red line and bounces off the limiter. Now notice that we didn't have any reference at all now to the gear class in order to drive the car, and that's because the gear class is like local to that gearbox class itself now. It's actually an inner class. So really the add gear calls are part of using the gearbox. So if we go back to our gearbox class again, and back up to the constructor, you can see there that really the add gear calls here, calls to that, they're really part of building the gearbox and not actually using it. So therefore you could consider that it'd be better to put them in the constructor of our gearbox class rather than actually having them as separate calls, which they actually are now when we've actually added them here. So let's actually go ahead and do that. So what we're going to do is change that, put some code here for int I equals 0, I less than max gears, I plus plus, add gear, I times 5.3. We'll assume the ratio is the same for all. That's now actually adding individual gears to the gearbox. Once we've done that, we can of course then remove the calls to add gear in main, because it's no longer appropriate to have those, so I'm going to delete those there now. And of course we can run it and it should still work. And as you can see, it's still actually working. So as you can see, getting back to our example of actually adding the gear class, the private class here, the inner class, it really can be a good way to improve encapsulation. So objects only know about other objects that they need to know about. So in this particular example, nothing apart from the gearbox needs to have any details about the actual gears. So we hide the gear class completely by making it a private inner class of the gearbox class. So you're not accessing the gear class at all in anything other than the actual gearbox class itself. So it's really a great way to encapsulate that functionality and to restrict other people from accessing it. Now obviously if we were writing a stock control program, then the program would have to have some knowledge of the different gears so they could be ordered, or a request sent to manufacturing to make them, for example. So you really need to decide how your program should be designed to work. Doing that or figuring out how to do that, that's really the great skill of object-oriented programming. So that's inner classes, but now there's two special cases of inner classes, and that's local classes and anonymous classes. So local classes are declared inside a block, such as a method or an if statement, and their scope is restricted completely to that particular block. So unlike anonymous classes, which can be very useful and we're going to be seeing them shortly, these local classes are used less often. Theoretically, you could argue that they increase encapsulation because they're only declared within the block that uses them, but in practice, you're probably not often that you'll need to or want to use one. But let's actually show an example of this. So one example that might be useful is as a comparator when trying to sort objects. To demonstrate, what I'm going to do is create our own button class and attach a listener to it so code will execute when the button's clicked. I'm going to go ahead and create a new class. And we'll call that button. I'll just close down the run window for now. And we'll create a string, a field called title, and private onClick listener, onClick listener. And we'll fix that error in a minute. We'll create that class, and we'll actually add a constructor. Constructor will be just for the title, and we'll also add a getter. And the getter is going to just be for the title as well. Okay, then we want to add a function to set our onClick listener and also one to handle the click. So we'll do public void set onClick listener, onClick listener, onClick listener, and it's going to be this dot onClick listener equals onClick listener. And Then we'll do public void onClick. This dot onClick listener dot onClick. This dot title. So the button's got a set onClick listener method which I just created that's used to assign an object to the button in order to be able to handle those clicks. So what we're going to do is we're going to create an interface for that. So I'm going to add that here. Public interface onClick listener and public void onClick and passing the parameter string. That now fixes that all up. So we can see now we've implemented a set onClick listener, which has passed the parameter of the onClick listener itself, and we set that field that we've defined up here to be equal to the value that's passed to it. And likewise in clicking, what we're doing is we're passing on the fact there's been a click, which is using the onClick listener field and calling the onClick method itself. So to see how that works, let's go back to our main method and we'll comment this out because we don't need that for now. And what we'll do is we'll actually add some code. We need a scanner first. So, and I'll put the static up here. Private static scanner equals new scanner. And we system.in. And let's also create our button. Private static button print equals new button print. Accept that import. So at this point we can now create a local class that implements that onClick listener interface and assign an instance of it to our button. And how we will do that is we'll do that in our main method. So I'm going to delete this code now so it clears up a bit of screen space. So we do class, and notice how I'm typing this within the method main class, click listener, implements onClick listener, public click listener, which is our constructor. I could have actually used generate, but I've just typed it out now. And we'll say I've been attached when the constructor is actually called. That's the point where the listener has been connected to the button. And the onClick, we're going to write that function. Again, if we wanted to, we could do an override or implement I should say. Click on onClick and we'll change that to actually show a message. We'll say title plus was clicked. So that's our local class that we've actually defined within the method. We then need to attach it to our button field, which was initialized up here. So we do button print dot set onClick listener new click listener. So we've created that class. And at this point, normally what would happen is, assuming that we were using some sort of graphic framework, that would actually automatically respond when a button was clicked, and the onClick method would actually be invoked for us. But because we're not using a graphics framework, we're going to simulate that listen method from the keyboard. So let's actually create a method to do that. I'm going to do private static void listen. Boolean quit equals false. And you've seen code similar to this before. While not quit, int choice equals scanner.nextInt, scanner.nextLine, switch choice. We're just going to have two simple options. Option 0 is going to enable us to quit. So I set quit equals true, should be case there, case 0. And then we'll do a break, like so. That should have been there. And case 1 is going to simulate the actual button print. So button print dot onClick. And what we'll do then is we'll add the code here to actually call this function. So we'll type listen up here. It's going to call the method. So now if we run this, I've been attached, which is the call from the constructor within the class listener. And if I actually type in 1, print was clicked, print was clicked, print was clicked. And that's obviously at that point using the onClick method, which is has been implemented from the interface, and that's actually been executed each time. The main thing to notice here is with the local class, how it's actually been defined, it is applicable just for that block only. And of course, we can enter 0 to quit out of our program. So this particular method using a local class could probably be pretty useful if you want to assign exactly the same object, say to several buttons. If you had several buttons on the screen at the same time, for example, the class is not used anywhere, so making it local in this particular scenario makes sense because we're not actually using this in a shared environment or anywhere else. implementing it as a local class within this method does actually make sense. So let's move on now to anonymous classes. So an anonymous class is also a local class, but it's got no name. They have to be declared and instantiated at the same time because they haven't got a name, and they're used when a local class is required only once. So this might sound like it's of even less use than a local class, but in fact they're very common for attaching event handlers to buttons in a user interface. For example, if you're programming Android apps. And I do use these a lot in my Android course just out of interest. So it's quite likely that if we did have several buttons, that each would require a different on-click method. So using a local class might not be the best solution. In other words, if you've got 4 or 5 buttons on the screen, chances are you don't want the exact same functionality to be called each time that button is clicked. For example, one button might be to quit out of the program, another one might be to print something. So the code to actually execute might be different depending on the button. So this is where an anonymous class can come into use, or can become quite handy. So because what we could do in that example is, rather than define a class for each button, we could use an anonymous inner class to declare an object and assign it to a button in the one expression. So let's see how that would work. So I'm going to comment this out, a local class. Let's look at the syntax for an anonymous class. So we will do that by putting button print dot set on click listener, and again that's very similar to the line above that's commented out. But what we do now is we put new on click listener. Now as I'm starting to type, you notice IntelliJ actually does this for us. It actually comes up with the braces and the 3 dots, and what that actually means is if you press return here now, it's going to create that anonymous class for us. So I'll press enter, and you notice what it did, it actually created that for us automatically. So it created the on-click listener, it also created the override, and it actually created the on-click method itself, which of course we have to implement for this on-click listener interface. And from there we can actually type title was clicked. So in all other aspects it'll work the same. If we run this, I'm pressing 1 there and 0, I can still exit the program. So the main syntax, the main difference rather, was that we're not creating a separate class. In this case, the first case of the local class, we created one, we used the name click listener, and that's a local class. But this one here, the second example, that's an anonymous class, and that's because we used a new on-click listener, or new button.onClick listener, which was added by IntelliJ, and there's no name there because it's been implemented there and then within the brackets. So that's what an anonymous class is for. And you can see that we overrode the on-click method, which we needed to do in order to actually ensure that we actually implemented the interface correctly. And it actually does that quite nicely. So the new object's got no name, and it's declared in the expression passed as a parameter to the button's set on-click listener method. So you've now seen the various types of inner classes. I'm going to end this video here, and in the next video it's time for a challenge. We're going to test your understanding of this. So I'll see you in the next video. So it's now time for an inner class challenge. And just before I actually start typing out what the challenge is, I've actually grabbed the linked list challenge, the final source code from my solution to that linked list challenge. And that's what I'm going to be working on. So if you've actually created the solution yourself and you've got the code that worked for the linked list challenge, take a copy of that and save it to another folder, because you're going to be actually changing that. So what I've done is I've actually grabbed my copy of the solution from the last video, the last completed solution. I'm going to be working on that. So what I'm going to do now is actually type in the challenge down the bottom, and then we'll actually go about implementing it. Because what I'm doing here is I'm going to leave all the code that is actually working in the main class and the main method, so that we can actually confirm that things are working. So once I've typed this out, I'm going to run this, then I'm going to make the changes and run it again to make sure that the changes we've made actually work. So here's what I want you to do in the challenge. So here is the challenge. As I mentioned, we're using the linked list challenge final solution code. And from there, what we want to do is we want you to modify the playlist challenge code so that the album class uses an inner class. So instead of using an array list to hold its tracks, the album class is going to use an inner class called song list to do that. So the inner song list class will use the array list and will provide a method to add a song. It'll also provide find song methods, which will be used by the containing album class to add songs to the playlist. So neither the song class or the main class should be changed. Okay, so this is future Tim making an edit to a video where I found a problem after creating the original video. Now the if statement isn't correct. So it actually should be index greater than equal to 0 and index less than songs.size. So it's basically that first part, the index greater than 0, that actually should be index greater than equal to 0. Now remember that index always starts at 0 and it ends with size take 1. So the problem here is if we add track number 1, the index will be 0 and therefore the if statement will be false because of the way we've got it testing, and that will cause the song object to be returned as null. So in other words, we can't access the first song basically from track 1. So this is the reason why we need the greater than and equal to sign so that we can cover for the situation where the index is equal to 0. And in case you want more information, there was a similar problem in the linked list challenge in this section of the course. And in fact, I showed a video after that one, immediately after that one. And the video for that is titled Bug Fix for Track 1 Error. So you can refer to that for more information. But essentially, that's what you need to do to get this to work. Replace the greater than 0 with a greater than equal to 0, and that will fix that issue. All right, so let's move back to the code. So in other words, you should still be able to run it and do exactly the same thing you could do before in the challenge in the main class and also the main method, and it should still work after your changes. So I'm going to actually just quickly run this just to make sure it still works. There's no reason why it shouldn't, but just to be sure. And I'm just going to go through, do a couple of things quickly. Previous song, this song's on the playlist, etc. That's probably enough now. So I'm going to actually stop that because, of course, the main thing was that the add and find's actually working. So I'm going to actually complete that to exit out of that now, which I've done. So at this stage, pause the video and go ahead and see if you can come back up with the challenge. And I'll just bring that on the screen again so you can see what's the challenge is all about down here. And when you're ready to come back and see what I've done, start the video again and I'll be here and I'll go through my solution. Okay, so how did you get on? Did you figure it out and get it working? So let's make a start. So what we want to do is we need to modify the playlist challenge, as I mentioned, so that the album class uses an inner class called song list. And the song list class has to have the ability to add a song, and also it's going to have the find song methods as well. So let's go back into our source code. And of course, album is what we're going to be ultimately writing this code. So what we'll do is we'll start by, at the end, within the class, adding our inner class. So it's going to be private class song list, and we need to have its own array list to store the songs. Private array list of song objects. Remember, we weren't changing the song class at all. The constructor for the song list is going to just be empty, so select none, and we're going to just initialize that array list in the constructor. List.songs equals new array list of song objects to initialize it, so when it comes time to adding, we can actually do that. We can actually add those. We need to add a method now for adding a song. Public boolean add, and add a song object. If songs contains song, return false. Otherwise, we're going to do this.songs.add song, return true, like so. And we also need our find song methods, and we can, looking at some of the code up here, we can actually add some of this code. So let's actually look at our find song. I'm going to copy that one there, and I'm going to take it out of the album class, and I'm going to paste it in to our inner class. So we've now got private song, find song, string title, and it goes through the list of songs looking for a match. If it finds a match based on the title, it returns the song that it actually found. Otherwise, it's going to return null. So the change is we've moved that functionality of find from the album class into the song list class. And likewise, we can also add another function. The other way that we had for finding songs, we had find song. I think we took it out of the final solution. But int track number, but we can put that back in just to be complete. Int index equals track number, take 1. And we can put if index greater than 0, 0, and index less than songs.size, return songs.get index. And otherwise, we return null. if we weren't able to find a match because the index was out of range or we didn't have that particular entry in there. So that's our private song list class. Nothing particularly complex about it other than the fact we've made it an inner class. So what we now need to do, now that we've done that, we need to make some changes to the album class to start using this inner class, this song list. So one of the first things we'll do is we're going to get rid of the array list of song objects because that's now handled by our song list class, our inner class. So I'm going to create a private song list class and call that songs. And obviously that means the constructor is now wrong because we don't want to initialize the array list because it's no longer an array list. This is now a song list object. So we're going to create a new song list object via the constructor like so. And add song. Now we actually are going to leave that method in there because that's the public method that is ultimately going to be called by the main class and its main method. So we need to leave that in there, but we need to change the call because it's no longer using an internal find song function. Instead, what we're going to be doing is we're just going to be calling the song list inner classes add method. So we're going to return this .songs.add, and then we'll pass a new song object to it. New song, which consists, of course, of a title and a duration, like so. And all this other code can now be removed. So in terms of the functionality, now, of course, add song is now calling the .add, and the .add within our inner class is actually checking to see whether there's actually a problem there when we add it. If it contains the song, it returns false. Otherwise, if we try to add it, then we return true. So in other words, we're still fulfilling this public interface, this public method for add song, but we're getting the song list to actually return true or false. So it's made the code a bit more compact as a result of that. Then we actually removed the find list because we didn't need that anymore. And the next thing we need to do is we need to actually modify the add to playlist because that's, as you can see here, that's actually adding, or it's actually looking for that array list to determine whether it can add it or not. So what we need to do there is I'm going to actually delete some of this code. And what we'll do is we'll start and we'll actually do song checked song equals this .songs.find song by track number. So it's now using the inner class's find song function that we wrote. Then we put if check song is not equal to null, playlist.add check song. Then we return true. Otherwise, this album doesn't have a track number, and we're going to return false. So really the main thing that we did there is we actually called the inner class's find song method to determine whether it was valid or not, and then we're just doing pretty well everything else the same as it was before. So that's the first function. That was where we're actually returning a track number, or that's where the parameters was a track number and then the playlist to add. But we can also add to a playlist by title. So we need to do the same thing there. We need to change that reference. So just to delete that, we can actually change this as a shortcut. I can actually put songs dot find song. This time it's going to be by title. If check song is not equal to null, we add playlist.add check song, return true. Otherwise, the song plus title was not in this album, which is as it was before. So that is literally it. So it's not particularly difficult in terms of the changes we need to make, but it's more so in the thought process to consider where the functionality should be. So you can see that we've stripped out the array list, but that was in the album class. And we've also stripped out some of the functionality, such as find song, adding songs and so forth, and put that all in the song list inner class itself. And then we're actually just doing the calls to those particular methods as appropriate. So the last thing now to check is to see that this still works. So if we go back to our main method, we should still be able to now run this without making any changes to the code. And it should still work. And of course, the reason it should still work is that all the code was changed internally, the album class. And as far as what we've exposed as the functionality for the album class, the exact same methods are still applicable and it's still actually there and we're still calling those. It's just all the functionality has changed internally. And the main method has got no understanding or concept of the fact that we're now using an inner class instead of the array list being in the album class. And that's one of the beauties about creating things properly the first time. We can make these changes internally without affecting any other part of the application. So just to confirm, I can just go through a couple of functions. And obviously the songs are there. Print out. So it's obviously finding the songs, so it's all working. So that's actually it. That's how to go about actually changing out an implementation. In which case, in this case, which was a array list, which was in the album class, and to adding an inner class, which was the song list class. So that's it. So I'll see you in the next section. We're going to start talking about abstract classes. So in this set of videos, we're going to start talking about abstraction. So abstraction is when you define the required functionality for something without actually implementing the details. In other words, we're focusing on what needs to be done, not on the how it's to be done. So interfaces, as you saw, are purely abstract and they don't specify any actual aspect of the implementation. The actual implementation, of course, was left to the classes that implement the interface, and that's why we use the word implements when we're using an interface. And as you can see, I've got the challenge from the interfaces set of videos, and I'm just going to go through and just confirm that again. So you can see that we've got our interface here. Now this was the interface that originally had the array list, and if you remember, I changed it back to a list, and I changed it back to an array list here just to actually talk about this a little bit more. But again, getting back to the interface defines what needs to be done. It doesn't define how it's done. The how, we actually have to go into the class, in this case say monster, and that's actually implements. That's implementing the iSavable interface, meaning that it's actually going to do the work. And we're getting that error right now, by the way, because as you remember, we actually changed this to a list, but I'll purposely change the interface back to an array list because I want to talk about that. So the iSavable interface, as you can see on screen, provided or specified that there must be a write method that returned an array list of values to be saved, and also the read method, as you can see on the screen then there, that was provided with an array list of values to be restored. So there weren't any other details of how the class should populate or write the array list. No details on what the class should do with the read values either. That's left entirely up to each individual class. You could, really, if you wanted to, set it up so that each class that implemented this interface might do completely different things with the write and read methods. So there's no rules of what's to be done in those methods in the interface, only that those methods have to be implemented in the particular class. But strictly speaking, if you look at this interface, it's not complete abstraction. And the reason is in this particular case, there's a specification that array lists must be used. But in a type language like Java, it's hard to avoid doing that sometimes. But in this particular case, and I explained this a little bit in the challenge, in the previous challenge, the interface challenge, we can abstract this and use just a list. So what we could have done is we could have changed it, and what we did do was we changed it. So we actually removed the need for an array list and actually just changed it. So in actual fact, it was just a list. And by doing that, we abstracted again because we then didn't force the monster class or the player class or any other class that implemented this interface to have to use an array list. They could use any type of list for that matter. And that can be really useful, and I have made a recommendation that you should do that whenever you're using a list of some type in your programs. Generally speaking, in terms of the declaration, it's good to write it like that, and that leaves your implementation open to actually use any type of list, anything that implements that particular interface, in which case there's the list interface, which is part of Java. And just as a recap, we can see that is, if we actually click on this, I'm holding down Command, I believe it's Alt on your Control, on a Windows machine, click on it, and we can go into the actual list interface, which is part of Java. It's quite interesting actually reading some of the code sometimes, and you can see that this is actually the public interface for the list, or a public interface for list, which the other classes such as array list within Java, etc., actually have to implement to actually use. Now obviously by definition, being an interface is abstract, so you can't use a new iSavable or a new list. What you need to do is instantiate a class that implements the interface, and you obviously saw that in the interface challenge. Now Java also allows abstract classes. Now, before we get too much into that, I just want to go one step further and just mention that with this interface, we could have actually taken it one step further because we specified the type to be string. But again, if we wanted to be really flexible, we could have even removed that and made that really a really generic list and left it up to the user, the class that implemented this interface, to actually decide what type to actually use. So I could have quite happily done that, and we could have then gone back to our monster class and actually looked at changing it. We would have had to change a few little things around a little bit in terms of the definitions, but ultimately you could have given that extra functionality, or that extra flexibility, I should say, for the actual classes that were implementing this interface. So keep that in mind, that you can take it one step further if you want to go to that level and leave yourself maximum flexibility, but sometimes there's a bit of a fine line as to how generic you make it and how specific. Sometimes somewhere just in the middle might be the way to go. So as I mentioned, interfaces are by definition in Java abstract. So you can't use the new iSavable or a new list. You have to instantiate a class that implements, the interface. And what we're going to do is I'm going to close this one down now. I'm going to swap over because I've created a new project in IntelliJ for our abstraction. We're going to actually start typing some code because, as I mentioned, Java also allows abstract classes, and these are classes that define methods but do not provide an implementation of those methods. The implementation itself is left to the classes that inherit from the abstract class. So this is different from inheriting from an interface. You can also inherit from an actual class as well. So in the videos on inheritance, we created a very basic animal class and then we extended it to create a dog. Let's see whether we can do something similar now using an abstract class. So I'm going to actually open up this now and create a new class, new Java class, and I'm going to call it animal. And what I'm going to do is I'm going to make this an abstract class. So to do that, we type in the word abstract after our modifier. So public abstract class animal. And we can define the variable. So let's type private string name. We can have a constructor which will pass us the name of the animal. And let's also add a couple of extra abstract methods. And this is the part I want to show you for eating and breathing. So we can put public abstract, again the abstract keyword after the modifier, void eat. And notice we've just put a semicolon there, so we haven't implemented this at all. And public abstract void breathe. Then we can also add a constructor. We can also add a getter, I should say, to name. So there's an abstract class. And you can see here what we're doing is as we're about to see, we're going to inherit from this abstract class, and it's going to let us define behaviors that are necessary without specifying how they are to be performed. And this really ensures that the subclasses, such as the dog, must actually implement them. Because, of course, normally in the normal class, if you're extending from a class, you can create a base method in the class, but there's no requirement for the other class, the class that is subclassing, to actually implement those methods. But by creating abstract methods, we actually are forcing the class that is ultimately going to implement from this abstract class to create those methods for us. And that's why we've actually marked them as abstract. So the other methods and the other field in this case are quite okay, and they work as normal Java code, but we're actually specifying and saying there's some abstract methods here that have to be implemented. So if you did actually refer back to the inheritance videos, you'll see that this is very similar to that. Really the only difference is we've actually marked it as abstract, the actual class definition at the top there, and also we included those abstract methods as well. So to keep things simple in this example, I've actually removed the member variables, brain, weight, etc., just to keep things really simple. Now, if we actually try and extend from this, I want to show you what actually happens. So I'm going to create a new class. I'm going to call it dog. And I'm going to extend animal. And I think I put animal in the wrong place. Animal should have been in our package, so I'm just going to move that, drag it. And it's asking whatever we want to move it to. We want to move it into that package. So I'm going to click on refactor. And that should fix it up now. So we're actually in the right place. But now you can see we've got a different type of error. And if we have a look at that, it's actually telling us that class dog must either be declared abstract or it needs to implement the abstract method eat in animal. In actual fact, there was two methods there it needed to implement. But this little error message is only popping up the first one. So you can see that now in order to be able to create a valid class, we have to implement those methods. So we could do something like, we'll create a constructor first for the dog, like so, and we'll just use the default super to save the actual name, which is in the animal class. And we can do some overrides now. So we can do Alt-N and we can actually go to implement or override. They'll both actually pop up the same things. And you can see now we've got two options here. We've got the two options there. And notice the little descriptions here, or the little icons are a little bit different. So get name, you can see that's like a method, but this one's also a method, but notice how it's got a chunk taken out of it. That's IntelliJ's way of telling you that this is an abstract method. So I can actually select both of those and override them, which then makes the class valid. And I can just put something in the code. Get name plus is eating, and for breathe in, breathe out, repeat. Pretty basic. So that's now made it a valid class, as you can see. And obviously keep in mind that because we did implement the getter for the name, get name in the animal class, it's available in this class when I've actually used it here in the eat method. And likewise for the constructor, I mentioned that we actually called the constructor using the super keyword, which calls the constructor that's actually in the animal class as well. So the important thing here is that not all methods have to be abstract. This is one of the differences between an abstract class and an interface. You can actually mix these up. An interface, if you recall, if you go back and have a look, actually looks like I closed the project. I probably should have just switched over. But with the previous interface, which you saw earlier in the video, it's the entire interface was completely abstract and there's no implementation whatsoever. So there's no opportunity for us to enter fields. There wasn't any opportunity for us to enter any other code. We purely were able just to specify the methods that were going to be used for that interface that a class that it was implementing that particular interface had to actually fulfill in order to make it valid. But as you can see in the case of animal, we can actually mix it up. We can actually add fields. We can add regular methods, or a constructor in this case, but also a regular method, as you can see there with the constructor. But then we can also specify that certain methods are abstract, as you can see there. So in terms of actually using this, it works now as you would expect. So if you go to write some code, we could do something like dog equals new dog, Yorkie. Dog.breathe, again, behave, you would think it would work, dog.eat. And if we actually run that, breathe in, breathe out, repeat, Yorkie is eating. So you can see that it's all working nicely as you would think that it would be. Okay, so that's working as you think it would, but let's take this now to the next step and actually now create another class, which in this case is going to be bird. New Java class, and we're going to call that bird. And we need to extend, because obviously we're using the extends keyword because it's a class, and animal. And create a constructor with works as you think it would, and let's also override those methods. Eat and breathe again, and we'll put for eating get name plus is pecking, and for breathing, well, that's going to be the same, isn't it? So it's breathe in, breathe out, repeat, like so. And of course we can then go back to our main class, main method, bird equals new bird, parrot, bird.breathe, bird.eat. We can run that. We get the results, as you can see. Bird's breathing and parrot is pecking, Yorkie's eating, so it's doing the right thing there. Now birds can also fly, so it could be a good idea to add a fly method to our bird class, but not all birds can fly, so implementing a fly method in the bird class is not a good idea. Better idea would be to create an abstract bird class that extends animal and also has an abstract fly method that individual bird objects can implement as they're able to. So let's go ahead and see how that would work. So we'll go through now and modify our bird class. Close this down to give us a bit of space. Now I'm going to change this up here now where it had public class bird. I'm going to make that abstract. Leave the constructor as it was and also leave the two methods as they were, but also down the bottom, let's add another abstract method. So public abstract void fly. So that's another abstract class at this point. So this is an abstract class that itself is extending from another abstract class. It's implementing the required methods that the animal class requires it to, namely eat and breathe, but it's also defining an abstract method fly that ultimately has to be overridden by another class as well. And of course we made this class abstract, which it needs to be in order to be able to do this anyway. So now that we've done that, of course, if we go back to the main class, we'll get an error because if we just highlight it, you can see what the error is. So bird is abstract, it cannot be instantiated. Remember we said that earlier in the video that you can't directly instantiate a class that is abstract in any way. So what we need to do is actually create another class. So to do that, we'll change this and we'll actually create a parrot class. Come back here and create a new class, parrot. We're going to extends bird. We'll add a constructor. And all we need to do here is, because the other methods are already overridden in the bird class, we only really need to do one. So if we go back there and have a look and go to override, we can still override eat and breathe if we wanted to. If for some reason this type of bird had a different way of eating or breathing, but really all we want to do is override fly in this case to make this class valid. So I'm going to do that, and I'm going to put something like flitting from branch to branch. So it's actually flying effectively from branch to branch. And again, parrot's automatically inheriting eat and breath and breathe, I should say, from bird, so we don't have to re-implement those methods again. But it now has its own implementation for fly. So if we go back to the main method now, we'll now change this so this is actually a parrot instead of a bird. Remembering that parrot is now extending from bird. Parrot. And we'll say it's a new parrot. And now instead of typing parrot as a name, we'll say it's an Australian ringneck. And it's going to be parrot.breathe. That will still work. Parrot.eat. But we can also do parrot.fly now. So if we run that, you can see that there's no errors anymore. We can see now Australian ringnet is pecking, flitting from branch to branch. And just as another example, to show that we could do something different, let's create one more class, a new Java class, and we'll call this one Penguin. And we're going to do extend from bird again. Extends from bird. Create the constructor. And let's just override fly again. And we could put, I'm not very good at that. Can I go for a swim instead? And that's our implementation of Penguin. So going back to the main method again, we could just come down here. We could put Penguin equals new Penguin Emperor, and Penguin.fly. And now if we actually run that, you can see we actually get the message quite correctly still that in the case of the bird, Australian ringnet is pecking, flitting from branch to branch, and we only printed out the fly method for penguin. I'm not very good at that. Can I go for a swim instead? So you can see that's working quite nicely. So I'm going to end this video here. In the next video, what we're going to do is start talking about how this is different to an interface and how you decide whether to use an interface or an abstract class. So I'll see you in that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
Okay, so we're continuing on from the previous video on abstraction, and we created various examples of abstract classes, and it's now actually a good time to bring up what is the difference between using an abstract class and an interface, and how do you actually go about deciding which one to use. So once again, as we've done in previous videos, we need to consider the relationships. The relationships is-a versus has-a or can. So in other words, a dog is an animal and a bird is an animal. So that makes sense to inherit from an animal class rather than implementing an actual animal interface. A parrot is a bird, so again, you would inherit from a bird-based class. Now we've actually done that. But there is actually a problem with this example though. And if you think about it, birds aren't the only animals that can fly. Bats are extremely good at it, for example, and even dragonflies are, and that's just two examples. But a bat is not a bird though. So to get around that, we could rename our bird class flying animals and have bat and bird both inherit from that, but it should be easy to see the problems that could potentially cause. Bats give birth to young rather than laying eggs, so this may lead to having flying animals being inherited by classes called mammals and birds. But not all animals can fly, and you can see we rapidly start to run into difficulties, all because we've actually got it wrong at the base level. So where we actually went wrong here was actually putting the fly method in the bird class. So we go back and have a look. You can see we added an abstract method for fly in the bird class. A bird can fly and a bat can fly, so better design would be to have created a can fly interface which both bats and birds can implement. So let's go ahead and actually do that now. Create a new class, or it's actually an interface, but we specify that and then select interface. We're going to call this can fly. That's our interface, and the interface is going to only have one method, void fly. Now, just a quick note on talking about interfaces. I know in the past I've sort of pushed the fact that they should be called, the standard is to call them I can fly, but you'll actually see examples of that certainly in Java code, but you'll see a lot of examples where they don't actually have that same naming convention. And one way to think of an interface is to name it what it is. So in other words, in this case, it's the can fly interface. It's not the I can fly interface, if that makes sense. One of the reasons that programmers in the past prefixed things with an I for an interface, for example, was for easy identification. But these days with IntelliJ, you can see there it's clearly shown in green to the left-hand side there that it's an interface. So you don't really have to guess that. So for that reason, it's probably better as a rule to not actually put the I there, because in many cases it's just adding extra sort of fluff to your code. It's not adding anything productive, and it could potentially be making code harder to read. So I'll probably go against what I said before and don't use I in front of interfaces unless you've got a really good reason for doing it. Okay, so I've created that interface now called CanFly. So I would actually go back to our bird abstract class. So we're extending animal still, that stays the same, but we now implements CanFly. Like so. And what we do is we get rid of the abstract method for fly, and instead we actually override that, or we actually implement that from the CanFly interface, like so. And we would implement it and we'd put get name plus is flapping its wings. So getting back to our parrot class, we go back there again, we can actually delete this method now, flitting from branch to branch, because it's now going to be inherited from bird automatically. And also then looking at penguin, it actually makes sense to override that and leave that overridden. And the reason for that is we want to implement some specific functionality for the penguin class. And if we wanted to, we could also call the super.fly as well. And if we go back to our main class and run this, you can see the emperor is flapping its wings. I'm not very good at that. Can I go for a swim instead? And the argument for actually leaving the super.fly in for the penguin is that the penguin has actually got those little wings that it can flap, but obviously it can't actually fly. It doesn't get very far. So we can now have a bat class and a dragonfly class that inherit from a suitable base class, and both could then implement the CanFly interface. So you can see that by adding the interface, in this case the CanFly interface, we're actually adding more flexibility into the design to enable us to create other classes, and we're not going to fall victim to the potential problems we would have had trying to get everything to fit into the one class as we did earlier in this video, as I discussed earlier in this video. Now looking at animal, you might actually argue that an animal can breathe and can eat, so that these should be implemented as interfaces, and absolutely that could actually work. You could actually do that. But as these methods are really common to all animals, it makes sense here to include them in the base abstract class and let later classes implement them. So in other words, a fish will implement breathe differently to a dog, so they remain as abstract methods. So that's the reason why I suggest you'd leave that there. So it really comes down to each sort of function of your class as to deciding whether you create an interface for it or whether it should be an abstract method, as the case here is for the eat and breathe methods in the animal class. And just to summarize the differences again between an abstract class and an interface. So an abstract class can have member variables that are inherited, something that can't be done in an interface. Now interfaces can have variables, but they're all public static final variables, which are essentially going to be constant values that you'll never change with a static scope. They have to be static because non-static variables require an instance. And of course you can't instantiate an interface. Interfaces also cannot have constructors, but abstract classes can, as you've actually seen in this example, and you can see it in the example on the screen now. We've got a constructor there. Now all methods of an interface are automatically public, whereas the methods of an abstract class can have any visibility, private, protected, etc. Abstract classes can have defined methods, i.e. methods with an implementation, and you can see that on the screen there with the get name. Whereas all methods in an interface are abstract. Of course, there's no code in abstract methods. All the actual code has to be actually written in the class that implements a particular interface. As you can see, the animal class implemented the get name method, and as a result, that code does not have to be reproduced in all classes that inherit from this abstract class. Okay, so it's time for a challenge. What I'm going to do is I'm going to copy and paste in the challenge because it's quite a big one, and then we'll actually pause the video, and then we'll actually come back and implement the challenge itself in the next video. So I'm going to go to my main method and I'm going to paste some code in. Okay, so I'm going to paste the code in. Okay, so let's go ahead and look at this now. So this is the challenge. So I'm going to get you to create an abstract class which is going to define items that can be stored in a list. Now the class should contain two references to items which are going to represent the next and previous items, which is the case for a linked list. So if you call your abstract class list item, then it would have two member variables of type list item that will hold references to the next or right, and previous, which is left, list items. Now the abstract class will also need to hold a value. Try and be as flexible as possible when defining the type of this value. Now the class will also need methods to move to the next item and back to the previous item, and also methods to set the next and the previous items. Now you should also specify a compare to method that takes a parameter of the same type as the class and returns 0 if the values are equal, greater than 0 if the value sorts greater than the parameter, and less than 0 if it sorts less than the parameter. Create a concrete class from your abstract list item class and use it in a linked list class to implement a linked list that will add items in order so that they are sorted alphabetically. Duplicate values are not added. Now note that you're creating your own linked list class here, not using the built-in Java one. So the rules for actually adding an item to the linked list here are: if the head of the list is null, make the head refer to the item to be added. If the item to be added is less than the current item in the list, add the item before the current item. In other words, make the previous items next refer to the new item, and the new items next to refer to the current item. And if the item is to be added is greater than the current item, move on to the next item and compare it again. If there is no next item, then that is where the new item belongs. So care needs to be taken when inserting an item before the first item in the list, because this obviously won't have a previous item, so you'll need to actually test for that scenario. And you'll also need a method to remove an item from the list. And just as a hint here, if you're creating classes with names such as list, linked list, node, etc., make sure you create your classes before referring to them. In previous videos, we've often referred to classes that we create later, but if you use names that IntelliJ recognizes as Java classes, such as linked list, then it will create imports for them automatically and possibly cause you problems later. So probably a better way is to actually don't use identical names to list and linked list, etc., then you won't run into that scenario. But if you are going to do that, make sure you create them to avoid that problem. Now, an optional task is to create a class that uses your concrete class to implement a binary search tree. So when adding items to a binary search tree, if the item to be added is less than the current item, then move to the left. And if it's greater than the current item, move to the right. The new item itself is added when an attempt to move in the required direction would involve following a null reference. Once again, duplicates aren't allowed. And another hint here is to avoid typing lots of add item lines. Split a string into an array and create your list in a loop, as in the example below, which I'm about to paste in. And just a note about binary search trees, we've only talked about that a little bit. So this would be your case to actually go away and actually research binary search trees, which are very similar to linked lists, but they've got a couple of key differences if you want to actually take up the optional task. You'll actually learn a lot in the process, but in any event, you'll actually see the answer to that with the solution to the challenge that I've actually created. So let me just paste in that code now, which will help you from typing lots of add item lines. And you can see in this scenario here, we've got a string containing all the data we want added, separated by space. We can use the .split function of a string, in which case the delimiter, the character that we want to split it, is with a space. So what will happen is automatically we'll actually get an array of strings which contain an entry for each item. And then we can just use a for loop to go through the actual list. We can go through all the strings in that array and process them whatever you want to do one at a time. So it's just a bit of a shortcut there. Alright, so I know that sounds like a lot of work, but a lot of this stuff we've actually worked on, or pretty well all of it, we've worked on in previous videos. So it's building on the knowledge that you've built up over this course. So go away and see how you get on and see if you can come up with a solution to this. In the next video, I'll actually show you the solution, my solution that I've come up with it, and you can compare it to yours then. So I'll see you in that next video. Alright, so let's discuss the main differences between an abstract class and an interface and when to use either of them. And this should hopefully give you a better overall understanding of both. So firstly, an abstract class. Well, these are very similar to interfaces. You cannot instantiate them, and they may contain a mix of methods declared with or without an implementation. However, with abstract classes, you can declare fields that are not static and final, and define public, protected, and private concrete methods. Now, an abstract class can extend only one parent class. However, it can implement multiple interfaces. Now, when an abstract class is subclassed, the subclass usually provides implementations for all of the abstract methods in its parent class. However, if it doesn't, then the subclass must also be declared abstract. So you want to use an abstract class when, firstly, you want to share code among several closely related classes, animal, for example, with fields name, age, and so on. Or if you expect classes that extend your abstract class to have many common methods or fields or required access modifiers other than public, so protected and private. You may also want to use an abstract class when you want to declare non-static or non-final fields, for example, name and age. So this then enables you to define methods that can access and modify the state of an object, get name, set name, and so forth. And also, you may want to use an abstract class when you've got a requirement for your base class to provide a default implementation of certain methods, but other methods should be open to being overridden by child classes. And as a general summary, the purpose of an abstract class is to provide a common definition of a base class that multiple derived classes can share. Alright, interfaces. So an interface is just the declaration of methods of a class, it's not the implementation. Now in an interface, we define what kind of operation an object can perform. Now these operations are defined by the classes that implement the interface. So interfaces form a contract between the class and the outside world, and this contract is enforced at build time by the Java compiler. Now you cannot instantiate interfaces, and they may contain a mix of methods declared with or without an implementation. Now all methods in interfaces are automatically public and abstract. Now an interface can extend another interface. Interfaces are more flexible and can deal with a lot more stress on the design of your program than the implementation. Now by introducing interfaces into your program, you're really introducing points of variation at which you can plug in different implementations for that interface. Now an interface's primary purpose is abstraction, decoupling the what from the how. And just a couple of general notes here. Since Java 8, interfaces can now contain default methods. So in other words, methods with implementation. Now the keyword default is used mostly for backwards compatibility and static methods as well. Before Java 8, that wasn't possible. And since Java 9, an interface can also contain private methods, commonly used when two default methods in an interface share common code. Alright, so when do you want to use an interface? Well, firstly, when you expect that unrelated classes will implement your interface. For example, the interface is comparable and clonable are implemented by many unrelated classes. Now, another reason to use an interface is when you want to specify the behavior of a particular data type, but you're not concerned about who implements its behavior. Still, another reason for using an interface if you want to separate different behavior. Now, the Collections API in Java is an excellent example of interfaces. We've got the list interface and implementations array list and linked list, among others, and more on this later in the course. Another example is the JDBC API. Now that exists of almost only interfaces. The concrete implementation of methods are provided as JDBC drivers. So that enables you to write all the JDBC code independent of the database, the DB vendor. And you'll learn more about JDBC in this course. Alright, so that's the differences between abstract classes and interfaces. Let's move on now to the next video. Okay, so here is my solution to the challenge, and if you haven't watched the previous video, be sure to do that, because towards the end I typed out the challenge and actually talked about it and actually went through and sort of said what the challenge was, and here it is again repeated on the screen. But if you want to hear more about that, certainly go back and do that. And of course the other thing to make sure you've done is to actually have attempted the challenge, and hopefully you've done that and you're actually watching this video to check your results. So let's actually get started. So I'm going to create firstly, the first base abstract class, and we're going to do this. So I'm going to right click new, as we've done now hundreds of times, and I'm going to call this list item, and we're going to make that an abstract class. Oops. So abstract class for starters. Okay, so we need firstly, we want a list item for the right link, so we're going to do protected list item right link equals null, because by default it won't have a link. Protected list item left link equals null. And notice how we're actually putting references to ourselves in the class. We're creating instances of this very same class within a class. And we want a protected object value. Then we need a public constructor, which is going to accept the object parameter. So just the object parameter, which will be that one there, and we'll click OK to that. So we're setting the value. Now, next we need to actually start talking about the actual abstract classes that we want here. So we need, firstly, an abstract class for next, so that it will return a list item. So list item, so it's abstract list item next. Abstract list item set next as well, which obviously saves the item. We also want one, because we've done a next, we also need a previous, so we do abstract list item previous, which returns the previous entry, and of course we want a set previous as well, so we can actually set that previous link as well to the previous list items. So set previous list item. We actually also want that compare to method that we talked about, abstract, that returns the integer. Compare to list item, so we can compare and see whether an object is the same based on not just a simple comparison, but actually a sort of in-depth one, field by field. Then we just want a getter and setter for value itself, even though that's set in the constructor, and that's not going to be abstract methods, it's just going to be overridden. So we getters and setters, but just for value as well. So that should be our base list item class there. So again, we've got two variables, and they hold references to objects of type list item, the right link and the left link. Thus, you can say that each list item object can hold a link to the previous and next items in the list that we're actually going to be ultimately be saving. And notice that define a constructor for the abstract class as well. Any concrete class that inherits from the list item will need a constructor that sets the value. So it really makes sense in that case, because it needs to be done each time, to put the constructor in this list item abstract class. We will also define a getter, as you can see there. And just a confirmation that the abstract methods define what must be implemented by any concrete class that inherits from this list item class. So again, next returns a reference to the next list item in the list. Set next, where we're passing the parameter of list item, sets the reference to the next item to refer to in the parameter, which is of course item. And previous and set previous does the opposite. It actually sets the reference to the previous item in the list, and then sets the reference, this is set previous, to the previous item to refer to the parameter item which is passed. And again, compare to compares an object to the item, whatever's been passed in the parameter, and returns 0 if they're equal, and also returns a number if the item parameter should sort before the object, which would be negative. Otherwise, it's going to return a positive number. And incidentally, the reason that I've actually declared the fields to be protected rather than private is because we need to be able to access them from our concrete subclass. Now, we could have left the access modifier off, which would have meant that the member variables are package private. So in other words, subclasses in the same package would be able to access them, but not subclasses in other packages. So that's why we made it protected. Okay, so in order to create list items, we need to actually have this concrete class we talked about. So one that actually implements all those methods, and as a result can therefore be instantiated. So let's go and create that. That's going to be a new Java class, and we're going to call that node. So the first thing we need to do is we need to extends from list item. And of course we're going to get a complaint there that we haven't implemented those abstract methods yet. We'll start with a constructor, which just uses the abstract classes constructor to set that value of that object. The next we need to start overriding some objects. So we're going to start with next. Actually, what we'll do is the ones we need are next, previous, set next, and previous, and also compare to. So what I'm going to do is just create the stubs for those by just going in here and overriding. And I'm going to select all of them, 1, 2, 3, 4, 5, all 5 of those there. They're the ones that we need to override. And by doing that, we've now got a valid class, but of course we now need to add the actual functionality itself. So we're going to start with the next method, and all that really needs to do, this is the next item to the right. So we return this dot right link, which is of course a field in the abstract class. And with set next, what we want to do is a little bit different. So we're going to do with this dot right link equals item, whatever was passed to us. And then we're going to actually return that very thing that was actually saved. So this dot right link. Okay, and likewise for previous, well of course previous is pretty straightforward. We're going to return the left link because it's the entry previous. So this dot left link. And for the set previous, no points for actually deciding what this is going to be. It's going to be this dot left link equals the item that's passed, then we actually return this dot left link as well. And that brings us down now to the compare to. And what we need to do there is return that value, which was -1 if the item parameter should sort before the object. Otherwise, we're going to return a +1 if that's not the case. And of course, we return 0 if they're considered to be equal. So firstly, we're going to do a test for null. So we put if item is not equal to null, then we're going to return string super.getValue dot compare to, and I need another string dot compare to string item dot get value. Otherwise, we're doing an else, return a -1 because it's actually null, and therefore it has to be in that sort order. Negative because any value is going to be greater than null effectively. So you can see that we're actually using the get value method to actually figure out using the compare to and comparing that to each item. And in case you're wondering, we're going to be actually using strings as our values, even though we've defined it as type object. So looking at our list item, we've defined it as type object there. But in the node, we're actually going to be passing this as string. So that's why I can actually use string here for a comparison. And dot compare to works nicely with string as well. And again, the next and previous methods are basically just getters. And the set next and set previous methods are very similar to setters in what they're doing. But they're also returning the values as well, and returning the appropriate reference variable as well. And you might be wondering why we're doing that, but don't worry, later on we'll actually talk about that. And it's not going to actually affect your solution. It's done really for more convenience rather than being essential to the program. So if you haven't returned it, that's okay. And just a confirmation that the compare to method looks actually like a lot, but it's actually quite easy. It's easy to implement here because we're storing strings as our value, as I mentioned, and the string class already has its own compare to. So if you were writing a special class, your own class, and not using a string class in this particular scenario, you'd have to write your own compare to operator. But in this case, because the string class itself has got that built in, all we really need to do is use the dot compare, and that's going to return the 0, the -1, or the 1, depending on the actual value. And the other thing we're doing is, if a null was passed, we are returning -1 automatically because we can't test that, but negative is always going to be that any value is going to be greater than null. That's why we're returning -1. So at this point now, we've got a concrete class that extends our abstract list item, and we can create objects of type node and build structures by making the node's next and previous links point to each other. Probably a good idea at this point, before we go ahead and actually do that, before we create our linked list, to define an interface that any structure using our node objects will implement. And we can actually use that interface later on. So let's actually go ahead and do that. So I'm going to do a new Java class interface, and we'll call this one node list. We're going to start off, we're going to have a get root, which is going to be the actual list item itself. So list item get root. And another function we need obviously is the add item. That's going to be list item. We need a remove item, which is also going to pass the list item. And we need a void traverse. So there's some way of actually going through the list. Traverse list item root, like so. And that should be it, because any data structure that we create must have a starting node. We know about that, and that's why we're putting in the list item, the get root. In the case of the linked list, this is often called the head of the list, but using the term root is also used a lot, and actually applies to binary search trees. If you did your research on that, you probably noticed that. We also needed methods to add and remove items to the structure, and that's what we've done that in our interface, and that's why we've used add item and remove item. And finally, we have that traverse method, which I mentioned, which will start at the root and print out the values of each item in the structure, so it traverses through the list, if you will. And I spelled traverse wrong. Traverse. Okay, so let's now create a linked list class. And I mentioned before about actually using the right names and getting confused with what is the linked list from Java and our own interpretation of linked list. So I'm actually going to call this my linked list, just so there's no confusion with the linked list that's actually built into Java and the linked list class that we're actually creating here. So public class my linked list implements node list. Obviously we're getting an error because we haven't implemented everything yet. So we're going to start off with the private list item root equals null. That's going to be our basic, our head record or our root record. And we need this constructor. It's going to be just that root item. We're going to set the value for the root item to start it off. Then next we need to override those other methods as well that were part and parcel of the interface. So I'm going to do that. So we'll click implement, and we've got 4 there, as you can see, that we actually must override to make it valid. So we're just going to do that. So some of these are easy. The get root will be just this dot root. Going to return the root. So what we need to do for that, for an add item, we need to check for the empty list item first and add a new item as the head of the list if it was empty. But if the list wasn't an empty, then what we need to do is compare each item in the list with the new item to work out where the new item should be inserted, because remember, we're sorting it in a particular order. So the way we'll do that would be, we would change the return for now, and we'll start by putting if this dot root is equal to null. Well, that's easy. So it's going to be just as a comment, the list was empty. Was empty. So this item becomes the head of the list. So if that's being the case, we can just put this dot root equals item, which was actually passed to us. I'll call that new item, just so we're really clear what we're trying to do here. So that's the new item that's passed to us. So in that case, because the root, we didn't have any other entries, this is the first time it's been used, we're setting this to become the head of the list effectively. And at that point we can also return true because we've succeeded in adding the item. Then we'll put an else, or we don't even need to put an else because we're going to start the code, because the code is only going to get down to here if that first block of code wasn't actually called. So now what we need to do at this point is we need to start comparing from the head of the list. So we're going to type list item, current item equals this dot root, so the first head item, the head of the list, while current item is not equal to null. So while we've still got the ability to actually link through our items, because we're going to be going through and comparing them one by one, so we need and going through to the next and the next, so on. And if we reach a null, that basically means that there's no more entries to actually go through in the list. So the first thing we need to do then is do a comparison. So int comparison equals current item dot compare to new item, the item that has just been passed to this method. And now we start doing our test. So we do if comparison, remembering that returns a negative number, a 0, or a number that's greater than 0. If comparison is less than 0, so we'll do that one first. And less than 0 is if the new item is greater, so we need to move right if possible. So we put if current item dot next is not equal to null, so if there's somewhere we can actually go forward, in other words, go to the next item, we're going to go to current item equals current item dot next. We need to continue processing. Otherwise, we've reached the end. We can't actually go to any other records, so we've actually reached the end of that list. So what we can do is we can put there is no next. So insert at the end of the list, which effectively is where we're at now. So we can put current item dot set next, new item, and the new item dot set previous current item, and then return true. So you can see what we've done there. We've pointed to the current item which we've reached, basically got as far as we can. There's no other entries when we go to dot next because we received a null. So we set the next now to the new item where it was null. The new item that we've just inserted currently can go back to the previous item, if that makes sense. So just as a recap, the current item, we're at the last entry in the list. We're setting the next, so there's another record which is a new item which was passed to this method, but then we're also setting the set previous entry for the new item to point back to what was then the current item, if that makes sense. So we can traverse and go back. So if we didn't do that, the new item previous would be set currently to null, and it would be sort of like an orphan record and it couldn't go anywhere. So that's why we're doing it that way. So that's the first comparison if the answer we got was less than 0, but we also need to do another one. We need to come back here and put else if comparison is greater than 0. So in other words, new item is less. So we need to try and insert before. So we need to do the other thing. We need to go through and do a test for null, but going backwards this time, going to previous entry. So if current item dot previous is not equal to null, there would be current item dot previous dot set next new item. We also do then a new item dot set previous. The new item dot set previous, which will be current dot. Oops, I put an extra bracket in there by mistake. Which will be current item dot previous. The new item dot set next current item, and current item dot set previous to be equal to new item. So again, what we're doing is we know that we have to insert this before. So if the current item dot previous returns something that wasn't null, so it still returned a record, then what we're doing is we're setting the current item dot previous, what was the previous entry, pointing to the dot next from there to set that to the value of new item, which of course is the item that we've actually added to this, or we've passed to this add item. And then we've gone to the new item and set the set previous link for that to point to what was the current items dot previous, if that actually makes sense. And then we've done the same for dot next. So we're actually pointing with the dot next for the current item, and then current item dot set previous item. So I know that sounds confusing, but essentially what we're doing is we're inserting the new item basically before what was the current item. And then the other thing we need to test here is the else, which would be else. And in this scenario, the node without a previous is the root. So if we got to this point, it means that we've got to the very first record and there is no previous. So if that's the case, we need to actually make this new item effectively become the new root. So we do new item dot set next, this dot root. Then we do this dot root dot set previous to be equal to new item. And then this dot root becomes equal to new item. So you can see what we've done there. So in that case, what we've done is we're setting the new items dot next to point to what is currently the root record. And that's because we're inserting ourselves, we're becoming the root. So we need to point to what was the root. So when you navigate and traverse, it actually goes to that entry. And then obviously the set root, we're setting the set previous to point back to the new item because it's now not going to be the root anymore. It's going to be sort of the second item, and it needs to have a previous link to a new record that we're adding, the new item. And then lastly, we're setting this dot root, which is our head, the head of the list, to become this new item. So that's the comparison for greater than 0 where new item was less. And then the other thing was, in the last scenario, is actually quite easy because we've already tested and then they're equal. So at this point they're equal, and we actually don't want to actually add them if they're equal. So we're going to put new item dot get value plus is already present. Present, not added. Because we decided we didn't actually want duplicates, and we're going to return false there. And incidentally here, I'm going to return true, because in both cases, whether we found the record at the head or whether we actually just inserted it previously and fixed all the other links up, in both cases we were successful there, so we're actually going to return true. And outside of all this code here, which we shouldn't hit anyway, outside of the while loop as well, we're actually going to there put return false, just to fulfill the method, so the method's happy with that. And that's it. So that's the add item, which is quite a bit of code there, but hopefully you understood that also based on linked lists, which we talked about in previous videos as well. All right, so I'm going to stop this video here, and in the next method we're going to actually look at some of the code we've actually typed, and I'm going to show you some of the shortcuts you can actually use to reduce a bit of code in scenarios where you're actually doing things like this. So I'll see you in that next video. So in the previous video, we started our abstract class challenge, the solution, and I want to actually finish it off hopefully in this video. But before I actually continue on with the code, there is actually a way to shortcut a little bit of this code. And I'm talking specifically about the add item method, which is of course in the my linked list class that we created in the last video. And the reason that we can actually shortcut the code is relating to the methods set next and set previous. So of course, if I click through to those, we actually go to the abstract class, and that's our list item, set next and set previous, and of course we implemented that in our node. So we go into the node, you can see set next, we're actually setting the item, and then we're actually returning the item as well, and it's the same for set previous. So because we're actually returning that reference in here, what we can do is we can actually shortcut some of our actual code. Because at the moment you can see we've got, every time we actually add a new item, we've got to set the set next and the set previous, unless of course it's a new item for the first time, but most times we're going to be executing both of those. So we can actually shortcut that by actually doing something like this. We can actually put dot set previous and then pass the current item as well. And that's actually an abbreviation instead of having sort of 2 lines, they're doing it all in the 1 line. And again, this relies on the fact that the method is actually returning the right item, so we can actually achieve that. So we're returning that, and then we're setting the set previous, we're calling the set previous method on the item that's been returned from the set next, if that makes sense. So we're actually doing that as well. So that's the first one we can actually change, but we can also make a change also down here. We can do the same thing for that. We can do set previous. Like so. Then with this one down here, we can do exactly the same thing again. Like so, which abbreviates it. And then the final else down here can actually do the same thing to that as well. Just a way to abbreviate the amount of code. And again, it's reliant on the fact that we're actually returning the item and then we're calling the method based on the item that's actually returned. Okay, so in order to actually test this code, we actually need to actually start writing some code for our traverse method. And it's actually not that hard. We can start off by putting a while loop. So we start to see to make sure we've actually got some data. So while root is not equal to null. Then we're going to do systemout.println root.getValue. So then we'll do root equals root.next. To proceed to the next entry. So that's in the case where there was some data, but it's probably going to be wise to actually also test to see whether it's null. We can actually put a message to that effect. So we can put something like if root is equal to null, then we'll change that to the list is empty. And we'll change this here to an else while, and I'll indent that code. Then what I'll do is I'll just actually put another semicolon in there. Like so, and it automatically gets fixed up as you saw by IntelliJ. It actually indented that for us. And now we should be able to output the actual linked list, but also display if it's actually null. So let's go back and actually start running some code to test some of this stuff. So I'm going to go down to our main method, and you remember that we wrote that code at the start for the split code. I'm going to start typing below that. So actually, I'm going to actually type above that because we're going to actually be adding to that. So I'm going to actually put it here. So I'm going to type linked list, my linked list equals new. List equals new, my linked list, null. So we haven't actually added anything yet. And if we do a list.traverse, list.getRoot, let's see what actually happens. So we'll actually run that first. The list is empty, so it's correctly showing us that there's no data in the list, which is good. We're going to leave that code in there for splitting the various capital cities of Australia. But what I'm going to do now is actually put this code in here now, write some code and actually put it in this place here. And we're actually going to add the item to our linked list, to my linked list class. So it's add item. We're going to create a new node, which of course is our list item, the class that actually implements the list item abstract class. So it's the class that is actually, if you go back and have a look, node, we're extending from list item, and of course list item was our abstract class. So going back to that code, so we're going to add a new node, which is the actual capital city in this case. So that should add the data there, so you can see. And just a confirmation, we talked about that briefly, but the string split method returns a string array, as you can see on the screen on line 63. And it returns a string array containing all the individual items of the string that we defined in line 61. So you can specify the character that separates the items. You can see on line 63, after the dot split, I've actually got a space. So the space is effectively the delimiter, or the character that sort of separates each key string in that actual big string itself. So now we've done that, we'll actually put another list in there, list.traverse, and let's put list.getRoot. So we'll actually go through now and actually run it. So the first time we ran that, of course, we passed the list, which was effectively at that point null. But now if we do this, we've actually got some data that we've added, so we should get a different result. And you can see we've now got the various cities. We also got an error message here to say Canberra is already present, not added, but the rest of the cities, Adelaide, Brisbane, Canberra, Darwin, Melbourne, Perth and Sydney, are actually added in the correct order. And of course the reason that Canberra come up as a duplicate was that we actually had it 2 times in that list, purely to confirm that that would actually work. Okay, so next we need to go back to our myListLink class. We need to implement the remove item. Currently it's not actually implemented, it's just returning false. So what we need to do is be able to actually delete items. Now, removing items is relatively straightforward with a linked list. We traverse the list until we find the item to be removed. Then we set the previous link to point the where our item to be deleted points, if that makes sense. So we basically are just sort of filling in the gaps and making sure that we're not actually creating any orphan records in the linked list. So again, what we're trying to do is set the previous link to point to where our item to be deleted points. So let's go ahead and actually do that. First, I'm going to test if it's null. So if item is not equal to null, we're just going to print out a message. So deleting item plus item.getValue, like so. And next, we're going to do a list item, current item equals this.root. So start at the top, basically, the very first entry, while current item is not equal to null. So while we've still got some records to basically go through. And then we're going to type int comparison equals current item dot compare to item, which was the list item that was passed to this method. If comparison, so remembering what we're trying to do is actually find this item in the linked list, so we can't do anything until we actually find this specific one. And remember, we wrote the compare to function so we can actually do an exact match to make sure that we're deleting the right record. So if comparison is equal to 0, then that means we've actually found the record to delete, or found the item to delete. But we need to do a test to see whether this is the root. If there's only one entry in it and this is the root record, we need to do some special processing there. So put current item equals this.root. So if this is the root record, the very first, the head in other words, then we're going to type this.root equals current item.next. So we're basically making sure that we're setting root, what is going to be the new root, to point to what currently is pointing to the next record, if that makes sense. So we're deleting the first entry, the root entry, and we're pointing it automatically, so it's actually pointing now to what is the next list item that list root is currently pointing to with .next. So we're setting that, but we haven't actually deleted it still yet. So we do else current item .previous .set next current item.next. So again, what we're doing is we're looking at the previous entry, because this particular record, so assuming this isn't the root record, we're looking at what is the previous entry, and we know that there is a previous entry because we've already tested to see whether there's a root, and we're setting that to point to what is the current item's next. So in other words, we're bypassing this record effectively, this item that we're actually going to be deleting. And then what we need to do then is do a test for null. So if current item.next, if that's not equal to null, we do current item.next.set previous current item.previous. The same thing there, we're actually doing the other side of the coin. For the next item, we're setting that to actually point to the current item's previous, if that makes sense. Sounds a little bit confusing, but we're just making sure that both pointers, the previous and the next, are actually now still pointing to the right places. So now that we've done that, in the case where we did have a direct comparison, we can return true, because we did find the record and we were able to make those changes. But otherwise, we need to do another check. We need to do here, else if comparison is less than 0, then that just means we haven't reached the point in the linked list yet. So we put current item equals current item.next. So basically we want to continue navigating through the linked list to see if we can find the record. But otherwise, effectively, if comparison is greater than 0, comparison is greater than 0 at this point, it means we've got past the point where we could have actually deleted it. I spelled that wrong. So basically here, we're at an item greater for sort purposes than the one to be deleted. So the item is not in the list. So we've reached past the point of where it would have actually been in the list based on the sort criteria. So we're going to return false at that point because we can't do anything else. We know that we've gone past that point, like so. And put a final test in and return false. We didn't actually find anything without finding the item to delete. So that's basically it. That's the remove item. So to test this, let's actually create a list of numbers in our main method and actually just run through it and actually see whether it actually works. So I'm going to go back to the main again, below the other code we've added. And actually for simplicity purposes, let's just do it this way. Let's just put this in here. And I'm going to put 57398210046 because all the other code's actually there to create our linked list. So we actually run that just to make sure it's actually working. So we're getting the data, you can see it's sorted in the right order, which is good. So let's actually just, what I'm going to do is I'm going to paste in a bit of code here just to save us a bit of time. So let's actually just paste this code in. And you can see what I'm doing here is I'm actually removing an item, printing out the list, removing an item, removing more items, and actually just running it through. So let's actually go through and actually see what it does. So you can see in the first case at the top, removing item 3. So that should leave us remove 3, 0, 1, 2, 4, 5, 6, 7, 8, 9. Removing item 5, 0, 1, 2, 4, 6. So 3 and 5 are deleting. Deleting 0, 4, and 2. It leaves 1, 6, 7, 8, 9. Deleting item 9, 1, 6, 7, 8. Deleting item 8, 1, 6, 7. Deleting item 6, 1 and 7 is only left. And deleting item 1 leaves only 7. Then the last entry, we're actually deleting what is left. So the last entry, the reason why we haven't actually specified the number here, we actually called it list.remove item. We called it with the root entry, basically the only one that was remaining, which was the number 7. Deleted that, and the list is now empty, so it's actually working. So I'm going to actually end the video here. I was actually going to actually show the search tree in this video, but I'll actually go ahead and actually do that in the next video. So that's the one where we're actually going to create the optional search tree. And I need to actually talk about the differences which are going to be in the implementation of the add item, remove item, and traverse, and it really needs its own video. So I'll see you in that next video. So this is video 3 of the Abstract Class Challenge, and this is the optional section where we're actually looking at implementing a search tree. Now the search tree is very similar to a linked list, but the differences are mainly in the implementations of the add item, remove item, and traverse methods. So what I'm going to do is actually create this search tree class first. Then as we go through it, I'll actually explain it more. Then I'll actually show you a diagram of how a search tree works compared to a linked list. So we're going to start off writing some code though. So we're going to create a new class, Java class, and I'm going to call it search tree. And this class should actually implement node list as the other one did, as our my linked list did. So implements node list. So we've got the right methods that we need to override. And we'll start off with a private list item root equals null. And we'll also have a constructor which is going to be passed the root item, which will set that to the root or to the head, as we did in the my linked list. Now let's override the necessary methods. So we're going to just do a command N and override. And I'm going to be more specific, I should actually select implement, even though you can get to both menus. But when I select implement, we only get methods that can be implemented, which come from the correct place, node list. So we'll do that. We'll select those. And in terms of functionality, firstly, the get root is obviously very simple. That's going to just literally just return this dot root. And we've obviously got the other methods now. And we'll actually start going through those one by one. So we'll start off with the add item method. Now this has actually got the same structure as in the case of the linked list, but instead of actually breaking and recreating links to insert, we're actually going to keep traversing the actual tree itself. So moving left or right as appropriate until we reach a node that's null. So let's talk more now about what this search tree is before we actually go too much further. So we're looking at implementing a binary search tree as opposed to a linked list. So what I'm going to do is bring up an image on the screen now, which is this one. And we'll just talk a little bit about that and how this actually works, because traversing a binary search tree is not really as straightforward as it is for a linked list. If you recall, the linked list traversal just involves going from node to node until you get a null reference. So either going using previous to go back or next to go to the next entries until you find one of those is null. Then you've reached either the start or the end of the list. That's the case of a linked list. But traversing the search tree involves actually visiting every node to the left, then the root, and then every node to the right in the same way. And you can see the example of that on the screen. So if we just go through what this binary search tree does. So from the root, at the top here, you can see we keep traveling left to visit Adelaide. So we're actually moving down, going left, 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 left until we get as far down as we can. We then go up to Adelaide, Adelaide's parent, which is Brisbane. So note that we didn't go there directly. We went all the way down and came back up to Brisbane. and it's left tree, we go right to Canberra. So you can see, and Canberra's got no children because at this level. So we visit Canberra and then onto its parent, which is Darwin. So again, it's going back up to Darwin again, as you can see there. And having visited Darwin and its left tree, again, having gone down that way, we go right towards Perth down here. And as Perth's got a left child, we're actually going to visit Melbourne. Melbourne's got no children, so we visit its parent Perth again. Having visited Perth and its left tree already, we actually come down here and go right to Sydney. And as Sydney's got no children and we visited every node, that's the end of the traversal. Now, if we actually printed the value of every node that we visited rather than pass through, and there was a difference there, we get the cities in alphabetical order. But the big difference is there's no links back from a child to its parent. So when we get to Adelaide, when we get down here, there's no way for us to know we got there via Brisbane. So this makes an iterative traversal of a binary search tree extremely complicated because we haven't got the direct reference, using a .previous, for example, that we would have in a linked list. However, if you look at the tree with Darwin as its root up here, this is made up of a left tree with Brisbane as its root and a right tree with Perth as its root, as you can see the two left and right there. So we can then describe Brisbane's left tree as a tree with Adelaide as its root with no children, and the same for Canberra, Melbourne and Sydney. So therefore a tree can be described as a root with optionally a left tree and a right tree. Now the tree in this slide on the screen there now shows the Darwin tree, which consists of the root Darwin plus the Brisbane tree and the Perth tree. So I hope that actually makes sense as to what we're doing here, the differences between the binary search tree. And I'll talk more about the advantages of a binary search tree as we go through this as well, particularly towards the end of the lecture, because it is actually a very important part of database management systems. They use binary search trees, so it's a good skill for you to have. So what we're going to do, given that we need to actually continually go back through some of these nodes, we're actually going to write a recursive function. So any definition that actually includes an object in its own definition is known as a recursive definition, and objects that can be defined recursively can be processed recursively. So what we're going to do is write a recursive method to help us traverse through the list. So to do that, I'm back here in search tree. So the traverse code is going to be, so that's going to be recursive method. If root that was passed to us is not equal to null, we're going to traverse root.previous. And we're going to actually also print out root.getValue. That should be print line, not printf. And traverse root.next. So looking at that code on the screen, and bringing back the image again. So when we call traverse for the first time, the root's going to be Darwin. So what is passed to it as a parameter is Darwin. So if this is not null, which in this case it won't be, so if that's the case, we come down here and traverse is going to be called again with .previous, which is the left node of Darwin, which in this case is going to be Brisbane. So this is also not null, so traverse is called again, so that goes through again, and it's actually called again with Adelaide as its root this time. So Adelaide gets called, the list item for Adelaide gets called to the traverse method, but this eventually ends up being null, because we can't actually go to a previous because there is no previous for Adelaide. So this is null. So because it's the code is, if it's not equal to null, we'll do this. It won't be doing any more processing at that point. So traverse returns to the line after traverse in that case, which is Adelaide.previous, and prints the value of Adelaide. And so because it's finished at that point, it's then going to print out this line there, and the current line is going to be Adelaide. So traverse is then called again this time. This is the next line with Adelaide.next. That's null, so the invocation of traverse returns to the line after traverse, which is Adelaide.next. So there's no further instructions, so this invocation of traverse returns to the point after traversal, which is Brisbane.previous, and so it prints Brisbane. It then calls itself with Brisbane, Canberra as the root, and so on. So I know that sounds complicated, and there's a bit of information out there to suggest that recursive methods really are complicated, but all you really need to look at here is consider is that a recursive method is just a method. It's just a method call like any other method call, but we just happen to be calling ourselves again, calling another copy of ourselves, if you will. So to test the traversal method, we can change the declaration of list in main to be a search tree. So let's go and do that. So at the moment we've got a list here, my linked list. Let's change that actually to a search tree. And what I'm going to do there, let's actually just change this variable, we'll refactor it. Rename, and we rename that to tree, like so, press enter, and we're going to change that so it's not a linked list anymore, it's obviously going to be a search tree. But before we actually run this, now we've uncommented it and got it ready to go, and what we need to do is actually add our add item method. So we need to go back to search tree, and come here into add item, because at the moment it's not actually doing any processing, and I'm going to actually paste some code in, then we'll actually go through the code. So this is the actual code that I've pasted in for the add item, which is different for the search tree than it actually is for the linked list. And the major difference is that it's very similar, so it's got the same structure like it has for the linked list, but instead of breaking and recreating links to insert, we don't actually need to do that. So we just keep traversing the tree, moving left or right as appropriate until we reach a node that is null. Once we reach the end of a path through the tree, this becomes the position to insert a new item. So you can see the code there. Firstly, we're checking for null, which is very similar to what we did in the linked list. If it's empty, our item becomes the head of the tree, and then we return. Otherwise, we start comparing, which again is very similar, and we go through actually making a while loop, checking to make sure that it's not null, and there's a bit of a note about that I'll add shortly. So the comparison, we're using the .compare to, which was the same. If it's less than 0, then it means that the new item is what we're actually using here. If that is actually greater, we actually have to try and move right if we can. So we're doing a test. Firstly, to see whether .next has got something. If that's not equal to null, and if it has, we actually move on to the next record. Otherwise, there's no node to the right, so we know at this point, because it's a null, we can actually add our item. So we do that, then return true. Otherwise, if the comparison is greater than 0, then that means that the new item we're trying to add is less in a sort order perspective, so we need to try and move left if possible. So if the current item's previous is not equal to null, we go to the previous entry. Bearing in mind we're in a while loop with both of these, so we're going to continue to do that until we get to the point. Otherwise, else, there's no node to the left, so we can actually add it at this point. So we actually then use the .set previous for the new item to actually put it in that spot, and then we return. And of course, we decided in the my linked list that duplicates we wouldn't add, and we're doing the same thing here. So if comparison actually returns 0, it means the item's duplicated, and we don't try and actually add it again. So that's actually the add item. So basically, whereas the insertion into the linked list involved changing next and previous references, as I mentioned, unless the insertion was at the end of the list. In the case of a search tree, insertion is always going to be at the end of a path. So you keep going either left or right until you can't go any further. So in other words, until you actually find a null and you put it in there. But one consequence of that, and this is what I wanted to bring up about the while loop here, is that the while loop is never going to terminate naturally. So the program is going to return out of it. As you can see, we've actually got returns in there. In this case, for the 3 scenarios with the compare. So that's not a problem, and our code is going to work fine. But the condition, just want to make it clear that the actual condition, while current item is not equal to null, it can never actually be false, because we're always checking for null before moving left or right. So technically, we could have written the code as while true and remove the need to have the return false at the end if we wanted to. But I've left that in there because I think it's more readable. That's certainly personal preference there. Okay, so that's the code for add items. So we should now be able to go back to our main, and we should be able to run this, and we should hopefully get a result. So if we run this, we get things in the correct order. So it's actually working fine now. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. And just to confirm, I'll comment that out and go back and put in our original string and run that. Canberra is already present, so we're not getting duplicates added. Adelaide, Brisbane, Canberra, Darwin, Melbourne, Perth and Sydney, so it's actually sorting in alphabetical order for that as well. So as you can see, I know it looks complicated. You might look at that and think, well, is this really that simple? But that's really all there is to a recursive method. They sound complicated, and when I was first introduced to them, I found them a little bit overwhelming to get used to, but really, it's just a method call like anything else. It just happened to be calling itself rather than another method. That's the way to really treat it in this case. And just out of interest, it's actually possible to write a linked list recursively as a root followed by a linked list. And the linked list traverse method could then be rewritten. So we'll just quickly go through and look at that. So that's our traverse method for our my linked list. So I've actually just commented that out briefly. So we can actually rewrite that as this: if root is not equal to null, we can actually print root.getValue. Then we can just do traverse root.next. That's that simple. We could actually do that if we wanted to, but generally it's not a good idea to do that due to the depth of the recursion. In other words, how many times it's calling itself. So a well-balanced binary tree with billions of records, billions of nodes, would have a maximum depth of around 63. With like in a huge database, if we had this many records, I can't even actually print it. I can't even say it because it's so big. It would only take 63 sort of levels, if you will, a depth of 63 to actually go right through all those records. But with a similarly sized linked list, it would not start to return until all the nodes had been printed. So it'd have to go through the entire linked list and the stack's going to overflow well before then. In other words, you're going to crash. So you do need to make sure that recursive functions are only picked for certain functions and not sort of just used everywhere. In this case, for a linked list, it doesn't make sense to actually use one because you're going to crash once you start getting a substantial number of records. So I'm going to just undo that. But again, for the binary tree, it's actually optimized for that. And even for that many large number of records, it still is only going to be at the maximum 63 deep, which would be fine for most, most platforms that are running in Java. This brings us to the next solution at the moment with the remove item. And it was pretty simple in my linked list. There wasn't really a lot to it. If we go back and have a look, there's a bit of code there, a bit of testing, but it wasn't particularly complicated. But with a search tree, using the binary tree, it actually takes a lot of thought, and there's several conditions that we really need to consider. So first, we need to think that if the item to be removed has no children, then the link to it can be set to null. This is fairly trivial, because obviously if there's no children, but we do need to keep a note in that case to the item's parent, because there's not going to be any link back to that parent otherwise. But if the item to be removed has got only one child, that's either pointing left or right, then removal is just a case of setting the item's parent to point to the child. Again, that's pretty straightforward. But the big scenario is if the item to be removed has both a left and a right child, then removal is not that easy because we need to ensure that every node to the left and every node to the right is greater than its parent. So basically there's quite a bit of work involved to that. And there's actually an algorithm to do that. So what I'm going to do is paste in some code now just to actually show you what we need to do. Then we'll actually just go through and explain what's going on here. So I'm just going to paste that in. And perform removal we'll actually add in a minute. So basically, there's a few steps involved there. So we need to, first for the item to be deleted, we move to the right subtree and we keep traversing left until we reach a node with no left child. This is then the smallest value in the right subtree. Then we set the value of the node to be deleted to this smallest value, and everything to the left is already smaller than that, and as a result, this is the smallest value of the right subtree, and everything to the right is greater than it. And then we finish off by removing the smallest node, which is easy, as it's got either no children or only has a right child. Now note that we're not actually removing the item to be deleted, we just set the value of that value to that of another node, and we actually remove the other node. So this method's basically traversing the tree, moving right or left as appropriate until it finds the item to be deleted in this case. And before the actual current item is advanced in the appropriate direction, left or right, the parent item reference is set to point to it. And we're doing it that way so that it eventually finds the item to be deleted, and we can also have a reference to its parent. So this is only determining the items to be removed. The actual code to remove the item is actually quite big, and I'm going to paste the code in there. It's quite detailed, as you can see on the screen. And I'm going to talk about one of the ways that database management systems get around this to keep performance high. So basically, we actually remove item from the tree. So if the item.next is null, there's no right tree. So we make the parent point to the left tree, which can be null. So if parent.next is equal to item, parent.setNext, as you can see there, item is right. Otherwise, if the parent previous is equal to the item, again, item is what we passed to it, then we set the parent set previous to the item's previous. So we're actually sort of removing that link and then adding it again. Otherwise, at this point, the root is now set to item.previous because parent must have been the item, which means we're looking at the root of the tree. And I'm not going to go through all this code there now, but basically there's an else there. We're looking for it in the other direction. In the previous direction, we're sort of more or less doing the opposite. We're actually going down the left tree at that point. And we get down to the else. And this is whether either the left nor the right were null. So deletion is now trickier. So we've actually got two ways to look at it now. So from the right subtree, we need to find the smallest value, i.e. which is the leftmost. And you can see we go into item.next there and using a while loop to actually go through until we actually get through to the last entry using current.previous. Then we actually put the smallest value, which is current.getValue, into item.setValue, using item.setValue. Then we actually delete the smallest item. And again, there's no actual delete as such. We're actually just changing the pointer effectively. And you can see otherwise, if we weren't in the situation where leftmost parent wasn't equal to item, we actually set the previous to the next record from the current one that we're actually going through. So I know that sounds incredibly confusing, but the bottom line is binary search trees are a lot more complicated as a result of that. And deleting an item is way more complicated in a binary search tree. And a lot of database management systems that actually use binary search trees, they don't actually delete the record straight away. So they're often flagged as being deleted, which means it's just like a flag set in the record. and they're actually ignored in searches and queries as a result of that. And it's actually the actual deletion, the physical deletion of the actual data only occurs, perhaps during out of hours maintenance procedures, recompacting or re-indexing the database. And because you can imagine with all this code, if there's hundreds or thousands or millions of records, it's going to take a long time to process. So again, pick your poison. You can't always choose. Part of becoming a good programmer is learning the best solutions, best code to tackle a particular solution, and that will come over time and with more experience. So I don't expect you to fully understand the binary search tree. If you sort of understand what's happening at a high level, then you're probably on the right track here. And you'll find out more about binary search trees and find out more about this code as we move forward in the course, because a lot of it will start making more sense as you just spend some time working with the concepts. So just before we finish off, now that we've actually added remove item, we should actually be able to remove some of these things. If I just comment this out again, put our numbers back in again, we should now be able to, I'll comment that out, and this code should all now work for us. So uncomment that, and we should be able to run all that and get the same results with deletions. And you can see we've got deletions, deleted item 3, 1, 2, 4, and scrolling all the way down, deleting item 1. Deleting item 1 was the last entry. Deleting item 6, you can see 1, 6, and 7 left, 1 and 7, and eventually we ended up with an empty list. So the code's working fine. So that's it. That's abstract classes and the challenge. And again, don't be too stressed if you don't fully understand the search tree. I've deliberately thrown that in to sort of show you some more advanced concepts of Java. The main thing was to focus on the first sort of 2 videos, which was the basic component of the challenge, and I hope you did well out of that and also got a lot out of this. So that's now the end of this section. In the next section, we're going to be moving on to generics, which is quite an exciting concept of Java. So I'll see you in that next section.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. Will be a star freelancer.
So we're now going to start talking about generics. So what are generics in Java and why would we want to actually use them? Now actually, as you'll see in a minute, we've already used generics so far in the course and they actually are incredibly useful. So just as we can create methods that take arguments in Java and we can replace the parameters that we declare for the method, generics allow us to create classes, interfaces and methods that take types as parameters called, unsurprisingly, type parameters. So different to other parameters, we're talking about type parameters. So you've seen in previous videos when we created array lists and also linked lists, this in use, but just to show how useful they are, we're going to start with an array list example that doesn't use generics. So we're going to create an array list populated with integers and a method that prints the contents of the array list doubled. So let's go through and write that code. It's a good idea to see that first before we actually go ahead and use generics. So I'm going to type array list items equals new array list, and we'll add some items. Items dot add 1. Let's add another 4. So 2, 3, 4, 5. So that's actually adding an integer to the array list, and it's using auto boxing automatically, which we've done before in the course. It's converting the primitive type that we've typed in there into an integer. And what we're going to do then is call a method called print doubled. We're going to pass the parameter, which is our array list items, and that function we're going to write now, and its purpose is just to double the contents. So I'm going to type private static void print doubled, and it's going to be an array list n, and we'll put for object I n, and we're going to print integer. We're casting it as an integer I times 2. So just before we discuss that, we'll actually run it to make sure that it actually works. And you can see we've got the numbers 1, 2, 3, 4, 5, and we're actually doubling them, multiplying the current value by 2, so getting 2, 4, 6, 8, 10. So that's actually worked. So we get the expected output. But note, however, we actually used object here because we didn't actually specify what the object was above, and we also had to cast it as an integer. So if I actually got rid of the cast here, we'd actually get an error, And the error was that it cannot be applied to objects. So we have to sort of tell Java what type of object is actually in that array list. So I'll put that back so that the code doesn't break. But technically, the array list, as we've created it, can actually contain anything, any type of object, not just an integer as we've actually done here. So that's actually more than a minor inconvenience, because it also completely breaks the compiler's type checking. And just to see the impact of how this will affect us, if I try and add something here, like items.add, and add my name there. Now that's quite valid, and there's no indication that we've actually got a problem with our code. There's no red indications, red underlining our code. As far as Java is concerned, this is valid, and it actually is valid. But the problem is when we run it, we actually get an exception. So what's actually happening is with the object, which was a string, Tim in this case, trying to be converted to an integer, and it cannot be actually converted. You can see that java.lang.string cannot be cast to java.lang.integer. So in other words, we actually got an error because I tried to add a different type of data to the array list. The real problem wasn't so much that it crashed, although that's bad enough, but the real problem is that it's not actually showing up until runtime. So in other words, the program compiles fine. I can come up here and build and rebuild the project. And as far as Java is concerned, there are literally no problems. We've got a couple of warnings over here, potential warnings. Uncheck call to add is member of raw type array list, which is IntelliJ's way of sort of saying that maybe you should be doing this a different way. But the point is we don't actually get any errors as such. So if you can actually see these errors in more detail, we can come up to the view menu, click Tools window, and actually select messages. So if we click on that, and we could do Command 0, and you can probably see what the equivalent keystroke is on your operating system. So click on that. You can see it's Alt 0 for Windows Linux, and we can actually see those warnings in more detail. We can actually see that main.java uses unchecked or unsafe operations, and that's Java's way of actually saying that there's actually a problem with our code. And again, just a confirmation that if we actually highlight this over here, IntelliJ is also sort of saying, okay, hang on, what are you doing here? So basically the Java compiler, and obviously IntelliJ by default, knows how to provide these warnings because they're actually looking at your code, and they know that ArrayList is a generic type, but we're using it without specifying a type parameter. In other words, using it without generics. So in other words, what we haven't done is sort of said with our ArrayList what type of objects we're going to be storing in the ArrayList. So the ArrayList as we've used it here is a raw type. Now prior to Java 1.5, this was the only way to code. There was no generics. And when Java 1.5 came out, they actually introduced the generics, which we're about to talk about. And they actually left this old way of doing things in purely for backwards compatibility with code that's written for previous versions. So in other words, if they didn't do that, that old code would no longer run anymore. So the old code continues to run, but when you're writing new code, you should almost never use these raw types anymore. And you can see why, because obviously in this instance, we're able to crash it quite easily by making a simple little change there. And you might look at that and think, well, hang on, I know that there's integers and I'm never going to actually add a string there. But thinking ahead, down the track when your programs start getting a lot more complex, it can be a lot harder to track these types of bugs. This one's quite easy because it's only a few lines of code. It's certainly not recommended to use these raw types, and because type safety is so easy to implement these days in the current versions of Java, I highly recommend you actually do that. So when we actually provide a type parameter to a generic type, this is called a parameterized type. So we actually specify the type using angle brackets, and I know you've seen this before in earlier videos. So what we're going to do now is we're going to specify an integer type when we declare the array list on line 8, and also in the parameter on print double on line 20. So we come up here to line 8, we're going to actually change this. We put our angle brackets in, integer. So we're actually saying now this is the type that we're actually going to be using in this array list. We're also going to come down here to line 20, to line 19 I should say, and put array list integer, like so. So we're now specifying this is the type of data that we're actually going to be saving in our array list. And you can see what's happened straight away, that there's still a couple of errors. And you can see this one here is actually an error. It's actually telling us now that you're trying to add a string to what we've defined as an array list of integers, and it's actually an error. It's not a warning anymore, it's actually an error. So it's actually not allowing us to do that. But the first warning, it's still saying it's an unchecked assignment. We're actually still trying to use Java. It's actually saying now java.lang.integer, but it's still, as far as it's concerned, an unchecked assignment. And if I press my control function F1, and you can see it's just giving us an example of that. So we can actually fix that, try and fix that by putting another assignment here. We can actually type integer as well there. And that actually does get rid of that warning. So So it does actually pay to look at these warnings that actually come up, and where appropriate to actually remove the code that is actually causing the warning. So you see in this case now, by adding an integer twice, we've actually removed the warnings, and I can actually now get rid of this as well, because that's no longer relevant. And we've now got a tick in the top right hand corner, and that basically says as far as IntelliJ is concerned, there's no longer any errors in our code, and our code is good to go. And again, if I get rid of that get rid of that parameterized type, we actually do get some warnings again. We get a few warnings, one here and also one here as well. So do actually pay heed to those errors, the warnings, because they do actually make sense to check them to make sure your code's adhering to the standards and you're not actually basically writing bad Java code. So adding a type here is actually unnecessary, because Java's got enough information in the declaration to the left-hand side to actually include that. So it's really just to see whether you're happy with these warnings or not. You could quite happily, as I showed you, delete that, and that is still valid and the code will still work. You've just got some warnings. So generally speaking, I would recommend just to do whatever it takes to get rid of the warnings, and you know that you're actually doing things the right way as far as the Java's concerned. And just also a note here, if you're actually doing this is another way of doing it. You can actually just specify the angle brackets without a type. And we've actually got an error message, and that's probably because I haven't set my appropriate language level up. So I'm just going to go into my settings, File, Project Structure, and I've got this set to 6 instead of 8. So I'm going to set that to 8. You notice Diamonds is set for version 7, but I'm going to set it to version 8 because that's what it should be for each project anyway. If I click OK to that error should actually go away. And so what that's saying there now, that's probably the best way of actually writing the code, because what that is saying is that the first declaration here on the left-hand side is all that it needs, and we don't actually have to type another one. And I think we'll actually get a warning now if we actually type this in here, because we actually set to 1.8. You can see we actually got a warning now. Explicit type argument can be replaced with the diamond, and that's what this is. The two, a less than and a greater than sign together, is referred to as a diamond. So that using the version 1.8, and again I did that with File, Project Structure. It's making sure project language level was set to 1.8. Because I've got that set to 1.8, we've actually got a tick across the board. So that's actually the correct way to actually use it to make sure you haven't got any warnings. But if you were using an older level of source code, as you saw I had 1.6 in use, then you will actually have to specify the actual parameter there. And again, using that without a parameter in the middle is called a diamond. So now we haven't got any errors and there's no warnings left. And I've actually removed this because, of course, before, without removing that, we've actually got one error. And of course, the error again was trying to add a string to an integer object, to an array list of integers. So I'm going to comment that out to get rid of that error. So we've now got no warnings and no errors. We've got the green tick in the top right hand corner, and that's exactly what we wanted. So by telling ArrayList what type of objects we wanted it to hold, the program now fails to compile when we try to add the value item Tim. So I have to comment that out in order for the code to even be able to work. Now incidentally, coming down here looking at the loop, we can actually get rid of this cast now. We don't need that in there anymore. And we can change this. We can either set that to be an integer, or we can actually even go back and set that to an int. And Java is actually handling that for us automatically. Obviously we don't need the object now because we know what type of data it actually is, and Java is smart enough to figure out that, okay, you're using an array list of integers here, therefore I know how to convert it back to an int, and it's doing that automatically with the auto boxing and unboxing that we've talked about in previous videos. And if we actually run this code, we should find that it actually works. And you can see we now get the same result. So that's the introduction to generics. In the next video, what I'm going to do is take it to the next level, and we're going to actually look at creating our own generic classes. So I'll see you in that video. So this is part 2 of generics for Java. And just before we actually start getting onto the code, I just want to go through a couple of brief points that the reason we're actually using generics. So it's commonly understood in programming terms that the earlier bug is spotted in the code, the easier and ultimately cheaper it is to fix. And that's because there's less resources and less manpower invested to actually fix that error. So if a bug appears in production code, production here means that code that has been released to the Google Store, or it's commercially available, or it's not test code anymore. It has to be fixed. There's no doubts about it that for most bugs, some minor bugs that perhaps you wouldn't need to fix, but ultimately, if it's in production mode, it must be fixed. And so what it's fixing it, the code itself must be then fully tested to ensure that the actual fix you made didn't in fact introduce another bug. And then of course, finally, the updated code containing the fix or fixes has to actually be redeployed and uploaded to the Google Store or whichever Android app store you're actually using. And so any system, so that's any other apps that rely on the program, they too have to be tested to ensure that the fix hasn't broken interoperability between the two systems. Now, if the bug itself is spotted in testing, the effort's actually reduced slightly, but there's still a requirement for any tests that previously passed to be performed again. And of course, if the bug is spotted at compile time, no one else actually notices except you, the programmer, and the fix has had very low impact on everyone else. So that's the reason why you want to get these errors fixed early in your code. You don't want to find all these surprises, bugs later in the process, because particularly with larger applications, and when you're involving other resources, other people, it starts costing a lot of money, if nothing else, in programmers' salaries and time to actually fix those errors. So basically what I'm getting at here is that it follows that anything we can do to pick up these bugs at compile time, when we're actually writing our code the first time, is well worth the effort to get right. So in the previous video, I showed you how generic types can be used and how they're actually very useful to ensure that we don't produce a program that compiles fine but actually gives us errors at runtime. And I used the example there of actually adding a string to what was an array list that we assumed only contained integers. So let's actually have a look at taking that to the next step, and that's actually creating our own generic classes. Now, what I'm going to use for this example is the concept of adding players to various types of sporting teams. So to begin, we need to actually create some basic classes. So let's start off creating the basic abstract class. We come down here as we've always done and create the new class. So I'm going to do a new class. It's going to be an abstract class called player. So I'm going to make that an abstract class player, and we're going to have a string which will be the player name. We're going to add a constructor which will be name, so we can actually create the object, and just a getter as well for the actual player name as well. Very basic class for our player. So what we're going to do now is we're going to create three types. We're going to create a baseball player for baseball, a football player as in Australian rules football, and a soccer player as in soccer, which is what in Australia we call football, if that makes sense. Football for UK people. So I know that sounds a bit confusing, but that's what we call them over here in Australia. So I'm going to create those classes. First one's going to be baseball. Baseball player, I'm going to call it. And the baseball player is going to extends from player. So we need to create a constructor to pass that through, so the actual name is stored because that field is actually in the player class. So there's our baseball player. Let's create the football player. So football player. That's also going to extends from player. And we also need to create the constructor for that, so it's happy with that as well. And lastly, let's create the soccer player class. So soccer player. And we need to extends from player. Then we also need to create the constructor like so. So that's our three classes. There's nothing generic about those at this stage. But what we're going to do now is create a team class, and in that team class, add the ability to actually add players. So let's go ahead and do that. Create a new Java class. We're going to call it team. Now we're not extending from anything else because this is a base class. So we're going to have a name, and then this is the name of the team as opposed to the name of the player. So private string name. And we're going to keep this simple. We're going to just track the played, number of games played, number won, number tied, and number lost. So I'm going to put int played equals 0, int won equals 0, int lost equals 0, and int tied equals 0. Now obviously in a real application you'd have to deal with fixtures and those sorts of things. We're going to keep it pretty basic as they're just with a basic number of fields. So we're going to create an array list that's using generics for our player object. So we're going to type private array list, and it's going to be of type player. Remember, player is our abstract class that all the other three classes extend from. And we're going to call that members. So this is members of the team equals new array list. And I'm going to remove that by default. And we're probably getting an error about the level. So I need to make sure I've set the correct level up. So you may not get that error, but if you do, go to project structure and make sure that the project language level is set to 1.8. So I'm going to click on OK. And you can see that error then disappeared when I did that. So we need a constructor now. Constructor is going to just have the name, team name, passed to it and saved. And we also want a getter for the team name as well. So we'll just use just that one. the getter for the name. Now we come to the part where we're actually going to add the player. So we're going to have an option to allow us to do that. So I'm going to type public boolean. And boolean will be whether we successfully added them or not. Add player. Player. So player is the abstract class definition, remember, that we can pass to this. And we can put if members contains player. And we can put message player dot get name plus is already on the team, so we're not going to allow a duplicate or duplicates. And then we're going to return false in that case. Otherwise, we're going to do add it, so members dot add player, and we're going to put the player name again, player dot get name plus picked for team plus this dot name. This dot name is the actual team name, and we're going to return true in that case because we successfully added it. You can see that's now a method, add player, and we're accepting the parameter of player, which is actually going to enable us with one call to actually pass a baseball player, football player, or a soccer player, and we're able to do that because we're using an abstract class, and obviously we're using a generics here for the array list definition of type player. So continuing on, we also need a getter, and the getter is going to return the number of players on the team. So I'm going to put public int num players, and that's just going to return the size of the array list. So this dot members dot size, like so. Okay, so next we're going to actually create a method that actually gives us a result, what actually happened with the team, whether we won or lost. So I'm going to put public void match result, pass team opponent, int our score, int their score. Instead of actually having to pass whether we won or lost, we'll get the method within this team class to actually determine that. So we can put if our score is greater than their score, 1++, because we obviously won the game, else if our score is equal to their score, tied ++, else we obviously lost, because that's the only other potential option. And then we increase the number of games played, and then interestingly enough we put if opponent is not equal to null, opponent dot match result null, their score, our score. So we're doing it this way now, so we can actually also update the opponent score. And when we basically call this opponent match result again, we're passing null this time, so that this doesn't get executed again. So this way we're actually saving our results for our team, but we're also saving the results in the opponent's team as well, saving the results in their sort of object, their separate object. So that's the match results. And finally, we want a ranking. So we'll just come up with some sort of ranking system that's pretty simple. So let's do ranking, public int ranking, return. Let's just do our ranking to be number of games won multiplied by 2 plus tied. Now that's obviously just one way of doing it. There's thousands of different ways of rankings, and you could actually implement this dependent on the actual class itself. But we're just keeping it simple for now. So now that we've actually got the base code in place, we can actually start creating various types of teams and adding players. So let's go to the main method and start that. So we could start by putting football player Joe equals new football player Joe, and say baseball player Pat equals new baseball player Pat, and soccer player Beckham equals new soccer player Beckham, even though I think he's retired. Okay, in team, so let's try typing team Adelaide Crows. The team I follow equals new team Adelaide Crows, and we can put Adelaide Crows dot add player Joe, Adelaide Crows dot add player Pat, and Adelaide Crows dot add player Beckham. Now why Beckham would be playing for AFO I don't know, but anyway, that's an aside. And we can print that out now just to make sure that the basic thing is working. Adelaide Crows dot num players. We should get the right result if we do that. So what I'm actually going to do is I'm going to stop the video here. In the next video, we'll actually tackle this problem. This is the problem of actually making sure that a particular team will only accept a player of the correct type. So in this case, if we actually specify a team, then we only allow the correct people who are part of that team, in other words, a football player in this scenario for the Adelaide Crows, to be accepted as part of that team. So we'll do that in the next video. Now continuing on from our generic class from the last video, so we actually started this code, we didn't actually run it, so I'll just run it now. Just to confirm that we've actually got the right number of players, we should get the answer 3 because we've actually added 3 there. And you can see we've got the answer 3. But it does actually bring up an interesting issue. There's an obvious problem which I started talking about, and that's that the first time, in this case, our baseball player, and that's Pat, the first time he actually runs onto the field and tries to hit the football with his bat, he's probably going to be red carded and sent off the field. So in other words, our team class is actually allowing us to add any kind of player to the team, and there's no actual check to see whether they're the correct type of player. Because obviously in the case of the Adelaide Crows, we've decided that that's a football team, so there should be some way of ensuring that only players who are football players can be added to that team. And likewise for a baseball player, only baseball players should be able to be added to a team with that baseball. And likewise for soccer. So we need some sort of mechanism to actually make sure that happens so that only the right types of players can be added to teams. Now there is a few solutions to this. One solution would be to create 3 different team classes. So in other words, a football team, a baseball team and a soccer team, like 3 different classes, and ensure that they only accept the correct player type. But in that case, the code is going to be largely identical. So we're going to be duplicating code, and it's usually never an efficient way to code to actually duplicate code. So I don't recommend that. And of course, that's not to say we couldn't extend the team class to create 3 different team types within there. So sort of have sort of private classes for each of those team types. But then if we did that, we need to implement functionality that's unique to each team type in that code as well. So the common code to do things like add a player, play a game, record a score, etc. would be in the base team class. But fortunately, Java's got generics, which we're talking about obviously in this section, and it enables us to really specify a type when we're creating our class. And this is exactly what we want here. So what we want to do is modify team to be a generic class. So let's go ahead and actually do that, and we'll see that working. So we're going to go to our team class. We're going to come up here, we're going to start making some changes to it. So at the moment, obviously it's accepting a generic player there. This is in the array list, also in the add player method. So let's actually make some changes. First, we're going to modify the class declaration to include a type parameter. So to do that, we use the diamond as we did before, but we put a T in the middle. And that's to indicate there's going to be a type there. We also come down here to array list and we do a similar thing. So instead of player, we delete that and make that T as well. And you can see it comes up, IntelliJ comes up and says it's a type parameter of com.timbercharco.team, which is correct. And the third area we want to change is our add player. So instead of allowing a player class, we're basically adding the type parameter again for add player. So again, we're changing the type so we can make this more generic and it's going to work for any type of player. And how this basically works is when we actually instantiate a class, the T will be replaced automatically by Java with the actual class we're using, with the real type, in other words, when we're actually instantiating the class. And that's why we've actually changed the add player and the array list as well. So all 3 are changed so that we can actually, we're able to actually do that sort of type checking. So notice that we're actually getting an error in add player. And the reason is that we've specified that its type is T, which is a parameterized type, as we've said before. And because this type's not known until we actually instantiate a class, in other words, at runtime, there's actually no way for Java to know that an object of type T in this case really does have a getName method. So the only sensible thing the compiler can do in this situation is to flag an error, which is actually showing on the screen. Now we can get around that for the moment. So what we're going to do is we're going to cast player, the player parameterized type, to make that a player type before attempting to invoke its getName method. So we're not going to change the parameter here. We're going to actually change it when we're actually referencing it. So we're just going to do this. We're going to cast that to player, because we know ultimately it is going to be a player object, like so. We need to actually put 2 brackets there for that to work. Player, and then put another bracket there, and that should fix that up. And likewise for this one, and I need to put the cast in as well. Player, and 1 more bracket should fix it. and that fixes it as well. Now, it is a solution, but it's a pretty ugly cast in the sense that we're invoking a method on the cast object, and we need parentheses around the cast before we can use getName. But do not fear, it's only temporary. Very soon we can see I'll actually show you how we can remove the need to do this, but this will get us out of trouble for now while we're working through our code. So getting back to our main method now, to our main class and then to our main method, you can see that there's actually no errors at the moment, but if we actually have a look at some of these warnings, we're getting an unchecked call to add player T as a member of raw type com.timbercharcoal.team. So I talked about raw types in the previous video and what they were and how to get around them, and you also saw why we shouldn't be using them. So with that said, the program is still going to run, but poor old Pat will still be given a red card. So in other words, we're not validating the type of player against a particular type of team. But we can actually fix that quite easily by specifying what type of team our football team variable should be. So team now has the ability to accept a type argument, as we've just changed in the team class. So all we have to do is provide it with one. So we're going to go back to our declaration for the Adelaide Crows. We're going to change that. So we're going to add the type argument to that. That's going to be football player. So once we've done that, we've still actually got an error here, unchecked assignment, because what we haven't done is we haven't added the diamond. So we need to add the diamond after the team. Now they're actually using it to the left in the declaration section. So I'm going to put the diamond in there now, and that now removes that error. So we've got a proper assignment of our generic class now. So we've actually indicated that we're going to be using the football player, and as a consequence of doing that, you can see now Joe was added. And the reason that Joe is valid and it's not being, the compiler is not telling us that there's a problem, is that he was assigned as a football player. But in here, the other two, Pat and Beckham, because they were baseball players and soccer players, they don't meet the criteria for this type now, and they're actually getting flagged as an error. So actually an error, not just a warning. It's telling us that we physically can't add those to this class anymore based on the definition. So in other words, this particular instance of team is now only going to accept football players, and the attempts to add Pat and Beckham are now showing errors. So let's give good old Pat a chance to shine. So what we're going to do is we're going to comment out these first, get rid of those, and let's actually add another class. We're going to call it team baseball player. We'll call it baseball team. I'll get rid of player team. We'll call it baseball team equals new team. Again, we need to add the diamonds if we're actually using that on the left-hand side, which we are for our type assignment. And it's type of team like Chicago Cubs, which is a baseball team in America, for those who don't know. And we can now successfully do baseball team.add player Pat. And that'll work quite nicely because, again, Pat is, he's been defined up here as a baseball player. He's a type baseball player, and we've defined that as the team being of type baseball player, so consequently he's able to be added without any problems. But with that said, there's still some problems here. And at the moment, the type parameter T in our team class can be supplied any type except primitive types such as int. So in other words, any object. So we're not doing any validation of that. So we could actually do something like, for example, team string broken team equals new team, and this won't work, which it won't work. And if we did something like broken team dot add player no one. Now string's invalid type, and as you can see there's no compilation errors. We're just getting a warning up here because Beckham's actually not in use at the moment. But the problem with this is going to be the cast when we actually go to run this. So if we actually run this code, we actually get an exception. And the exception has got to do with the fact that java.lang.string cannot be cast to com.timbercharcoal.player. And of course, if you remember, going back to our team class, we actually defined that in here. We actually added this ugly cast to get the .getName to work. So what we really need is some sort of way to validate the type of class actually when we're using it for this team. So in other words, we need the ability to restrict the type that can be provided for this T argument from the team class. Now the good thing about that is that Java also provides a mechanism for restricting the types that can be used as type arguments, and they actually call these bounded type parameters. By using those, you can provide them with an upper bound. So I'm going to explain these terms in more detail once we've seen them in action, but let's actually change the declaration of our team class first, and then we'll go through it. So at the moment we've got team, and then we've got the type in diamond, as you can see there, but we can actually change this to put extends player, noting that I'm actually typing it within the diamond. So T extends player now. And if we go back now to our main class, because we've done that, we're now actually getting an error here. And notice it's not a warning, it's actually an error to say java.lang.string is not within its bound. It should extend com.timbercharcoal.player. So that's our way of actually restricting the type of class that we can actually use for team. And just opening that up again. So basically what we've said is that we've told Java that the type parameter we'll accept for this class when using generics is going to be any type that extends from player or a subclass of player. So in other words, by typing it like this, with this extends player, player is said to be the upper bound of T. And of course, T, as I mentioned earlier, is a bounded type parameter. So if we attempt to use any class, in other words, that is not derived from player, we're going to get that error, which we're seeing here in main now. And as a consequence of that, because we've actually done that, the good news is we can go back to our code again, go back to team, and we can actually get rid of this cast. So we can actually remove that and go back to what it was before, which is just player.getName. So I'm going to do that, like so. And for the next one. And again, the reason we're able to do that is because of the bounded type parameter we've put up here. We've said that all valid upper bounds of T have to extend from player. So as a consequence, Java then knows that, okay, so in other words, Java now knows that the type T in add player extends from player. So it's going to have all its methods, including get name of player. So basically there's no longer an error and there's no need for you to actually add that cast anymore. So going back to our main method again. So let's actually change now this team here. We're at the moment the broken team to be a soccer team. So we can type soccer player, broken team equals new team. This won't work. And notice how it still is going, it's come up okay. We've defined a new team, and even though we haven't changed the name. But the important part here is this next declaration is broken team.add player, and we're passing the string. Java's also showing an error for that when we try to pass the string to the add player method. And again, this is exactly what we want because we've defined the add player method and the class to require us to use the player class or a subclass of player, and obviously string isn't that, and that's why we're actually seeing that error. So if we actually replace that string with our soccer player Beckham, we actually see that the error goes away, and we've got a tick in the top right hand corner and no warnings either. So before going on to the challenge in the next video, I just want to discuss a few other points. Firstly, an argument passed for a type parameter can either be a class or an interface, so you can actually use interfaces as well. So although we use the player class in this example, this is going back to team, we've used the player class there. You could have declared team to accept an interface instead, and that's certainly valid to do that in Java. And the other thing to note is that interfaces themselves can also specify type parameters. So in other words, you can create instances of a class that implement an interface, and then you can ensure that the interface methods you implement act on a specific type of object or objects. And we've seen that in previous examples when we used the list string, for example. List was an interface that takes a generic type parameter, and the usage is the same as it is for a class. Now, we also used a single bound when we specify the team type parameter, so restricting teams to being created for objects that will inherit from the player class or a subclass of player only. Now, Java does allow multiple bounds. Although, so you can have class T extends player and coach and manager, for example, to allow multiple instances of player, coach, or manager to be added to the team. But with that in mind, the normal inheritance implements rule still applies. So in other words, you can only extend from a single class, but multiple interfaces. So basically, if you want to do this with more than one class, you'll need to use interfaces for those other types as well. And the other thing to keep in mind is if you're specifying multiple bounds, then the class must be listed first. Otherwise, Java is going to raise an error when you try to actually compile it. So in other words, class first and then interfaces. And the way you do that, just briefly, we're not going to actually add the code there now, but you put something like and coach and manager for argument's sake. That would be the syntax you would actually use, but obviously you could only have one class, so these two here in this scenario would actually have to be interfaces. So I just want to confirm that is actually the syntax if you're wanting to use multiple bounds. So you put the player, in this case the class first, and then you'd actually put the interfaces after that if you wanted to do that. Obviously we're not doing that in this example, so I'm going to actually remove those. And obviously in the case of multiple types, you'd have to then include code to check what type of object you're dealing with before invoking its methods, because it wouldn't be just in this case, just the one class which was player, and there'd be a little bit more code to actually add to do that. And finally, soccer player and also football player are both subclasses of player, as we know. So obviously there is a relationship between them. So either can be used when calling a method that expects a player, for example. But the important thing here is to remember is that there's no relationship between something like this. So if we look at list manager, list soccer player, and list football player, And I'll just add those even though we're not going to do anything more with them. So there's basically no relationship in this case between those two. And the reason is because neither of them are a subtype of list player. They do have a common parent, but the common parent in this case is list. So I hope that makes sense. The bottom line is for a code, probably a lot of the time with generics, you'll probably be doing something like this where you'll only be extending or using one class and maybe an interface. But if you do need to use multiple bounds, you'll need to specify the ampersand and then obviously also the interfaces as well. And just one more thing we need to look at before we actually get to the challenge. So the team class has got fields to track how many games were won, tied or lost, but we haven't actually made use of them yet. So we did include a match result method. So let's make some calls on it now in main just to record the game results before we discuss the method more. So I'm just going to actually copy and paste some code here. I'm going to go back to main. I'm going to paste this paste this code in, I should say, like so. And I'm going to change that to Adelaide Crows. Then I'm also going to do Adelaide Crows dot match result, and I'm going to type Fremantle 2-1 and Adelaide Crows match result dot match result baseball team 1-1. So if we actually run that, basically it does seem to be doing something, but we're not actually getting a lot of feedback from it. Now the match result method, if we go back to that and have a look, you can see that it does actually take a team object called opponent and two ints, which is our score and their score. And if our score is greater than their score, then we've won. So we've won is incremented, as you can see in this code here. Similarly, for tied and lost, we actually go through that process. If the scores are equal, tied, otherwise we indicate that it's lost. So that takes care of the team that match results called from, but the opponent also needs its fields updating, and that's why we've actually got this additional call here. So we do that by invoking the opponent's match result method as well. And this time, obviously, we're passing null for the opponent argument, and only we're invoking the opponent's match result method if opponent is not null. Otherwise, we'd end up calling match result on the first team again, on and on and on again. We get into an infinite loop. So let's actually just print a little message here. So we'll put something like this, just to so we've got a bit more feedback. We'll add a variable called the message, string message, and let's set that up to be message equals beat. And for tied, we're going to add message equals, drew with, and lost, message equals lost to, like so. And if opponent's not equal to null, we're actually going to print the result there. So we're going to put system out this.getName plus message plus opponent.getName. Just so we've got that bit of output on the screen. And notice here that we're also only printing the message for the initial team. So we're doing that test for it's not equal to null. This makes sense, but because we're printing the name of the opponent, we get an error if we attempt to display the message outside of the check for opponent being null. So let's actually run this. And you can see we're getting some output now. And Drew, we've got a problem there with the way that I've typed in Drew. I need to put a space there. So I'll go back to there and run it again. And you can see it seems to be getting better feedback now. Hawthorn bet Fremantle, Hawthorn lost to Adelaide Crows, Adelaide Crows bet Fremantle, Adelaide Crows drew with Chicago Cubs. Now can you spot a problem with match result yet? So the Adelaide Crows drew against the Chicago Cubs. What's going on there? But the Adelaide Crows play football, and of course Cubs play baseball, so that's rather an odd match result. So what we really want to do here is make sure that only the correct team type can be passed to the match result method as well, inside of any object of type team. So you can probably figure out how to do that now. So if we go back to our code again, and I'll just bring up the project window again and close down the run window, go back to team again. So we need to do something in here. You can probably figure out what we need to do to make sure that happens. We need to make use of its generic type, essentially, which we haven't been doing. So we're going to change that to use the generic type, which we've defined for this class. So now if we do that and go back to our main method, I should say, we're now correctly getting this error, and it's saying that Adelaide Crows, well, we're supposed to only be using football players because that's how we've defined the Adelaide Crows up here as to be a team football player. So Java is quite correctly indicating that's now a compile time error. So this video has gone on for long enough. So what I'm going to do is stop the video here. In the next video, we'll continue on and we'll just finish off a few other things to do with the way we've set this up, and then we'll move on to the challenge. So I'll see you in that next video. So just a few little things now to finish off in our generics code, and then we're going to actually move on to the challenge. So in the last video, I just showed you how to actually change the team match result method like here. So we could actually use that type to actually confirm that only players of the appropriate type could, or only teams I should say of the appropriate type could call the method. And so consequently, in match result, when we're calling that from the Adelaide Crows, we can't actually pass a baseball team to it because we've defined Adelaide Crows to actually be a team of type football player. So therefore that baseball team isn't going to work. So I'm going to comment that out now. Now, the team class includes a very simple ranking. I think I talked very briefly about that. And the ranking was just a very simple formula to calculate how this team is ranking in the league. And it's the number of games won multiplied by 2 plus the number of games tied. So pretty simple. So in a real, obviously, league, the ranking would also consider the number of games played and things like the goal difference and perhaps other things as well. And obviously you're free to play with more complexity to the method if you're interested in doing these things for yourself and having a bit of a play around. But we're going to leave that as fairly simple with this exercise or for this example as we move forward. So let's actually go ahead now and actually print these rankings out. And that's actually quite simple to do. So we can just come in here and do some print out or print out some items. We can say rankings. Then we could do Adelaide Crows .get name plus colon then plus Adelaide Crows .ranking. And likewise we could do the same for Melbourne. Melbourne .get name plus colon space plus Melbourne .get ranking. Ranking. The next for Fremantle. Fremantle, these are all Australian rules football teams. Get name plus colon space plus Fremantle .ranking. And lastly, Hawthorn, who incidentally won the 2015 Premiership in Australia, plus space like so, and it'll be Hawthorn .ranking. So we can actually now run that. And we can actually see the Adelaide Crows have got 4 points. And if we have a look, we can sort of see why. Melbourne and Fremantle have got 0 points because we haven't actually defined them as having any results, essentially. It's only Fremantle and Adelaide Crows have actually got some results in there. And Hawthorn have got 2 points. And you can see that's obviously from the various match results that we've actually entered. So that's all very well, but one thing we can't do is compare teams to see which would be the highest in the league table. And let's make a change to that. Let's actually make a change to our team class to implement something that's very useful, an interface called comparable. So I'm going to close down the run window and go back to the team class. We need to actually change the definition at the top. We've obviously got extending player. We need to then implements. We can implement comparable, and we need to actually use the diamond again, so team T again, because obviously we want to make sure that we're still using the same generics like that. And obviously we're getting an error now because it's saying we must implement the abstract method compare to in order to actually fulfill this interface. And you can see there that there's literally only one thing to change, one method we need to do to actually fulfill the interface, and that's the compare to function. Now, because we only want to compare our teams to other teams, that's why we're actually using the team and the type. So it doesn't make sense to compare a football team to a baseball team. So that's why we're actually adding team and then the actual type in another set of diamonds. So the implements part looks complicated, but essentially what we're doing is we've created the ability to have generic types such as team football player. So all we're actually doing here is specifying a generic type as a parameter to the generic interface comparable. So team is the type in this case, and team football player or team T's you've got here is also a type. So comparable T in this case can accept either. So the compare to method that we're about to write, which is defined by the comparable interface that we're implementing up here, takes an object and returns a negative number if this is less than the object, 0 if they're equal, and a positive if this is greater than the object. So here what I'm talking about is less than means that we should sort earlier than. And as we want teams with higher rankings to sort higher up the list, we need to make our compare to return less if the ranking is greater than the opponent's. I hope that actually makes sense. Now, we've actually used the compare to method when we implemented our own linked list in a previous challenge. And many of the Java classes actually implement this interface, including the string and integer classes. And that's how these objects can be sorted as a result of doing that. But what we're doing is we're going to be writing our own code because, of course, we used the string compare to in the previous challenge. We're using the comparable interface, and we're going to be implementing the compare to method, which takes the parameter of team T, the type, type parameter to compare. So, and again, we're doing that so we don't try and compare football and baseball teams for argument's sake. So if we had just changed that so that was just literally team like this, compared to it could only take team as its parameter, then when we write the method compared to, it will only also be able to take team as its parameter, and we wouldn't have that ability to ensure that only the types of teams in this case that are appropriate can be passed to that method. So I'm going to leave that back in. So let's go ahead and actually write this compare to interface. I'm going to come down here under ranking, and I'm going to implement. Let's implement the compare to method. And you can see how it's automatically looked at their definition and has added a similar definition. So I'm going to change the default of 0 to team, because that's essentially what it is in this case. It's the team. And what we now need to do is go through and do this test like I've said. So the first test would be if this dot ranking, so this is the current object we're comparing, if it's greater than what's been passed to us, the team dot ranking. Remember, the higher the score, the better. Then we're going to return -1. So in other words, the current team, the one that we're actually in, this class in other words, or this instantiation of the class, if the team ranking for that is higher than the team that's been passed to this method, then it means that this is actually higher in essence, and we're going to return -1. That's the first one. Otherwise, we're going to put else if this dot ranking, if it's less than team dot ranking. So it's the other way around, we're going to return 1, because the opposite is true. The current object hasn't got more points, essentially, it's got less points, so we're going to return 1. And otherwise, we're going to return 0, because it obviously means that the rankings are actually the same. So that's all we need to do to implement that. And then we can go back to our main Java code, and we can actually print that out. So we could do something like Adelaide Crows dot compare to, and let's just say Melbourne. And Melbourne, I believe, had 0 points. And then let's do the same for Hawthorn. So Adelaide Crows compared to Hawthorn. Let's just try those two and run them. So you can see in this case, Adelaide Crows has got 4 points. And comparing to Melbourne, which has got 0 points, it returns -1. Because we've got a higher ranking in this case than Melbourne, and likewise compared to Hawthorn, we've also got a higher ranking. But if we actually wanted to do a test, let's actually compare Hawthorn to the Adelaide Crows. So we'll do it the other way around, just to confirm it's still working. We'll put and Hawthorn compared to Adelaide Crows. We should get the opposite because we're now comparing Hawthorn to the Adelaide Crows from the other point of view. But also let's do one that's the same. And we'll do Melbourne dot compare to Fremantle, with which both should return 0, so we should actually get 0 because they're both the same score. So we run those. So you can see the third example now we've got Hawthorn compared to Adelaide. Adelaide's got more points, Hawthorn had less, so we returned 1 there. And in the last example, Melbourne.compare to Fremantle, they both actually had 0 points, so obviously the compare to returned 0. So that's actually working, which is good. Now, the reason we've implemented the comparable interface, other than to show you how to use it, because I think it's actually very useful, but it's also it's going to be to help you with the challenge to come in the next video. So if you've got a list of objects that implement comparable, now such as ArrayList team, for example, what you can do is you can quickly sort the list by using the static sort method of the collections class. I'm going to talk more about that and give you a little bit of a hint in the next video when we're actually going to go through the challenge. But essentially, if you've got an array list of teams, you can use this code, something like this. Some pseudocode would be, if you had something like an array list of teams, like so, you could do collections.sort teams. And that would be sorted, and the whole point about this is it'll actually be sorted using the compare to function that we actually wrote for the actual team itself. So in other words, this method would be actually automatically utilized by the actual code when we're actually doing the dot sort. And we're just getting an error there because we haven't actually initialized that. This is just purely to give you a bit of an overview of what it can do. Now that's obviously one way to do the sort, but you can obviously go back and refer to the sort method that we actually wrote for the arrays challenge as well. But you can see this is quite simple, actually using the built-in Java collections class. And we've got an entire section of that about collections in upcoming videos showing you how to use that. But this is just a simple way of doing that. But anyway, I'll talk more about that in the next video. I'm going to stop this one now. There's probably no point me starting the challenge in this video. What I'll do is I'll actually start the challenge in the next video, and we'll go through what's required and then actually type out the solution. So I'll see you in the next video. So it's time now for the generics challenge, and if you haven't actually looked at the previous videos, I do suggest you make sure you do that, because you'll need to understand the concepts of generics. And what I've done is I've just added this little bit of code that I talked about right at the end of the previous video, relating to how to go about actually sorting an array list of teams that we had in that example. And you'll need to know something like that when you're actually implementing this challenge. So let me go now and actually type out the generics challenge. Okay, so here is the challenge. So you need to create a generic class to implement a league table for a sport. Now the class should allow teams to be added to the list, and it should also store a list of teams that actually belong to the league. Now your class should have a method to print out the teams in order, and the team at the top of the league should be printed first. Now only teams of the same type should be added to any particular instance of the league class, and the program should actually fail to compile if an attempt is made to add an incompatible team. And this is relating to the concepts you've learnt in the last 4 videos in this generics section. So basically, if you've watched those videos, you'll have basically everything you need to be able to go ahead and actually do this challenge. Alright, so when you're ready, pause the video and go away and see if you can actually figure out this challenge and come up with your own solution. When you're ready to come back and see what my implementation is, start the video again, and I'll actually show you how to do it. So for now, pause the video and I'll be waiting here patiently for you to get back. Okay, so how did you get on? Did you figure out the solution? Hopefully you figured it out and have come up with a good alternative. And just a reminder, I know I've said this a few times, is there is no one answer that's perfect. So if you've got basically fulfilling the criteria that I've typed in here in the challenge, and your program does that, then that's great. You don't have to have typed the same code as me. So it's important to actually know that. Let's continue and start work on it. So firstly, we actually need a class. We're going to call it League. New class, call it League. And what we're going to do with the League, we're using generics, of course. So we're going to come over here. T extends team. Now what I'll need to do, which I haven't yet, is I'll need to actually paste the team code in. I'm going to do that in a sec. And team code is obviously the code that was that we used previously. So I'm going to do public string name, private array list of the same type, league, equals new array list, like so. So I'm not sure if I've shown you how to do this before. I think I may have, but if you've got one IntelliJ project open, you can actually open up a second one. So we're going to leave this one open and do File, Open Recent. I'm going to go to the generics challenge, which was the last video prior to this one. I'll open that, and it should come up with an option here, and I'm going to select New Window. If I select this window, it's going to effectively close this current project and open another one. But I click on New Window, it's going to have both open at once. Then I can either come up here to Windows, probably the easiest way, and then choose Generics Challenge, which is the other project. So what I'm going to do is start copying some of these over. So I'm going to tab over. Now I'm going to actually use the Command tilde on a Mac, which actually switches, and you can see down there it's a new window project, Control Alt close bracket for Windows or Linux. And I can go to my generics challenge and I can actually select, say, player first. I can copy that, copy, tab back over and paste. Now, obviously, depending on the number of classes, it may or may not be appropriate for you to actually do this amount of work. You know, it'd soon get tedious doing sort of a heap like this, but if there's only got a few classes, it can be a good way of doing it. It's a couple, and we'll add a few more. Football. We might see whether we can just get by with just football, and we'll come back and do some more if we need to. We'll paste that as well. So that we've done that, we'll just actually do a build. And I've got the same error, source 1.6. I need to make sure I'm running source 1.8. And if I fix that, that should actually make that problem go away. Okay, and I'll get rid of that window down the bottom. Okay, so we've got now the basic mechanism, so we can go back and continue with our leagues. I'm going to close down these other classes. We don't need them for a while. Go back to our league. So our league has now got an array list. We've got a type there, the parameter, so that we're using the team. And we're going to make sure that that's actually enforced. And just a note here, we don't actually need to have that in there. Remember, we just put the diamond by itself to actually get rid of any error, any warnings. Okay, we need to add a constructor. The constructor is only going to be the name of the league. We're going to add a function for add. It'll be public boolean add, which will be the team, and a simple if league dot contains team return false, so we don't want to accept any duplicates. Otherwise we're going to do a league dot add to the array list for team and return true. So that is a mechanism now to allow us to actually save teams to the league. Then the other thing we want to do is actually go through and show the league table. We can do that quite simply with public void show league table. Now we use that collections dot sort league. And I'm going to accept the import. Now it's coming through automatically by IntelliJ. Now again, the reason that sort works is because within team, we've actually written our compare to. We're obviously implements a comparable, but we've actually written our compare to, and this will be used automatically by the collections framework when we're sorting. So this, you can see that this is incredibly powerful to have our own compare to method, because it makes sorting quite trivial, and this is sort of like an automatic thing that will actually take that into account now, which is fantastic. So that's now sorted in this method, and then we can go through and we can put for type, the type, and t colon league, go through each entry and do an output of t.getName plus t.ranking, like so. So that's our show league table method. And again, we defined league to be a parameterized type that's bound by the team class. So in other words, a team or any subclasses would be allowed as the type argument when we create an instance of this league. And the parameterized type is used in the declaration of the array list up here as well. And that's obviously going to hold the league's teams. And also we're using that again in the add team. And then finally, when we're in the for loop in the show league table, that method sorts the array. So as I talked about, collections.sort, and you can see that I'm actually going through now and actually printing that out in the right order. And again, we've got the parameterized type as well in use there. So to actually go back to the main now, we could actually write a bit of code there now. So we could put something like league team football player, like so. So we're defining the type of team, and we'll call that a football league equals new league, and we'll say that's the AFL, Australian Football League, AFL. And what we need to do is to go back and copy those variables for those various teams. So I'm just going to tab back over to that other class from our main method, and I'm going to add some of these. And we had so what I'll do is I'll just copy a heap of these, and then I'll actually just remove what we need to. Paste that in. So we've got the Adelaide Crows, and then we also had these other teams here, Melbourne, and we had Hawthorn and Fremantle. So we actually had, in this case now, we've actually got 4 teams. Let's actually go ahead now and actually add those. So it would be football league.add, Adelaide Crows, football league.add, Melbourne, football league.add, Hawthorn, and football league.add, Fremantle, like so. And that's actually all working perfectly as you'd expect. But also let's go back and just copy from the other project, the baseball league, which I probably shouldn't have deleted that. So let's just copy that one. And we'll come up here and put that in there as our definition. So what we need to do is copy the baseball player class as well. So I'm just going to come back here, baseball player, right click, copy, go back to our generics challenge project, right click and paste, baseball player. And obviously that now, if we go back to league, should fix that error. So if we go back to main, I should say, we've now got that. So if we actually now try and add it, so football league.add, baseball player team, we actually get a compile time error, as we should now, because obviously the baseball player cannot be applied to league, because we've actually said this particular league, we're using generics. Yes, it's a team, but this is the type football player only. So that's good, that's actually working. And now to actually print out the results, we can do football league.show league table. Now if we do that by default, we should run that. I haven't got any results in there at the moment. So everything's on 0. So what we need to do is actually, again, copy through results. We'll copy these 3 results, paste those in. Let's put them in there, some results. And if we actually run it again, We've actually got things in the right order. We've got Adelaide Crows on 4 points, Hawthorn 2, Melbourne 0 and Fremantle 0. So that's actually good. So that's the basic challenge. But what I want to do is, before I finish, I want to just talk a little bit more about, go through the warnings about using raw types, because it's really important to actually understand why we actually don't want to do that. And probably a bit of code here will actually help. Because again, the raw types are actually allowed in order to allow their legacy code, that's code prior to Java 1.5, or code written before the generics was introduced to Java, to allow that to actually work. But you can't rely on the compiler giving an error when you use those raw types. You'll actually get a warning. IntelliJ will also warn you, but the code will compile. So again, just as a confirmation, I'm going to paste a bit of code in here. And I'll change that to Adelaide. And we need a couple of players. We'll go back to Beckham and Pat. We'll copy those two, like so. And we probably should have done this at the start. Copy the soccer class as well. Copy that. Paste it over here into this package. Paste. Okay, go back to main again. So again, in this example, this code will actually run. It's an unchecked warning. So if we actually close down the run window, you can probably see this a little bit easier. IntelliJ is going to be telling you that this is an unchecked call. So we're not actually defining the types as we have up here. So the code will still actually run, but we'll get those warnings. And we notice how we can actually add literally whatever we want. We're adding Adelaide Crows baseball team and raw team to this league, and it's quite happily allowing us to do that, even though, of course, they're all parts of different types of sports, and you wouldn't normally want to do that. And this is all because we're using the raw types, not the generics. So that's should hopefully really sort of hitting home to you that you want to be using these generics whenever you can, because it makes your code cleaner, less likely to have crashes, and easier to debug, essentially. Because the errors that you're getting are going to be there at compile time, and not obviously when the code's in production and you're trying to fix these weird bugs. So again, the real issue is the line something like this, where we're actually just not specifying a type for the team. So without going into it any further, we could actually mitigate some of these problems to at least prevent the raw league declaration from compiling. We could actually go back into our league class, where it's got t extends player. We could put something like u extends player, t extends team, something along those lines. If we go back and actually have a look at main, it's now requiring 2 parameters, and we could actually put league, we could actually force it there by putting something like football player, team. That would be one way of actually solving the problem, because it's now actually coming up and saying that there's a problem with the baseball team. But it's still not an ideal solution. And for that reason, I would actually recommend you do as I've done in the challenge, and you actually come back and actually do something like we did there to actually make it far easier to actually work with. So that's it with generics. I hope you've got a lot out of this section, and we'll see you in the next section when we're continuing on our journey into Java.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
So in this section, we're going to start talking about naming conventions and lead on to packages and statics and so on. But we're going to start with naming conventions. And there's actually a good reason why you want to do this. And 2 of the biggest reasons for adopting these accepted conventions, which we're going to be going through in this video, for naming your variables, methods, and objects in Java, is that it makes your code easier for others to read. Now, others here actually includes yourself when you come to look at your code weeks or perhaps months or maybe even years after you've originally written it. Because trust me when I say that you will forget why you've done something. So if you can make your life easier and the life of other programmers by following these accepted conventions, it's just going to make things a lot easier for all concerned. So let's start off talking about packages. So the things you actually get to name in Java are packages, classes, interfaces, methods, constants, variables, as well as type parameters. And pretty well all of those you've actually seen in the course so far. But let's actually start talking about packages first. And the format of the package is to always be in lowercase. Now the package name should be unique, and you need to use your internet domain name reversed as a prefix for the package name. And you've seen me using that in the course with com.timbachaka. And Oracle actually specify a convention for package names, and there's a link to that, quite a long URL, which you can actually find out more about that. But I'm going to give you a bit of an overview of what they are anyway on the next slide. Now, some of the invalid domain name components. Firstly, if your domain name has got a dash in it, which is fairly common for domain names, you need to change that when using a package to an underscore. Now, the domain name components starting with a number should instead start with an underscore. And also importantly, domain name components that are Java keywords should have that component starting with an underscore as well. So here's some examples of converting invalid domain name components to valid ones. In the first case, switch.supplier.com, if that was your package name, you should actually make that com.supplier._switch, because of course switch is a Java keyword. Second example, oneworld.com with the numeric 1, you should actually change it to com._oneworld. And the third one, experts-exchange.com, would be com.experts_exchange. And that's an example of some package names: java.lang, java.io, org.xml.sax.helpers, and com.timberchowka, which you've seen throughout this course, .autoboxing. Okay, let's move on to class names now. Now, class names should use camel case. The class names should also be nouns because they represent things. They should start with a capital letter, and each word in the name should also start with a capital. For example, linked list, as you can see there, with a capital for the word linked and a capital also for the word list. Now, some example class names: ArrayList, linked list, string, top song, gearbox, and main, as you can see there. And again, we're capitalizing each word for the class name. Okay, interface names, very similar rules. Capitalized like class names with camel case. Consider what objects implementing the interface will become, or what they will be able to do when you're actually coming up with a name. So examples for that would be list, comparable, serializable. Method names, let's talk about that now. Now, the method names should be mixed case. They're often verbs because they reflect the function performed or the result returned. Examples would be size, get name, or add player, as you can see on the screen there. Let's talk about constants. Now, constants, so we haven't used those much in the course, but they're actually to define something which is actually a constant value. In other words, a value that's never going to change in your program. And you can see there's a couple of examples there of max_int, severity_error, and pi. And some of those are actually used within the Java framework itself. So constants should be all uppercase. You need to separate words with an underscore, as you can see below. And they should also be declared using the final keyword, which actually tells Java that you won't be changing the value. And you'll be learning more about what final and static and so forth is in this section of the course as well. Okay, variable names, also field names as well. And just to remind you, a variable name I'm using to really pretty well covers any variable that you're defining in your class, but also this applies to fields, which of course are basically variables assigned at the class level that we actually assign, using a scope and so forth at the top of the class. So in both cases, you should follow these rules, generally speaking. To be a mixed case, the actual name should be meaningful and indicative. Start with a lowercase letter, unlike classes or interfaces which are uppercase. Don't use underscores for variable names, and you can see some examples there. League, Sydney Swans. And in case you're playing along at home, Sydney Swans is actually incorrect because that's actually showing a capital S. So that should actually be a lowercase s for Sydney, but then after that, the second word is an uppercase. So again, just confirmation there that you start off in lowercase, but then the second and subsequent words, as you can see that in the case with box length down the end, should actually be in uppercase. So that's camel case essentially. Okay, moving on, type parameters. Type parameters generally are a single character and capital letters as well. And you saw that in the generic section of this course where we actually used type parameters and we used just a single letter. And there's a link there you can go to find out more about it for the guidelines given by Oracle, who look after Java. And they've got quite extended information if you want to go in there and find out more about that. And just as an example of some type parameters, you saw this in the generic section. E, as in element, which is used extensively by the Java Collections Framework, actually, which you'll be seeing when we get to that. K for a key, N for a number, T for type, V for value, and SUV, etc., second, third, and fourth types. So that just gives you a bit of a standard way to actually come up with type parameters when you're needing to use those in your code. So that's actually it. I know it's a quick overview, but I just thought it was important to give you a bit of an overview of some of the standard naming conventions used by Oracle. And there were links in the slides, as I mentioned, where you can actually find out more about that. And it's just important to try, and again, as I mentioned at the start of this video, to follow these conventions because they can ultimately help you and other developers in the future who may have to look at your code at some point down the track when you've actually forgotten why or how you did a particular thing. But just by looking at these standard conventions and making sure your code implements them, you can save yourself a lot of time. All right, thanks for watching, and I'll see you in the next video. So in the previous video, we actually discussed some conventions for naming packages, but we haven't actually looked at what a package is yet. Now, if you think back to the abstraction challenge, which is now a few videos ago, I actually suggested that you didn't call your linked list class, the one that you were creating, your own linked list class. I suggested you didn't call that linked list because that is the name of the linked list class that actually comes with Java. But with that said, that was only a suggestion because it may have actually caused a little bit of confusion. So there isn't actually a reason why you couldn't have used the name linked list, even though Java's already used that. So I just want to open up a slideshow and just talk briefly about a few things. So firstly, in talking about packages, things to keep in mind that there's over 9 million Java developers worldwide. So classes or interface name conflicts are going to be inevitable because the thing to remember is that people are going to use common words, so it's highly likely that you're going to find these conflicts. So as a result of this, Java were pretty well forward thinking, and there was a mechanism that was actually needed to fully specify the class, and as a result to allow use of classes with the same name in the same project or even the same class itself. So let's go back to the code and talk about that a bit more. So what we're going to do is just type a bit of code here just to show how these packages actually work. So to start with, I'm going to actually type node equals null, like so. And as you've seen before in the course, Java is going to come up and say, I've got some options for you. So if we select that, now look at all these different options that actually come up. There's actually 9 there. So there's actually a ton of different options that Java is actually recommending with the word node in it. So because this lecture is all about packages, you probably guessed by now that the mechanism I'm talking about to make sure that people can reuse names is actually called packages. So a package, think of a package as a way of grouping related classes and interfaces together. So the actual package mechanism provides a way to manage the namespace of object types, and it also extends access protection beyond the traditional access modifiers you've seen before, public, protected, private, etc. So we'll actually be talking about access in the next lecture, not here right now. So I've actually seen this come up before. When this does pop up on the screen, the normal response has been to import the appropriate package. So we go down and actually select the appropriate package. And obviously at the moment we've got an error. So if we go down here and actually choose, say, javax.scene.node, which is one of the nodes, that obviously gets rid of the message. And then automatically, as you can see here on line 3, the import line got added to the start of the line. Now that's just one option. That's one way of doing it. There's actually another option that you can use instead of using these imports. So we can actually delete that again, delete that out. And obviously that brings up the same error again. And instead of actually importing, we can come up here to the start of node and we can actually type in javafx.scene.node. And you can see at that point that Java is now happy and IntelliJ is happy because we've actually specified the actual package that contains the node class that we want to actually work with. Now the important difference here is, unlike the first situation we did a minute ago where we saw the import statement come up on line 3, in this case the package is not imported. So what that means is every time you want to reference this node, you actually have to type it out. So you can see how that would really get tiresome really quickly, having to type javafx.scene.node and doing that for all your classes as you're actually using them. Now, if you're actually using 2 different node types in the same class, then you actually have to refer to one of them that way. So if we try to import the same class from 2 different packages, Java's going to give us an error when we try to compile. So if we actually want to put our imports in, we decide to actually use the import. So we do something like import javafx.scene.node, the first one, and we try and do this, import a second one, org.w3c.dom.node. Notice the error there already. And then even if we actually come along and put org.w3c.dom.node, another node, we've already got an error here, and it says javafx.scene.node is already defined in a single type import. So we've actually already used node essentially. So IntelliJ in Java is not going to allow us to do that and get away with that, even if we're qualifying our classes with the full, what is the package for that class. So what we could do then is, therefore, with the first statement, we could get rid of that package and just use the normal reference. So if I come along here and leave that as node now, I'm going to temporarily comment this out, and we'll get rid of that second one. I just want to show you another way of doing things. So with that method, we can then come along here and we can uncomment that, and that's going to work fine at that point. So one of them is using the import, and the second one is using the fully qualified name pointing to the actual package that's actually got node. But noting again that we can't actually have two imports. So if you put the import up here, org.w3c.dom.node, we're going to get an error on the second line, and then IntelliJ starts trying to help us because it's a little bit unsure as to which import to use. So we're going to delete that, like so. So in summary, the javafx.scene.node can be referred to as node, as you can see in the code on line 10. But the second one, the org.w3c.dom.node, has to be fully qualified whenever it's used. Now you're actually free, obviously, to actually use the full name for both of them, and that can actually make it clearer as to which one you mean. So in other words, you could actually come up here and paste that into there. Oops, added an extra node there. And use both, and then obviously you can see IntelliJ's actually got rid of the imports. Now, just in terms of those imports, just to be clear, some of that's happening automatically because of the way that I've actually configured the editor. So I want you to go into IntelliJ and go into Preferences. Now, if we go to Editor, and there's a couple of ways of doing this actually. What you can actually do, I'm not sure whether I've actually mentioned this to you before, but you can click on a particular section and you can do a search, and it will actually give you a shortcut. So I can type in import, because that's the thing that I wanted to look at, and it will actually point out where that is. So in this case, it was under General, Editor, General, Auto Import. So that's actually the one I wanted. So if I go there and just to show you the options I'm talking about, you can see that we've got some options for our imports. We've got the Show Import pop-up, Optimize Imports on the fly, Add Unambiguous Imports on the fly. We can actually exclude from import and completion if for some reason we didn't want that to happen. But the one I actually want to talk about is optimize imports on the fly, because that's the one that's actually adding and then deleting imports as our code changes. I actually like to have that option on. And the reason for that is that it just cleans up your code. If you're no longer using an import, then IntelliJ is automatically deleting those, and that just makes your code a little bit cleaner. So I would suggest that you have the options for auto import in IntelliJ set to that what I've got on here. And notice also other languages, you've got similar options there to actually set for different languages depending on what you've set up, what plugins you've actually got in IntelliJ. So I'm going to leave that option there. And then the only other one here is ask. If you're pasting in a block of code, IntelliJ will come up and ask you which imports. That can be a good idea to do as well, so I suggest you leave that on ask. So I'm going to cancel out of that because I've already got my settings set. So basically you can see now, if we've got more than one class of the same name, it can get a little bit confusing, or there's more work to do to make sure you know which one you're referring to. You either have to use one import, then refer to the second one with the same name by its fully qualified name, with the actual package name, or you need to just use all the references and actually have the fully qualified name, whichever you want to do. So just going back to our slides for a minute. Now, you might be asking now, why would I want to use packages? Well, some of the reasons that you actually want to use packages is that it makes it actually easier for programmers to determine that classes are actually related to one thing or another. The other great reason is it's easy to know where to find the classes and interfaces that can provide the functions provided by the package, because they're all sort of in the same group, if you will, or the same package. And the other important thing is because the package creates a new namespace, the class and the interface name conflicts are actually avoided as a result of that, because they're actually in their own separate area, which effectively is what that namespace is. It's sort of a different area that all these classes and interfaces are actually sort of put together or placed together. And importantly, classes within the package that you create have unrestricted access to one another, while they still restrict access for classes outside the package. So that's another sort of very important reason why you'd actually want to use packages. So let's go back to our code again. Now, you may or may not have been aware of it, but we've actually been using packages throughout this course to date. One example is java.util.scanner. Now, you've seen that in many programs, and that's the code that actually provides the ability to accept user input. And we've used that in quite a few previous videos. Now, we've also imported java.util.ArrayList, And we use that in order to use array lists in our programs. And of course, we've used array lists and other lists quite extensively so far. So basically, it's actually impossible to create a Java program without using at least one package. And java.lang, for example, contains the class object that is used to support our classes, as well as integer and double, etc., and all the fundamental building blocks of a Java program. So that happens automatically when you create even the most basic of Java programs. Now, you will actually not see an import for java.lang because it's automatically imported for us. Now, you could import it. You could import, just say, for example, if you wanted to use an integer, you could come along and you could actually type import java.lang.integer, like so, and it's actually been removed automatically because of those the optimization settings in IntelliJ. But my point is, you could do that, but they're automatically, for this base java.lang package, they're actually automatically imported anyway, and it's not something you need to worry about. Just in case you're wondering where all that code comes from, any of the basic stuff like classes and as I said, integer and double, they come from java.lang. Now, before we actually create our own packages, which we're going to be doing, it's probably worthwhile to have a look at some of the other ones that are included when you actually install the Java Software Development Kit. Okay, so what I'm going to do at this point now is create a new project, and we're just going to go through a bit of a demo to solidify our understanding. So I'm going to type in select new project, select Java, create project from template, making sure command line app is selected. I'm going to call this one WinDemo. Doesn't really matter what we call it. But I'm actually going to type this one as com.example.awt sample. Now, the com.example could easily have been com.timbachowka, but we're just going to use that as this example. Click on finish. We're going to use this window because we've got the other project open to close that, so I've only got this one opened. And what we're going to do then is we're going to leave this main class, we're going to create a new one. So we're going to come up here into source and into our package, and new Java class. We're going to call it my window. And for that one, what we're going to do is we're going to write a bit of code that actually draws something on the screen. So we're going to type extends frame. And frame is the java.ort, as you can see there. And notice how the import went through straight away. And we're going to create a constructor. And it's going to accept a title as well. We've got frame, which accepts a title. And the title is going to show on the little window that pops up. So we're going to use that constructor. And actually, we'll get rid of this throws headless exception because we don't actually need that. That's just added by default by IntelliJ. So we're going to set the size of the window. Set size 500, 140. We're going to add a window listener. And I'll talk about these shortly, what they actually do. Window adapter. And window closing is the one we want. It's asking us which one do we want to override. We want to override window closing to do something when that closes. So I'm going to click on that. And you can see it's automatically come up with that code for us. But I'm going to change the super.window_closed and actually put system.exit. And essentially what we're doing there is we're just saying if you click on the close button in the window, it's actually going to override the standard function and actually close down the app, which, believe it or not, doesn't happen by default. And just a general note here, I'm going to put a screenshot on the screen there now. So instead of using window closed, we should really be overriding window closing. Otherwise, the application will keep running in the background. Now, window closed, well, that's called when a window has been closed, while window closing is called when a window is in the process of being closed. Now, in an ideal world, it would probably be better to use JFrame and swing utilities.invoke later when creating a frame, but I haven't really worried about it too much here because this is really meant to be just a simple example, and we're not really talking about swing at this part of the course. All right, so back to the code. We also want to override another one, which is paint. And this is a method that is actually called automatically to actually draw the screen. So we need to leave the super.paint in there. And this is only a few lines of code here just to show basically how these packages work. So we're going to create a font, sans serif large equals new font. Type is important there. Need to get the correct upper and lower case. Be font.bold 18, size 18. Now, just to be clear, the exercise is about packages and not about using the actual graphical side of Java, just to be clear. But we'll continue on. As sans serif small equals new font sans serif again. And be font.bold, this time with a size of 12. Then we need G, which is the graphics object that was passed to this method, set font. And be sans serif large initially. Then I'm going to g.drawString, which is a mechanism to actually draw something on the screen. And I'm going to put the complete Java developer course. And we're going to position it at 60,60, like so. Then g.setFont, sans serif small, g.drawString by Tim Bachalka, 60,100. You can probably guess now what this actual program does. And just to confirm, when we actually extended up here, when we actually extended by frame, you saw IntelliJ offer some suggestions, and I accepted the import, the top one, java.ort.frame. Now, I want you to notice that when we actually did that, did you notice how this first import that went through was java.ort.star? Probably should have mentioned that a little bit earlier, but I didn't type it like that. Whereas in these other things, when we use the Windows adapter and the window event, it's actually only imported those, but with the java.ort, it's added .star automatically. So we'll have a look at what that means and why later, but for now we're going to use some of the other packages, as you can see, to create a very simple window. But we use some of the other packages, window adapter and window event, and we've created just a very basic window. So basically this is just a standard mechanism to enable us to pop up something on the screen. So now that we've created that class, we can go back to our main method, our main class I should say, the main method within that, and pop this up. So let's do that. We'll call it my window equals new my window, complete Java, and my window got set visible true. So there's actually the code now to actually run it. So we should be able to run this now, and it should actually pop up our little window. And there's our little example, as you can see there, very basic, but it is actually working. The actual name that I actually signed, the complete Java developer course, and obviously my name as well. So what's the point of all this? Well, if we just go back to my window again, can you actually imagine having to do this all automatically? You can see there's, relatively speaking, considering what's actually happened, there's actually very little code you actually had to type. All the infrastructure code to do a lot of this work is automatically in these various classes, these packages that have been provided by Java. So writing all this yourself, writing a window manager, something that actually creates fonts, that actually sets different fonts, that enables you to draw things on the screen, positioning it at certain places. That would be a huge undertaking to do something yourself, and it could be months or even years of work. But by using the Ort package, we can actually take advantage of the facilities that it's provided for producing these GUI programs. And just in case you're wondering, Ort, AWT, stands for Abstract Window Toolkit. Now, because that package, the Ort package, provides everything necessary to create the GUI interface, we know that we can actually find all the classes and methods that we need within that package. And the thing is that if Ort needs to be upgraded, new packages can be deployed rather than having to update files that are scattered around the Java SDK. So that's why packages are really essential. They can actually bundle these changes, and from your perspective, nothing really changes. You're still accessing them via the package. All the new code is actually happening, and it's all actually added to that package, making it a far simple exercise for you to actually work with. So this video is getting on a little bit long now, so I'm going to actually stop the video here, and in the next video we'll continue on talking about packages. So continuing on with our packages discussion. Now you may have actually noticed, we talked about this briefly, the fact that the way the Ort classes have been imported at the top of the window is like so. So the line import.jar.ort, I mentioned before that I'll tell you what that does. The star means to import all the classes, interfaces and static objects from the java.ort class, AWT class. So you can do that, or we could have actually done something similar, which is we could have actually copied the relevant ones we wanted and done it manually. So in other words, we could have actually deleted that line there. We could have pasted in these references, but notice when I do that, when I actually paste them in, IntelliJ is actually changing this and making it a star anyway. But we could have, the point is we could have actually specified and done something similar to what we've done there. We could have done import java.ort say frame, for example, which is one of the ones we actually used, and done them all manually. But by doing the star, that's the equivalent of actually saying, give me access to everything that's in that particular class. Now, another thing you might be asking is, well, okay, we've done the star there. Why do we also need to do these? Because if we actually remove these, actually get rid of them temporarily, we actually get IntelliJ coming up actually saying, well, hang on, wherever they're gone, I need them. I paste them back, they'll actually go. At first glance, you'd think that the import above would actually be doing everything, but it's not actually the case. there's actually two different packages here. There's java.ort and there's java.ort.event. So java.ort.event is actually a separate package to java.ort. And that's why the star, the asterisk, the wildcard for matching all, doesn't actually bring these in here. Now, if we had to change the event and change that to a star, like so, then that would have meant that we wouldn't need to use window event because window event would automatically be found. But in that case, we don't want to do that. It was easier. And the other thing was IntelliJ automatically added those for us as we were actually adding them. Now, just to see what I'm talking about a little bit further, we can actually hover over frame, this part here, and I can hold down Control on my Mac, and I believe it's actually the control key for a PC. And you can see that the tooltip actually briefly pops up, and it's actually popping up on the screen there now. And it describes the frame class. It actually says that it extends from window and implements menu container. The important thing is at the top, it's got the JDK, the Java version 1.8, and it actually shows you also the package where that's come from. So if we go down here into Windows Adapter, notice how that says java.ort.event. That's the package that Windows Adapter comes from, and it's got the JDK again, and it's also got some details about the class, and in this case, the constructor, and how to actually call it, and if there's any parameters. So this is a good way by doing that, pressing again Command on the Mac, and I believe it's Control on the PC, might be Alt, I always get confused, but it's one of those on the Windows and Linux to actually do that, and you can actually then hover over something and see some more information about the package and other information relating to that particular class. Now the other thing you can actually do is you can come over here to where it's got external libraries, and I haven't shown you that before either. You can actually navigate to the Ort package and start expanding it out, so I'll click on that. And it shows all the various packages, and we can actually start sort of finding our way down there. You can also do this. You can actually come down here to Ort, and you can click that. And notice how that actually opened it up automatically. You can do that for most things as well. I'll actually find that for you. That's a really great shortcut to enable you to just sort of find the particular file that you're looking for. Because you might have been looking for, in here, rt.jar. You may not have been able to see the java.ort package from there. Again, so just click on that. Again, it's Control, I believe, on a PC, and in my case, it's on a Mac. I can click on there and I can go to any of these things. Well, I can't go to the source code to the get class level. The clicking to get to this left-hand side is only at package level. So I need to go back and click on Ort, for example, to get to Ort as well. And again, if we just close off event, you can see we've got font in there, and we used font within this before. Lots of information. And there's java.util. So if we close down Ort, there's actually lots of other ones in here as well. There's the util. We've actually used that before. There's some common things in there. Lots of different classes there, and it can be a great way for you to actually just click on and find out more information. Double click it will actually bring up some more information about the particular class. So again, just to clarify, the java.ort.event, as you can see when I actually click on event, the left-hand side, that's physically a different package to when I actually click on java.ort. It's physically a different package. It's sort of like a sub-package, if you will, sub-part of Ort, but they are different, and that's again why the asterisk, the star, the match all didn't actually work. So when you're actually importing classes from another package, you can actually choose to import the entire package, and you notice that IntelliJ did that on line 3 with the java.ort.star, or of course, as you saw on lines 4 and 5, you can actually just specify the classes and interfaces that you actually need. So there's really no right or wrong way about this. There's lots of heated debate about the pros and cons. One thing though you should be aware of, if you are actually using something like line 3 where you're putting a star, there's a possible impact if you've got a new class or interface is added to one of the packages you actually import. So if the other package contains a class or an interface with the same name, then your program's no longer going to compile. So you might think that's very unlikely to happen, but it does actually happen. One example was with the java.ort package. So there's actually several reasons I chose to use this package for the examples here, and this is one of them. So in Java 1.1, which I know was a very long time ago, the java.ort.package contained a list class. And this was often imported as java.ort.star. And of course, java.util package is also imported as java.util.star, and everything worked fine then. But in Java 1.2, Sun included the list interface in java.util, and of course, we've used the list interface quite a bit. So the programs importing these two packages continued to run, but because Java actually compiles the fully qualified class names in the compiled code. But the point here, and this is the big point, when one of the programs needed to be changed, it wouldn't compile anymore. And that's because the entire package has been imported at that point, the star, in other words. So Java actually had no idea which of the two packages the list they were actually referring to. Was it the list class in java.ort or the new list interface in java.util? So if it was a different programmer making changes to the program, they'd probably be cursing the original programmer for leaving code in that didn't even compile, when in fact the code had been fine when it was left. So the problem arose because of a change in a third-party library. So explicitly importing the class, the list class, in other words not using the star, would have actually avoided that problem altogether. Okay, so moving on, it's now time to actually create one of our own packages. So we're going to do that now. We're going to another new project, and we're going to do another Java one again. And again, create project from template, command line app as we've done before. And we'll call this one package demo. Package demo. And the actual package name, we're going to do com.example.mypackage. And create that project. And we'll put this window, so we close down the other window that we had open. And just as a recap, in case you're wondering what com.example is, the naming conventions with Java is that com.example and org.example are actually reserved and can be used for packages that you're never going to distribute. And this is very useful if you haven't got your own domain. So you can substitute org.example instead of com.example there. Or if you've got your own domain, as you've seen me use com.timbachauka, you can also use that as well. It doesn't really matter in this particular test. This is more down the track when you're actually packaging your own source code. So what we're going to do is open this up. And what I'm going to do here is I'm going to actually delete the package. But before I do that, I'm going to go here into source. Noting I'm actually in the source folder. And I'm going to, so what I'm going to do is create a new class. I'm going to right click that new Java class, noting that I'm actually clicked at the source level. And we're going to call that one main, so it's a new class there. And then we're going to come back here to package. I'm going to delete that. Delete the package. And that deletes the package and the subfolders. And notice how we've still got com.example in there. So now we're going to go right click here again, right click new, come down here to package, and we can then enter it again just to show you how to go about creating a new one. com.example.mypackage again. Notice how that's now created a new package for us. And just to confirm that, we actually right click on the project name, click on new, there's no option for package. Notice, well, there's Python package because I've got the course on Python, but there's actually no option for us to actually enter a package there. We can actually do one in the source folder. We click on that and the package option actually comes up for us to actually select a new package in Java. So the other thing we can do now is we can actually move the main class. So to do that, we can just click on that and then just move it to the package name and then release the button. It actually comes up and says, do you want to move it to this folder? And you can see the folder has got the package com/example/mypackage. I click on refactor. You notice that the main class, the new one that we created, bearing in mind the old one actually got deleted when we actually deleted the package, has been moved into this package, this com.example.mypackage again. And you can see that it's actually physically now within that package. So we go back and just have a look in the browser at this code. So if I have a look at package demo, source, now this is the actual physical folder that contains this code, and there's the code there. And I can actually just hold down the button there and you can sort of see the navigation there. We've got package demo was the name of the project, the source folder, and the package is com/example/mypackage. So these are all sort of subfolders. So the package name has been added, as you can see, to the list here automatically. So that in summary, the package statement defines which package the class, in this case main, belongs to, but the directory structure has to also match the component parts of the package name. So in other words, a folder, subfolder com, subfolder example, subfolder my package. And looking at that structure, we can see that that's mirrored exactly. Com, example, and then my package of these is the subfolder. So if we actually change this and made this org.example instead of com, we'll actually get an error, and it says the package name doesn't correspond to the file path com.example.mypackage. So they have to actually match, and IntelliJ will actually enforce that. So if we just undo that change, the error then goes away. There is actually a correct way to actually rename a package. If you want to rename a package, you just come up here and actually right click it and do refactor, rename. And you can actually literally change it to whatever you want at that point. Click on refactor and then it will actually change, taking into account that it will actually rename the actual folder. So just to show you how that works, let's go ahead and change that. So we'll change that to org, refactor. Noting how that's actually changed there. It's now org.example.mypackage. Com.example was the package that was left over when we deleted my package previously, but we've now got an org.example.mypackage, which main is now in. And if we go back and have a look at the code, noticing how source example is no longer there anymore. If we go up to source level, there's now an org example, my package, and there's our code again. You can see that it's now been renamed. So IntelliJ, when you go to actually use that, will actually rename that, as you can see. Now you can also specify a package name as part of the class name when you're actually creating a new class. So in the next video, I'm actually going to create a game package and show you how to do that, and also create some classes that might be useful in an adventure game. And we'll be using some of the code from the interface challenge that we've done previously. So I'll see you in that next video. So continuing on with our discussions about packages, the other thing you can actually do when you're creating a class is you can actually specify a package, and IntelliJ will actually make that package for you automatically at the same time as creating the class. I come up here to File, New, click on Java Class. Now ordinarily I will just type player, and that should go into the org.example.my package because I'm actually in that area. I've got main clicked, so click on OK. You can see it's automatically created that class in that folder, in that package. I'm going to undo that. So we go back and actually do it again though. File, New, Java Class. And this time if I type a package name, com.example.game.player for argument's sake, click on OK to that, you'll notice it's actually created a package sort of within a package. So org.example.mypackage.com.example.game. Now that's clearly not what we want in this particular case because we wanted to create a package which was just com.example.game. So it's important to, if you have got something clicked here to the left, to probably click, or to definitely click source. So I'm going to undo that again. And then come back to source this time. Or I can make sure, that's probably the easiest way is to do that. And then click on File, New, Java Class. And now if we type com.example.game.player, it correctly creates the new package, com.example.game, and puts the new player in there, the new player class in there. So what we're going to do now is we're going to use a few classes from our interfaces challenge. So we're going to specifically use the player class, and I know I've already created the player class, but also the monsters class and the iSavable interface. And we're going to overwrite the player class as well. So I'm going to go back to the source code for the interfaces challenge. And if you haven't got this already, if you haven't typed it in yourself, go back and you can actually download the source code from the course itself. There's actually links there so you can grab this source code. So I'm going into Interfaces Challenge, going into my source folder and down to com.timberchalka, and I'm going to select, first one I'm going to select is Monster. Now you might think you can actually just select it and drag, and it does seem like it's going to work, and you can see it's highlighting in red the package it's going to put it to, it's going to place it. But the thing is that's a move, and by moving something you're actually deleting it from the source folder. So you probably don't want to do that. You don't want to delete the code that's in the interfaces challenge, because that code will then no longer work because that file won't be there anymore. So a better option is to come back to the Finder, or and again you'd use Windows Explorer or whatever your Explorer is for your operating system. Select copy, and copy will be the same for all operating systems. There's a version there for you. So select copy, come back to the package you want and paste. And this time you can see the message is copy. The name is giving us the file name, and ultimately that'll be the class name as well. And you can see that the folder it's putting it into matches the package com example game. So I'm going to click on OK, and it's been added successfully. We're getting an error here because of course we haven't yet got the iSavable interface, but we're going to do that next. So I'm going to go back and do the same thing for that. iSavable, copy, back to here, select the package, right click, paste, and I'm going to click on OK. That's now added the interface, and that leaves us with the player class. Now currently that's empty, and what we're going to do is do the same thing. We're going to go back to the player, right click, copy, back here to com.example.game, paste, and yes, we're going to use the same name. This time we get a dialog pop up to tell us that it already exists. Do we want to overwrite it or do we want to skip it? We want to overwrite it because we want the version that came from the interfaces challenge. So click on OK. We've now got our 3 files. And just confirming, when it's doing this, it will actually fix the package name. So if the old source code had a different package, when you're actually copying it into here, IntelliJ is actually changing the package in this code for you. So it's quite handy how it's doing that for you. So what we're about to do is create a package for these 3 files, the player.java, monster.java, and iSavable.java, so that we can actually use those in another project. But before we do that, we should actually update our main class, and put in the test code that come back from the challenge so that we can actually test to make sure that things are working as they should. And it's always a good idea before you create a jar file, which is what we're doing, a library, is to make sure that the code is obviously working and tested. So we're going to go back one more time to our Finder. I'm going to select main. I'm going to copy that. And we're basically going to go in here to com.example.game, and I'm going to paste it in there. And I'm going to overwrite the existing main.java. Actually, there wasn't a main.java because, of course, I was thinking of the main.java down here on org.example.mypackage. So we've now got 4 classes in our com.example.game. And what I'm going to do now is just remove this other package, this org.example.mypackage, because we no longer need that anymore. So I'm going to right-click that, delete. And I'm just going to double-click main, which is already selected, and we'll just run that to make sure that it's actually runnable, works, and there's no errors. And you can see we've got the same output we got from the challenge, the interfaces challenge. So the code's obviously okay, there's no problems, we're not getting any compile errors, and you would obviously do your normal testing at this point to make sure that it actually worked. So assuming that's working, what we're going to do now is delete the main class. I'm going to delete that. And the reason we're doing that is we're going to be importing this project, these 3 files effectively, into a jar file that will then be imported into another project altogether. And that project will have its own main class. So we're specifically trying to include only the code relating to the actual game itself. So now that we've actually removed the other examples, I'll actually remove this org.example as well. So if that shows up for you, delete that as well because we don't need that anymore. So we're left now just with the com.example.game package and the 3 files. So what we want to do next is go into File, select Project Structure. Then what we want to select then is Artifacts. We want to create a new artifact. So we're going to click on the plus button. We're going to click on jar because jar is stands for Java Archive, and that's like sort of like a zip file but for Java code. And we're going to select that and come over here and click on From Modules with Dependencies. When I do that, you should see that package demo came up automatically as the module. Module is basically the project in this case, the package demo, although you can have multiple modules in a single project. In our case, we've only got just the one. Now, if you wanted to make the jar file executable, you would specify a main class, but we don't want to do that, so we're going to leave that blank. We're also going to extract to the target jar as well. I'm going to click on OK to that. Now, this actually gives us a folder, and if we have a look and just go to the end of that, this actually shows us in this current project /out/artifacts/package demo _jar, which is still a folder name. That's where it's going to actually create this jar file, package demo.jar. So make sure you actually know where it's going to be creating that by having a look at the output directory. Once you've done that, click on OK. That's now specified the folder, and we can actually just go ahead and we can make the project. We could also at any time build artifacts. And build artifacts enables you to actually build this jar file. So package demo jar, you can see we've got options to clean, edit, rebuild. I'm just going to click on build. And a very quick process, you probably saw something briefly down the bottom left-hand corner of the screen. That jar file has now been created. And just to confirm, if we go back to our Finder, to our navigator, and actually have a look, we'll look now in package demo because we're finished with interfaces challenge for now. Package demo out. There's now an artifacts folder that's been created. Package demo _jar folder, and there's our package demo.jar that has been created by that build process. So at this point, what we're going to do now is we're going to actually create a new project, and we're going to import that library and just make sure that it still runs. So I'm going to click on File, New, select Project, select Java, go Next, do what we normally do, create a command line app. I'm going to call this one Game Test. Into the base package name, click on Finish. IntelliJ is asking us, do we want to close this project down and or have 2 open? In this case, I'm going to click on this window because we don't need the package demo anymore. So click on that. We've now got a very base package, as you can see there, the base project, I should say. And at this point, what we can then do is we can actually import that library. So if we have a look at external libraries, you can see there's a heap of libraries there that are part of the Java ones that we've talked about. But our library's not in there yet, obviously, because we haven't actually imported it. So what we're going to do now in this new project where we want to actually use the jar file that we've created, click on File, go into Project Structure. Then we want to go into Libraries. We click on Plus. We want to specify that it's a new project library, a Java one. And we need to specify where that is. So I'm going to go down to our folder. We created it, which was in Package Demo out artifacts, and that one there you can see it's the package-demo.jar, which is in the package-demo_jar folder that was created when we had the other project open. Click on OK, and it actually tells us that the library package demo will be added to the selected modules. Game test, which is the name over here of our project, our current project. We do want that, so we're going to click on OK to that. Then we click on OK. So now we've actually done that. We have a look at external libraries. We've now got another option here. We've got package demo showing as a library. And if we expand that out, you can see we've got our package com.example.game, and we've also got two classes there, monster and player, and one interface, iSavable. So now that we've actually done that, you can presume the code is there now, the executable code to actually run this. So what we can actually do is actually add some code to our main.java, and we should be able to run this now. And instead of the previous interfaces challenge, where we were running the code that was part of this project, we'll be running the code that's really embedded or included in that package demo.jar. So the easiest way to do that is just to go back to our interfaces challenge. And what I'm going to do is copy the main. And I'm going to actually paste it. I'm going to open and close down the external libraries, open up our project. I'm going to paste it in com.timberchalka, which will overwrite the existing one. I'm going to do that. And confirming that yes, we do want to overwrite it. Now, did you see what happened there? There was a brief delay where the import statements weren't there, then they actually showed up automatically. And again, they're automatically coming up because of the way we've configured our preferences, which I showed you in not last video, I think it might have been the video before, but in an earlier video in this section in any case. And it's automatically found these three classes, this time in the external library, package demo, as you can see there. And that's why that we're able to run it. So if we actually now run this, we're still getting the same results. The code is being executed, but of course, looking at our project, we've only got a main class in com.timberchalka. We haven't got those other classes because they're actually coming from this package. So that's how to go about actually adding a library or creating a library, as you saw, and then adding it to your code. And that's a good idea if you want to have some code that you reuse for multiple projects. You create a library like we've done there, then you import it using the mechanism that I showed you, and then IntelliJ will actually do the rest for you, as you saw there. So that's it for the package discussion. In the next video, we'll go ahead and actually do a package challenge. So I'll see you in the next video. So in this video, we're going to actually talk about the package challenge. So I've already actually pasted in the challenge for you to actually do. And going through it, we need to create a suitably named package containing a class called series. And that class should have the following static methods. First one's nSum, which has actually got an int n parameter, and that actually returns the sum of all numbers from 0 to n. So then the first 10 numbers, to give you an idea, are 0, 1, 3, 6, 10, 15, 21, 28, 36, 45, and 55. The second static method is factorial, which also accepts an integer, and that should return the product of all numbers from 1 to n, n being the parameter, of course. So i.e. 1 times 2 times 3 times 4, right up until n take 1 times n, as you can see on the screen there, multiplied. So the first 10 factorials are 0, 1, 2, 6, 24, 120, 720, 5040, and so on. And the last one, Fibonacci, the Fibonacci static method returns the nth Fibonacci number. And these are defined, as you can see there with that algorithm. F0 equals 0, F1 equals 1, and then Fn equals Fn take 1 plus Fn take 2. So there's actually the algorithm for Fibonacci on the screen there. And you can see in that case there, F2 is also 1. So the first 10 Fibonacci numbers, 0, 1, 1, then it's 2, 3, 5, 8, 13, 21, 34, and 55, and so on. So once you've actually tested your functions, delete the main class and actually produce a jar file. You want to create a new project and add your series library to that project, and then test the 3 methods in the main method of your new project. And what you want to do is actually use this code, which I'm going to paste in when you actually test it. That'll be the code there. Now that obviously won't work at the moment because I haven't actually created and added the library, the series library yet. But that will be how you'll actually go about actually testing your code. And as you can see, again, they are static methods. So that's the challenge. So now it's your turn to actually see if you can solve this challenge. Go away and actually create the series class and the 3 static methods and do some testing. create a library, and when you're ready to actually come back and actually see the solution, start the video again and I'll go through it. So pause the video now. Okay, so how did you get on? Did you figure it out? So let's actually go through that. So the first part was we needed to create this package, or this class I should say, called series, and with the three static methods, HinXcm, factorial, and Fibonacci. So what I'm going to do is create a new package when I actually create it. I'm going to come up to my source and do right-click it, new Java class, and I'm going to actually call this com.timberchalka.mylibrary.series. So the class name is series and the package is com.timberchalka.mylibrary. Click on OK. And you can see we've got the new package created and the class also create. So let's actually go about now creating the three methods. So the first one we're going to start with is the HinXcm. And HinXcm is a matter of is the easiest of the three. So it's public, static, returning a long, HinXcm, int n, returning a long because it's basically can accommodate a larger number if we want to go higher. And the actual method, if we go back to our code again, to our example, HinXcm returns the sum of all numbers from 0 to n to whatever was actually passed, n being the parameter. So to return that, all we need to do is return n multiplied by n plus 1 divided by 2. And that actually should give us the answer. And we'll test that shortly. We'll actually write the three methods, test them, and then we'll actually create the actual library. So going back to our main, the second one was the factorial. Return the product of all numbers from 1 to n, i.e. 1 times 2 times 3 times 4, etc., right up until n take 1, or multiplied by n take 1 times n, as you can see there on the screen. And it gives you some examples of the first 10 factorials. So the code for that, still pretty straightforward. Public, static, long, factorial, int n, because that's the parameter of course. Now firstly we need to do a test for 0, so if n is equal to 0, we can actually just return 0, because obviously we can't calculate anymore. And just a quick video edit here, I'm making a change after the original recording, and I've made a change because there's an error here. And the issue here is the factorial of 0 is actually 1 and not 0. And you can see that in the code here, I'm returning 0, which is wrong. So the correct code you can see on the screen now should be returning 1 and not returning 0. So you might want to make the change to return 1 in that scenario, and the code will then work properly. Otherwise, we're going to actually start with the value 1, and then we're going to do a for loop and actually go through and multiply that, or add to that the multiplication for each one. So to do that, we're going to go for int I equals 1. I is less than or equal to n, then I plus plus. And then we just do fact equals fact multiplied by I. And then we return fact. You can see there. That's actually it. That's the factorial. And the last one we need to do now is the Fibonacci. And just going back to our overview, returns the nth Fibonacci number, and you can see there the way we actually calculate it. So fn equals fn take 1 plus fn take 2. And f2 in this example is also 1, and we got the example of the first 10 Fibonacci numbers there. So let's go ahead and do that. Public, static, long, Fibonacci, int n. So we start off doing a test for 0. So if n is equal to 0, just like the factorial, we can actually return 0. Sorry, return 0. But else, if it's 1, we can actually also return 1. So basically, if it's 0 or 1, we're returning those hard-coded numbers, 0 or 1. But if we get to here, we know that the number has to be 2 or higher. So we put long n minus 1 equals 1. Long n minus 2 equals 0. So that's the initial values, because we're going to take the number minus 1 will be 1, because we're going to be getting a number that's at least 2 or higher, and n minus 2, we're just going to start off with 0, because of course n being 2, n take 2 is going to be 0. So basically we're initializing that with the two values, assuming the number was 2. And then we run through our for loop. So we put for int I equals 1, I less than n, I plus plus. Then we calculate it as fib equals n minus, and I need to create a variable long for fib equals 0. Fib equals n minus 2 plus n minus 1. And then we put n minus 2 equals n minus 1 because we're incrementing the loop. Then n minus 1 equals fib. So basically we're setting fib initially to n minus 2 plus n minus 1. Then we're setting n minus 2 to equal n minus 1. And as you can see in the last line, n minus 1 then becomes the current value of fib. And that's it. So we let the for loop go through and complete, and then we return fib. So that should be our Fibonacci method. So now we've actually done that, it's time to actually create the actual package. So what I'm actually going to do now is actually remove the main method, because we don't want that in our file, our jar file, so delete that. So we're only left with series. I'm going to come up here now to File, Project Structure. I'm going to choose Artifacts. I'm going to add, or click on plus. I'm going to select jar from modules with dependencies. We're going to just leave the default set. There's no main class, which is correct because we're going to write the main class to do the testing. And the jar file is okay. Click on OK. And you can see it gives us a default location. Java programs package challenge underscore jar. And we're looking in there shortly to get the jar file so we can actually include it in the new projects we're going to create. Click on OK to that. And that's actually created. Then we can go up to build and build artifacts to make sure that the jar file is built. I'm going to select build. So that's now built. And we'll just go and check that. So let's have a look now. Package challenge, out, artifacts, package challenge underscore jar, and there's our jar file. So that was built successfully. So now what we want to do is create a new project, and we're going to actually import this series class via the package challenge jar file into that new project. So I'm going to go back into here, file, new project, a new Java project. And I'm going to call this series test. We can call that obviously whatever you like, but series test, common.timbachalka. So what I'm going to do is create something completely different. So we used common.timbachalka before. Let's actually try common.example.series.test like so. So it's a completely different base package. Click on OK. And we're going to use this window so we can let the other one close because we're finished with that project. So we've now got this one. And the next thing we want to do then is we've got our main method, which we're going to write our test code in. We want to actually go to project structures and libraries, and we want to actually add our artifact file. So I'm going to click on Java. I'm going to go back to our challenge, package challenge, out folder, artifacts folder, package challenge folder underscore jar. Then there it is, our package challenge underscore jar. Click on OK to that, and it's going to be added to the series to the selected modules. That's click on OK to that. That's fine, and click on OK. So now we've got that. We can go into external libraries, and we can see we've got package challenge, and you can see we've got our series class. So it's obviously found it, so that's good. So now we should be able to write some test code. And if you remember, I actually had that test code from before. Let's actually check this out. So we're going to go for int I equals 0, I is less than or equal to 10, I plus plus. So let's try the nsum first. That's going to be system out, and we'll put series.nsum I. Noting that it actually found our class automatically and did the import as soon as we started using it. And you can see now it's a different import altogether, com.timbachalka.mylibrary.series. So we'll run that. And we've got the numbers. And at the start of the video, I mentioned that the numbers we were looking for was 0, 1, 3, 6, 10, 15, 21, 28, 35, 45, 55. So that's working correctly, which is good. The next one, factorial, let's do that. It'll be for int I equals 0, I less than or equal to 10, I plus plus. And we'll print out the series dot factorial for I. If we run that, And actually what I might do there is just print out some asterisks there just to indicate that this is to show us there's a separator between one method's output and the next. And obviously what we were looking for was 0, 1, 2, 6, 24, 127, 25,040, 40,320 and so on. So that's obviously working for the factorial as well. That's good. So let's go and do the last one now. And the last one, of course, is going to be into I equals 0. I less than equal to 10. I plus plus. And we're going to print out series dot Fibonacci for I. And the output we'll be wanting for Fibonacci 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. So let's run that. And there we go, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So that's actually it. So that's the actual solution. So you're now able to, if you followed along, create your own packages and use them in other Java projects. So I hope you did well with that challenge. It's now time to move on to the next part of this section, and that's all to do with scope and visibility. So I'll see you in that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
Okay, so in the previous couple of videos, we learnt what packages were and how to actually use them. And it's now time to actually have a look at scope and also granting or restricting access to our objects. So the thing is with scope, it's probably one of the easiest things about programming once you understand it, but it's actually also one of the most confusing until you do actually understand it. So scope here actually refers to the visibility of a class, member, or variable. So to consider that in non-computing terms, let's imagine you're going to buy a particular computer and you find a local store and let's just say it's got the computer for 20% off, 20% discount. Now the same computer in another store would still be at the full price though. So the scope, in other words, of the price reduction is just that one local store. But contrast that to a situation where you've got a large company, and let's use Walmart as an example, huge company in the United States. And let's just say they decided to discount a particular computer. So the discount then would actually apply in about 4,500 stores across America. So in that context, the scope of the discount is therefore much, much wider. And actually, as Walmart is a multinational company, if they applied the discount worldwide, the scope would be over 11,000 stores. So the important thing here is that Walmart's discount does not apply to any other stores. So the scope is limited to the stores controlled only by Walmart. And the same with the local example, the local store that had the 20% off. The scope there is just for that one local store. So the same computer, and in a Java context would be the same variable, in other stores is not discounted. So I hope that makes sense. So our Java objects have got scope in much the same way. So what we're going to do now is code up an example to discuss the scope. We'll show you the scope of various objects to help you sort of understand the scope a little bit better. So we're going to start off by creating a new class. And we're just going to call that scope check. So I'm just going to click on and select a new class. Scope check is the name of it. And what we're going to do is create a few variables. First one, a member variable, public int. We'll call this one public var equals 0. But we'll also have a private int private var equals 1. We'll add a constructor. And this constructor won't have any parameters, but what we'll do is we'll actually just print out a message to say that scope check created, and just show the variable value. So public var equals plus public var plus, and private var equals plus private var, just to show the values. And we'll also create a getter as well. So we'll need that shortly. And the getter will be just for the private var, like so. So there's our basic scope check. So what we're going to do now is go to the main class and to the main method and check and create a new instance and then check the value of private var in main. So to do that, we're going to go back to main. In here in the main method, we're going to do string private var noting the name is the same as it was typed into the scope check. This is private to main. Then we'll create an instance of scope check. So scope check, scope instance, doesn't really matter what we call it, equals new scope check. Then we'll just do some output. The first one we'll put is scope instance private var is scope instance dot get private var using the getter. And then we also want to print out our value for private var. And of course, we're noticing that the private var there and private var here are the same named variables, but they're actually separate variables. So we've got two variables called private var. One's the string, which I've defined above in the main method, you can see on the screen. And the other is the int in our scope check object that we created, which is going to be scope instance. Now we can only access the private var in scope instance by using the getter. Again, the getter was what we created here. We can't access that directly. So if we actually run this, unsurprisingly, we get the first one, scope instance private var is 1, and that was called from the constructor. If you recall, we put that message in there. And this is private to main, is the same variable name, but a different variable that is local to the main method. And that's got a different value. It's actually a different type. In this case, it's actually a string. So within the main method itself, whenever we refer to private var, Java actually knows that we must be referring to the one declared with main, as that's the only one that's available in the current scope. So in other words, it's referred to, that variable is referred to as being in scope. So access modifiers such as public, private and protected, they're actually one way to restrict the scope of an object. And we'll be looking at these access modifiers in more detail shortly. But as it turns out, scope is even more important within the same class or method. So what we're going to do now is shoot over to scope check, our scope check class, and we're going to create a new method there. And we'll call that one public void times 2, and it's just going to be a simple method that actually prints out some of the 2 times tables. So we're going to start with the definition, private var equals 2. Note the name of the variable and note the fact that on line 8 we've also got a variable with the same name. For int I equals 0, I less than 10, I plus plus, and we're just going to output I plus times 2 is plus I times private var. Very, very simple, as you can see there. So the method, as you can see, as I mentioned, also declares a variable called private var and sets the initial value to 2. So when we use it in the loop, I is multiplied by the value of this one, of this variable here, and not this variable here. And that's because private var that's actually local to this method is actually in scope. So just to confirm that actually is the case, we're going to go back to our main method. And let's actually just print that out, or just run this method. So scope instance dot times 2. So if you run that, we should actually confirm that that's working. 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4, and so on. So it's clearly multiplying by 2. And if we go back and actually look at our code, we've got this line here on line 19, setting the local variable private var to 2. And obviously, if Java wasn't reading that, it would be coming back up here and looking for private var, which is have the value 1. So you can actually see that in our example, it clearly did work. It multiplied by 2. So by declaring that private var again inside the times 2 method, we created a new variable whose scope is the current method. So anytime we refer to private var inside the 2 times method, we're now actually referring to the variable within the most local scope. So although they've got the same name, the rules of scope ensure that the variable with the narrowest scope is the one that is used. Narrowest being the one that's most local. So in this case, private var in the times 2 method. So another way to consider this is to use the concept of enclosing blocks. So when Java sees a reference to a variable, what it does, it starts by checking the current block of code to see if the variable is actually declared there. Now, if it is declared there, then that variable is used. But if there's no such declaration and it's not there, then Java actually checks any block that encloses the current one to see if there's a declaration there. So it keeps doing this, working backwards until it finds the variable declaration. And if it doesn't actually find one, then you'll actually get an error in your code. And of course, the code won't be able to run because the variable won't be found. So in this times 2 example, there's no declaration of private var within the current block. So the current block being the for loop I'm talking about. So there's no declaration in there. So Java actually checks the enclosing block, which is the method itself. So this would be the current block, the block in braces for the for loop, and obviously where the brace starts and ends, that group of code, there's no private variable defined. There's no variable with that name defined. So it then takes it out to the next level, which is the next enclosing block, which in this case is the entire method. And it does actually find the variable private var, and that's why it's able to use it, because that's the next most local one. Now there's two variables, as you can see, within this for loop that are actually being used. We've got private var that we've discussed just now, and also I. So I is actually declared in the for loop. So here, in this loop here, it's actually defined. It's actually in that loop, so it's in that scope. The scope of the two braces, in other words. So the scope is limited to that block plus any contained block if there were any, in which there isn't in this case. So to check that, we can actually try doing this and we should get an error. So if we try to do something like value of I is now plus I, we're immediately going to get an error. And as you can see, it's in red. IntelliJ is actually showing there's an error because it cannot resolve the symbol I. And if we actually tried to run it, we'd actually get the same error as well. And that's because I is declared in the for loop, but its scope is actually restricted to within that loop, and it's not actually available outside of that loop. So as soon as the loop terminates, in other words, as soon as it actually finishes off, 9 times 2 is 18. So once it's done that, and it has exited that block of code, effectively, that's it. The variable I then goes out of scope. So just to confirm again with the scope, so what we'll do now is we'll just comment this line out because we don't need it because it's not going to work. And if I was to comment this line out here, the private var equals 2, which is the local variable we introduced for the times2 method, obviously we haven't got an error, and the reason now is what's happening is Java has looked at that and determined there's no local variable and kept looking above, sort of expanding its search, and it's found this private var in the scope check as a member variable. So if we run this now, even though it says times2, that's because we've actually typed that times2. But you can see the calculations clearly are now multiplying by 1. So it's actually using the value of private var, the member variable on line 8, instead of the local variable that we defined on line 19. So we'll just uncomment that again. So it's actually working. And obviously if we run it again, we now get the correct answers again. Now note here in this situation that the class field, private var with the value 1, still exists and it retains its value, and it can actually be used outside of the 2 method. And as it turns out, we can actually even use it within the 2 method, even if we've also got a variable of the same name. And what we have to do in that scenario is we need to tell Java that we want to use that private var rather than the local one. So what we do is we do that by qualifying the variable name with this. So in other words, if we did specifically, you had this variable on line 19, int private var equals 2, but you specifically wanted to use this variable that we defined at class level, then we could do that. We could change this and we just actually type the word this dot in front of private var, and that actually tells Java, use this variable on line 8, even if you've got a variable of the same name in this in scope effectively. And you've seen that in the course a lot of times with getters and setters when we refer to this dot field name to actually specify the field. And obviously if we run that, we're back to multiplying by 1 again, and that's because we've used the this dot, and Java knows then that we're actually talking about this variable on line 8. And incidentally, if I commented that out, we then get an error. This dot private error doesn't exist anymore, because as far as Java is concerned, you've told it to look for a field in this class or the name of private var, and there's no longer one because we've commented it out. So I'll just undo that again. I'll just set this back to what it was as well. Now the concept of scope doesn't just apply to variables. Methods also have scope as do classes. Class scope can be a little bit confusing, but let's actually start by adding an inner class to our scope check class and have a look at what it does to the scope of things. So I'm going to come down here at the bottom of scope check and add an inner class. So I'm going to call that public class, and we'll call this one inner class. And let's set up a public variable, public int private var, and so on at the value of 3, so it's distinct from anywhere else. We'll create a constructor, and we'll just do a simple output inner class created private var is plus private var, and let's also add exactly the same method we had there, the times2 method. And I'm going to paste that down here again as a method for inner class, and I'll just delete that. It's a little bit confusing with that now. I've commented that out, so I'm going to delete that there as well. making sure that I haven't got this specified anymore in either of the ×2 methods. And what we want to do then is create an instance of this inner class, and we'll go back to do that in the main. And we do that using that slightly odd syntax we covered previously, in previous videos for inner classes. So it'll be scope check dot inner class equals scope instance dot new inner class. Like so, I know that's a weird syntax, but we have talked about that in previous videos. And let's now run that code, inner class dot ×2. And just if we run that, and what we'll do here is we'll actually put some exclamation, some asterisks here just to make it clear. And we actually run this. You can see the inner class was created and we've got the same calculations happening. So that's all working fine. So once again, getting back to the code, the rule of scope applies, and because private var is declared as a field of the inner class, in this case here now we're talking, and actually what I'll do here just to make this clear is I'll actually delete this declaration here. That's actually what I wanted to do. So that's in the ×2 method for inner class, I'm actually deleting the private var. We've run that. This is what I actually wanted to show you. So in this case, what's happening? Well, previously when I had the local variable in there, it used that. But as soon as I've actually deleted that, of course, the scope, the Java is going back checking what the scope is, and it comes back and finds private var, which is defined here in the inner class as the field, and it's using the 3 for calculations, as you can see there, 3, 6, 9, 12, 15, etc. So in this case with the inner class, this definition here, public int private var equals 3, still overrides the private int private var, which is in our scope check class. And just out of interest, it doesn't actually shadow the private var and scope check ×2. So in this first one here at all, those two blocks are not enclosed by or enclosing each other, so there's no actual possibility of either variable being in scope in the other method. And once again, we can actually comment this out if we wanted to here. We don't get an error, so you can see there, and now if we run it again, we're getting the calculations multiplied by 1. So what's happening again is it's looking for a private var, can't find it in the inner class, or couldn't find it either within as a local variable in the ×2 method. So it's come up here to private var in scope check and to retrieve the value of 1, and our calculations actually use that again. Now if we actually came back here to ×2 within the inner class and we use this, we actually get an error, and that's because it's looking for the field in inner class. Now obviously that hasn't got a value because it hasn't been defined within inner class. So what we can do then is in that example, we can type scope check.this.private var, which confirms that this is the variable up here that we're actually talking about. You can run that and you can see that's calculating correctly based on the value of 1. But then if we actually uncommented this out again, so we now have got a field in the inner class called private var. If we run this, we're still getting the same calculations based on 1 multiplying by 1 because that variable has been defined in scope check, and because we've used the name of the class .this.private var. So we've explicitly said use this field in the scope check class. And then just out of interest, in the ×2 method, we could use scope as well. We could actually, if we wanted to actually call the ×2 method, we could do scope check .this.×2 if we wanted to specifically call that method that is a method in the scope check class itself. So what I'm going to do is actually finish this video here now. It's getting a little bit long. In the next video, we're just going to finish off a few little minor things to do with scope. We're going to talk a bit more about visibility, and then we're going to start on a challenge. So I'll see you in the next video. So in the previous video, we talked about scope for the first time. So what we'll do is we'll actually test that with a challenge at the end of this video, or possibly the next, depending on how long the video goes for. But we'll be talking about visibility. But in Java, getting back to scope, things can be a little bit more complicated, and that's because objects themselves also have visibility. But before I actually go about explaining that, what we'll do is we'll do a bit of refactoring so that our private var variable names will have different variables themselves, have different names, which is going to make them easy for us to refer to. So firstly, in scope check itself, what we're going to do is we're going to refactor the private var and call it var1. So I'm just going to click on that, right click, refactor, rename, and I'm going to call that var1, var1. noting all the places in the code where that's being updated. Note down here, IntelliJ was smart enough to figure out, okay, you're using the field which is part of scope check, and it's updating that as well. So I'm going to press enter then to accept that, and I need to put space there. Actually, what I'll do is I'll undo that. I'll try again. So I'll right click, refactor, rename, and I'll delete all this extra guff out this time. We want to call this one var1. var1, press enter. And it's actually telling us, do we want to actually rename the getter as well? And that can be a good idea because at the moment it's called get private var. So I would say yes to that. And then down here, what we need to do is we need to actually click on do refactor. Basically, are we happy with the scope? And this is the way that IntelliJ shows you what's going to basically change. In this case, it's quite simple, so you can see what can be changed. But in cases where you've got a lot of code, you can actually come down here and actually see all the places where the code is going to be changed, and it can be really useful. In this case, I click on do refactor, and you can see we've changed all the variable names, and also note the getter has now been changed as well. I'm going to change this actually, and leave that as private var for now. So that's scope check. In the inner class, what we want to do is we want to actually rename the field to var3. So I'm going to come down here and rename that rather to var3 with refactor rename. var3, press enter. And again, we're going to do the refactor because there's multiple places. I'm just going to accept that. That's been updated. And coming back here to the scope check method ×2, we're going to actually rename that. I could just type it, but I'm just going to refactor it again. Refactor, rename. I could have pressed Shift F6 there, as you can see on the screen, if I wanted to go directly to that. And you can see it's Shift F6 also on Win Linux. And delete that, and we can change that, and we'll call that var2. Just so we're really clear now. And incidentally, when I did the first refactor, it also changed what was in double quotes. So I could have actually got it just to change the variables, just not made that other change, but in this case I just accepted it all. So it actually has changed the actual name of the variable also in the double quotes as well, the actual string representation. So lastly, going back to main, down here, what we'll do, just to be consistent, we're going to rename or refactor that. And we'll call this var4. Notice also that when we renamed the getter, it automatically changed that in the main method, which again, pretty cool how IntelliJ could do a lot of that work for you, making things a lot easier. But notice also what's happened here. This is probably not what we wanted. When I did the renaming of in the scope check for the third variable, I'll just go back and have a look, var3, it actually renamed this as well, and that's because it did a match on that the name, the private var string, the text in there, and actually renamed it as well. So I'm going to change that back. That should really be var1 now, because this is where we're getting it from. We're getting it from the scope instance, and it should match that. And just coming back here, I actually made a typo there. I didn't actually type that properly, so I'll just refactor that again. Let's call that var3. Press enter, as you can see there, and now we've got it working. And going back to the inner class, what we're going to do there is we're going to actually show the var3, and I actually call it var3 there, because that's actually what it is now. So we're showing the value for the inner class, but let's also show var1 as 1. So var1, 1 is plus var1, plus, and var3 is var3. And coming back here, I'm going to delete that method call, which was only an example. And I'm going to actually print out var1 is still available here. And you can see that we haven't got an error. So as far as IntelliJ is concerned, it's quite happy to actually put it in there. So now that I've done that, the reason I was doing that is I want to show you the scope of each variable in turn. So starting with var1, variable var1, the first one we defined up here. So that scope is the entire class scope check. And you can see that's used in the constructor, var1, but we've also actually put it in the inner class as well. You can see it's in the inner class constructor as well as the ×2 method. So the class and all inner classes have got access to var1, and that's because it's a field of scope check. Now because we renamed it, it's no longer shadowed by the inner classes field, because the inner classes field has got a different name now, var3, and that's why we can actually print it out without having to put a this prefix or anything like that. Let's fix that up there, but also here in the ×2 method we don't need to put a this prefix because it's actually a different name now. So what this confirms is that the object scope is the block in which it's declared, including any contained blocks. So looking at var2, and of course var2 is here. So looking at var2, that's defined in the times2 method for scope check. So that includes the for loop, and var2 is also in scope with that as well, as you can see there, because it's defined above and it'll work within the next set of blocks, the enclosing blocks, if you will. var3, which was a field in our inner class, which is the inner class to scope check. That's in scope anywhere within the inner class, and we've got it printed in the constructor, as you can see, var3 there, and also multiplied in the times2 method as well, down here as well. So it's still on those two places. And finally, going back to main, var4, the scope for that's anywhere inside the main class and the main method, because it's a local variable for the main method. So it's worth noting here that at no time did any of our other private var variables shadow the one in main, so because that's a different class essentially. So a variable can only shadow one with the same name if it's declared in an enclosed block. So that brings us to the next topic, which is visibility. So in Java, an object's visibility is governed by the access modifiers, and we'll be discussing those in detail shortly. But the thing to point out is that visibility is connected to scope, and we need to look at that aspect of it first before covering the access modifiers themselves and how they actually relate to access control. So getting back to our scope check, if we look at the inner class down the bottom, starting at line 25, we've printed out the var1 variable despite the fact that it was declared as private in inner class. Now an inner class has got access to all the member variables or fields of its containing class, so not only is var1 in scope within the inner class, it's also visible. So the same is true the other way around. So the containing class can also access all the methods and fields of a contained class, even if they're marked as private. So we can actually check that, but what we can do is we can create a method in scope check to instantiate its inner class and print the var3 variable. So I'm going to go here, making sure I'm actually within scope check. So I'm not in the inner class at all. And I'm going to create a method called public void use inner. And within there, I'm going to type inner class, noting how IntelliJ can see that. Inner class equals new inner class. Then I can do system.out to print var3 from outer class plus inner class dot var3. So now we've created the use inner, what we want to do is go back to the main method and actually call that method that use inner method. So up here below the various printouts, I'm going to actually put scope instance dot use inner just to actually make sure that it works. I'm going to run that. var3 from outer class 3, so you can see it's actually working fine there. But now if I actually go back to scope check, I can change this to a private, run it again, and the code still works. So notice that the scope of var3 hasn't extended to the outer class. So we actually had to qualify its name with the class instance in order to print it out. So inner class dot var3, as you can see there. But the visibility does extend to the into the outer class. But with that said, the variable itself can't be accessed from any class external to scope check, and we can actually check that ourselves by going back to main and seeing if we can access it. So I'm going to comment out some of these other lines for now. Okay, so after that then, if we actually set up here and type scope check dot inner class equals scope instance dot new inner class, and try and print out var3 is not accessible here. Inner class dot var3, noticing how IntelliJ can't actually find the variable. Now the reason we can't do that and we can't run it and we actually get an error is because var3's got private access and therefore has no visibility outside its class or a containing class of its class. So in other words, from scope check or scope check.inner class. But if we went back and actually changed this, change that so it was a public, notice that the error disappeared from the red disappeared from under main.java, and the error actually goes away because we've now given visibility for that variable basically as a public to any other class. So I'm just going to undo that change. So back to a private again. So this concept now is moving away from scope and into visibility and access. But var1 and var3's visibility within scope check is related to the scope of the variables, and I think it's important to discuss that before we move on to access modifiers sort of properly. In particular, the fact that both var1 and var3 are declared private, as you can see on the screen there, private on line 8 and also on line 31, but both can be accessed from both the outer and inner classes, can actually be surprising when you're starting Java. So finally, when we look at inheritance, we often actually had a subclass override a method from the superclass. In other words, the class that it was extending. So the mechanism for this is very similar into variable scope that we've discussed. So Java will look for a method in that case in the current class and use that if it finds it. Otherwise, it's going to look for it in the immediate superclass and so on up the chain until it finds a class that actually has the method. But with that said, it's not actually correct to say that the overriding method shadows the one in the superclass. Override is actually the correct term here, not shadow. If, though, the method was static, then it can be shadowed, not overridden. But for now, don't worry about that until we get to the lecture on the static keyword, because we want to talk about that separately. So time is ticking on. I'm going to actually leave the challenge to the next video. So the next video, we'll go through a challenge for the various things that we've learned in this video and the previous one. So I'll see you in the next video. So in the previous few videos, we talked about scope and also about visibility in Java. So now it's actually time for a challenge. So I'm going to paste the challenge in here, then we'll just discuss it, and then you can make a start on that. Now, just before we start talking about the challenge and going into the details of it, I want to make something really clear here. This is not good coding technique. What I've attempted to do here with this challenge is to help teach you scope. So by going through the challenge and completing it, I believe you'll come up with a firm understanding, a much better understanding of what scope is and how it actually works. But going through the challenge and doing things like I'm telling you to do, creating variables of the same name with the letter X and a class with the same name also with the letter X would be very bad programming practice, and you would never do that in a production environment. I just wanted to make this really clear that the challenge is designed to help you understand scope. Do not assume that the coding standards here are standards that you would use with the short variable names, in this case with the letter X, that they're, again, purely to help you understand scope. All right, so let's get back to discussing what the challenge is. So here's the challenge. It's to write a small program to read an integer from the keyboard using scanner. And of course, we've used that many times in the course today. And also to print out the times table for that number, whatever the number was entered from the keyboard. And the table should run from 1 to 12. Now, you're allowed to use one variable called scanner for your scanner instance. And you can use as many other variables as you need, but they must all be called X. So that includes any class instances and loop control variables that you may decide to use. Now, if you use a class, the class can be called or should be called X with a capital, but any instances of it must be called X with a lowercase. So any methods you create must also be called X. And it's an optional extra. Change your program so that all variables, including the scanner instance, are called X. So what we're trying to do here is learn what scope is and to use the appropriate scope to make this happen. So by actually having you go through calling everything X, you're going to really have to understand where to use things and where the scope is appropriate for you to be able to do that. So that's the challenge. Now's the time to pause this video and go away and have a go and see if you can come up with a solution to that. And so when you're ready to see my solution, come back and we'll go through that. Okay, so how did you get on? Did you figure it out? So let's go ahead now and implement the solution. So the first thing we're going to do is we're going to create a class. And I mentioned there that if you use a class, the class can be called X. So we need that. So we're going to create that. So I'm going to go into our package, right click, new class, X with a capital X. And we're going to create a field, int X, the private. We're going to create a constructor, which is going to accept that parameter, then update the field we're using this. So this.x equals X, as you can see there. We're going to create our function, which actually does the times table. And it's going to be public void X for int X equals 1, X less than 13, X plus plus And we'll print out x plus times plus this dot x plus equals plus x times this dot x. And what we need to do is go back to our main class now and actually call this. So we're going to go back to main, and actually first things first, we're going to input from the keyboard, the actual number that we're going to process. So scanner equals new scanner system.in. And then we're going to print out a message, please enter a number. And x equals new x scanner dot next int and x.x. So if we run that just to confirm that it's actually going to work, number we'll try 2, and we can see we've got 2 work from 1 to 12, and that's working fine. So you can see what we've done there. We've used X everywhere, but we've managed to, by using the appropriate scope, to get the program to work without it actually coming up with a problem with the X being considered like a duplicate. And of course, the way we've done that is in the X class, we created a field. We've got a constructor that accepts the parameter, then updates the field. Then in the method X, we're using the integer X for the for loop, but we're using this .x instead of obviously the X for the for loop to get it to work. Now, as the optional extra, change the program so that all variables, including the scanner instance, are called X. And the way we can do that is we can go back here to our X class, and instead of just having this .x equals X and having a parameter, we'll change this. So we'll actually pass a parameter of scanner, and we'll accept that import. And then we'll actually put a message here, please enter a number. And we're going to accept the input. This .x equals x dot next int, like so. So now if we go back to main, we can change this a little bit. And we can copy this new part because we're going to need that. Delete out those first 2 parts. Then x equals new x, and this time it's going to be new scanner.system.in, like so, then just x.x. So now we've literally got everything using X. And if we run that again, confirming that it works fine. So I know it's a contrived example, and it's something it's certainly not a way you'd normally code, because it's very hard to read with all the variables and even the methods and the class being called X. But the point is, by understanding scope and visibility, we're actually able to achieve our goal of doing that. So I hope that's actually helped, and I hope you did well in the challenge, and we'll see you in the next section. Okay, so it's time to start talking about access modifiers, and in particular private, public and protected, as well as package private. So what we're going to do is now, to see why you'd want to restrict access to the fields and methods in your classes, what we're going to do is implement a very simple and, frankly, seriously flawed bank account to demonstrate that. And just before I go on, in case you're wondering about the color scheme, you've probably noticed, if you've been following along, the last few videos have been looked a little bit weird with some of the buttons and so forth not fitting. There's currently an issue with IntelliJ 15 when you're trying to size up fonts, and for some reason when I select Darkular, which is the dark theme, it doesn't happen. So I'm just going to leave it in this mode now. Let me know what you think of this. And I find it better to work in this mode, but generally the white background's better for videos, but we'll see how we go with this anyway. Okay, so first thing we want to do is create a class. We're going to create a class called account. So I'm just going to do what we normally do. Select the package and create a new class, call it account. Okay, so that class is going to have firstly a string, private string, account name. It's also going to have a balance. Actually, what we're going to do, we'll change that to a public. Because we were talking about access modifiers, it's important to understand this. So we'll also make the balance 0, that's also a public. And public array list array list integer for transactions. And transactions on the account. We're going to create a constructor, and the constructor will accept account name. So we set the field account name to whatever's passed, and we also initialize the transactions. So this dot transactions equals new array list integer. So it's just creating an empty array list ready for us to start adding records. And we also need a getter for the balance. So getter balance. So that's our base accounts class. And just to confirm the transactions, very, very basic. What we're going to do is store the amounts as a positive number where it's a deposit and a negative number for withdrawal, and put those in the array list. Okay, so next what we need is some methods to support deposits and withdrawals. So what we're going to do is implement those, and then we're going to get the account class to calculate the balance as well. So firstly, the deposit, public void deposit, and pass a parameter of the amount we want to deposit. We check if the amount's greater than 0, and if it is, we're going to add that, transactions.add amount, and we also want to add that to the balance. So the balance gets incremented by the amount that was passed to this method, and we'll put a message to the effect to say amount deposited, balance is now plus this dot balance. Else, what we're going to do is, if it wasn't greater than 0, we'll print out a message just to say cannot deposit negative sums. Okay, so that's our very basic deposit method. So let's now write the withdrawal one. Similar, but obviously the money is coming out or being deducted from the balance. So public void withdraw, pass an amount as well. Int withdrawal equals minus amount. So we're converting it to a minus, remember, because a negative number we're going to assume is a withdrawal. And we'll put if withdrawal is less than 0, this dot transactions dot add withdrawal, this dot balance equals, we're adding withdrawal, remembering it's going to be a minus number, so we can still use the plus there. And we can say amount withdrawn, balance is now plus this dot balance. Else, message, cannot withdraw negative sums. So that's our basic withdrawal method. Again, it's checking, converting it to a minus because we're going to pass a positive amount, and then we're setting it to a minus amount, and then we're checking to see if it's less than 0, which means we can withdraw. We're going to add that to the transactions, bearing in mind a negative number we're considering to be withdrawal. We're adding the balance, or adding withdrawal, I should say, to the balance, but bearing in mind it's going to be a minus number, we can still do that and give a reflected updated balance, and then updating how much is what the current balance is after the withdrawal, and we're just showing an error message if there was a problem. So next, the last method we're going to create here is going to be calculate balance. So public void calculate balance. So we start with a balance of 0, then we put for int I this dot transactions. So we're going to go through all the entries in our array list, and this dot balance, add to that, bearing in mind that will work for plus or minus numbers. And then we'll just print out a message to say calculated balance is plus this dot balance, like so. So that's our method there now for calculating the balance, where we start on 0 and we can go through and tally up all the transactions to come up with what the balance is after all of those. Okay, so to do some testing, we want to go back to our main class and then into our main method. And we'll start with account, and we'll call it Tim's account equals new account Tim. Let's do some do some transactions. So Tim's account dot deposit 1,000, Tim's account dot withdraw 500, Tim's account dot withdraw minus 200, Tim's account dot deposit minus 20. Some of these are obviously wrong. Tim's account. Oops, with a semicolon on the end there. Count dot calculate balance. And we'll print out a message. Balance on account. Account is plus Tim's account dot get balance. Very, very straightforward, as you can see there. Okay, just fix that typo up and we'll run this. And we can see that we started out 1,000 deposit, balance is now 1,000, 500 withdrawn, balance is now 50. When we get an error on the next line because we're trying to withdraw a negative sum and we can't deposit a negative sum either, as you can see there. So calculating the balance is 500, which is correct, and the balance on account using the getter is also 500. So everything works, and probably in a real application, the withdraw and deposit methods would also log somewhere to provide an audit trail of activity on the account. But notice that we've declared everything as public. This is the thing I wanted to point out. So going back to account, you can see everything's public, the account name, balance, and transactions. And what that means is this allows any program using the account class to modify the balance directly. And we can do that by inserting the following code into main. So under this line here, if I added another entry, Tim's account dot balance equal 5,000 and run that, we've now changed the account balance to balance on account is 5,000. Now that's obviously not good being able to do that, but the bank would spot the attempt at fraud by checking the transaction list, except we can also modify that as well. So we could do something like Tim's account dot transactions dot add 4,500, and then we could do Tim's account dot calculate balance again. So I could run that. We now have a match, you can see, of the account balance, but also there's now an entry in the transaction array list as well. So in a well-designed system, the transactions list, in this case the array list, should only be modified by the deposit and withdrawal methods. So by allowing access to the transactions list from outside the class, and the balance for that matter, we're introducing the potential for errors in the program, or in this case, for fraud. So obviously, here the fraud would be a deliberate act on the part of a programmer, but it's also the case that objects can be altered by mistake because the implications of doing so aren't apparent. In other words, the programmer didn't really understand the ramifications of what they're doing. The point is, if you expose fields of your classes, then anyone using the class will reasonably assume that they can manipulate the value of those fields. And because this bypasses the methods you've written to use those fields, as you can see in this case, your classes may no longer behave as you intended them to. So you actually lose control over that. So in other words, by making the account name, balance, and transaction fields public, what we've done is we've allowed them to be modified outside of the account class. And it's a simple fix. All we need to do is change them to public. So I come back here and change these to private. 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 So after we do that, when we go back to main, we actually now get errors, as you can see on the screen. So really the only way we can access those directly is by using, in this case, the deposit and the withdrawal methods, which means it's a lot more secure. So let's now have a look at the 4 access modifiers, and we'll discuss their effects, and then we'll produce some code to put these into practice. So access control is granted both at the top level or at the member level. So at the top level, what you can do is you can make your classes and interfaces public or package private. You can't define a private class at the top level, as we can see if we try. So let's try and do that. So I'll try and create a new class, and we'll call it private class. So I'll come along here and try and firstly add a constructor. That will work. But if I change this public to private, we'll get an error. Modify private is not allowed here, and that's telling us we can't have a private class at this level, at sort of the top level of this file. And let me just shoot over to the slide now while we just talk about this a little bit more, just to confirm what can happen at the top level. So basically at a top level, only classes, interfaces, and enums can exist at the top level. Everything else must be included within one of these. So public means that the object is visible to all classes everywhere. Whether they're in the same package or have imported the package containing the public class. But package private, what that means is the object is only available within its own package, and is visible to every class within the same package. So package private is specified by not specifying, if that makes sense. In other words, it's the default if you do not specify public. There's not actually a package private keyword as such. You just remove public and leave it as a class, and then you get package private for doing that. So moving on. And this is an example of a top level public class, as you can see on the screen there. So standard public class definition there, and with a public constructor. Top level public interface, very similar as you can see there. Again, the public keyword, the word interface, and then obviously the name of the interface in this case. Now a top level package private class, I mentioned that you remove the public identifier. You can see on line 3 there's no public there, it just says class. So that's how you define a package private class. And likewise for interface, package private interface, removing the word public again. Now at member level, this is once we're actually in the class itself, public, so using public at that level, at the member level, has the same meaning as the top level. So in other words, a public class member or field and public method can be accessed from any other class anywhere, even in a different package. And we saw that when we were using the main method to update the balance manually instead of going through the withdraw and deposit methods. Now package private, this also has the same meaning as it does at the top level. So an object with no access modifier is visible to every class within the same package, but not to classes in external packages. And lastly, private, and we saw that when we changed the fields in the example code, the object is only visible within the class it's declared in. It's not visible anywhere else, including in subclasses of its class. That's very important to know as well. Lastly, protected. The object is visible anywhere in its own package. It's sort of like package private, but also in subclasses, even if they're in another package. So that's why you'd want to use protected instead of private. Okay, so let's go back and look at doing some more coding now. So we've been using our access modifiers throughout this course, and I've briefly discussed the use of private in earlier lectures, but now you've got an almost complete definition of what they all mean. Now I said almost complete because there's one case that we've not specifically mentioned, although it was covered in the lecture on interfaces. That case is part of the solution to our mini challenge. So what we're going to do is I'm just going to delete this private class because we're not going to need that. And I'm going to create an interface. I'm going to new, call it a class, or select class, choose interface, and I'm going to call this accessible. I'm going to close the run window down. So what I'm going to do now is paste in some code. Now note I'm actually deleting this first part of the interface as well, so I'm going to paste it all in. Okay, so the challenge is in the following interface declaration, what's the visibility of 1, the accessible interface, 2, the int variable sum underscore constant, 3, method A, and 4, method B and method C. And what you might want to do is think back to the lecture on interfaces before answering this. So pause the video at this point, and when you come back, we'll go through and give you the answer to them all. Okay, how did you get on? Hopefully you figured it out. So firstly, let's talk about them. So number 1, the accessible interface. What's the visibility of that? Well, it's set to package private. So in other words, it's accessible to all classes, in this case in the com.timbachauka package, because that's what I've defined above. The second one, the int variable sum underscore constant. The visibility was set to public. And what that means is all interface variables are public static final. And again, that was the hint to go back and check the lecture on interfaces before answering. Method C, number 3, step 3, method A on line 19. What's the visibility of that? Well, it's just public. It's just a standard public, and we talked about that. And method B and method C are public because all interface methods are automatically public. So the lack of an access modifier here does not imply package private. So there's a little bit of a trick question there, and that's why I suggested you went back and check on interfaces. So with method B and method C, they're still public because this is an interface. So it's a little bit sneaky, sorry about that. But it's not possible to have anything except public methods in an interface. Now this does make sense if you think about it, because the whole point of declaring an interface is to provide methods that have to be implemented. So if you hide those methods, then any class implementing the interface will struggle to implement the hidden methods, which sort of defeats the whole purpose of using an interface. Now you can make the methods effectively package private by ensuring that the interface itself is package private, as we've done here. Now although all three methods are public, if the interface itself is not visible outside the current package, then those methods obviously won't be visible either. So that's it, you've now got the complete picture. The lack of an access modifier means the default of package private, except with interface methods and variables, which are always public. So that's it. I hope you got a lot out of this video, and I'll see you in the next one. So we've been using the static keyword when declaring variables and methods throughout this course. So it's now time to look at what static actually means and why we used it and why we had to use it in particular places. So what I've done is I've created a new class, as you can see here, and I've actually called the package static using our new naming conventions for packages, which we talked about earlier in this section. So let's go ahead now and create a new class. So we're going to create a new class. I'm going to come down here, as I normally do, down to source. I'm going to right click it, new Java class. We're going to call this static test. Like so. And what we're going to do, it's going to be a public class, and we're going to put a private int, which is going to be num instances. We'll set that equal to 0. Private string name. We're going to create a constructor, and we're going to use the name as the constructor. But what we're also going to do is every time the constructor is used, we're going to type num instances plus plus. So we're going to increment that variable num instances. And then also we need a getter for the two. So we want to put a getter for both num instances and for the name as well, like so. So that's it, very basic class. And so we'll go back now to main and create two instances of the class and print out the value. So we'll go back to there. And so let's start and type static test first instance equals new static test, and we'll call this one, unsurprisingly, first instance. Done original. So we'll print it out. We'll go first instance dot get name plus is instance number plus first instance dot get num instances. So, and then we'll do static test second instance equals new static test. It's going to be second instance, and print out second instance dot get name plus is instance number plus second instance dot get num instances. Like so. Now, if we run this, now you probably may have expected each instance to think it was instance number 1, as both have a copy of the number of instances field. So when we increment it to the constructor, it becomes 1 in each case, because of course we started with num instances equals 0. But a static field, which is also known as a class variable, is associated with the class rather than with any particular instance of it. So there's only ever one copy of the variable in memory. All instances of the class share that one class variable. So this means we can get the behavior we originally wanted, where this instance number was incremented every time we instantiated a new object from this class, by coming back here and changing the variable num instances to a static. So we make a static int num instances equals 0, and not changing any other code. We go back to main and we run that again. You can see now on the screen that we've got num instances number 1 for first instance, and instant number 2 is now for second instance. And just to confirm, we can also create a third one if we wanted to. Third instance. And third instance. Okay, so if we run that now, and we correctly get first instance is set to instance number 1, second to second, third to third. So it's still working. As you can see, we've got a single variable, a static variable, num instances, and only one version of that exists in memory at any time. Now you may or may not have noticed, if you're pretty sharp, that I didn't change this variable here, second instance, yet the program still worked. So why, with me leaving that to second instance when we're calling the third instance, did it still record, or return rather, the correct value? Well, the reason it returned it is because they're all sharing the same copy of num instances, so it doesn't matter which instance of the class we use to access a static field, it's always going to return what is then the valid number. So 1, 2, and 3 again. And likewise, I could have changed that to third instance, which would have been technically correct, and run that. And again, we still get the same numbers coming back, and that's because we're still only sharing one copy of that variable with all instances of the class. Now, it's a little bit odd that we can do that, and if you come across code like that, you probably have to stop and think for a while just to make sure it isn't a bug. It's really bad practice. I mean, leaving that error there is, I think it's really bad practice, and it's not something you'd really want to do. Even though it's perfectly valid, it's much better to use the class name and make it clear that what you're accessing is a static method or field. So in other words, changing this to what should have been third instance. Now, if you're using a method that only works on static fields, it makes far more sense to make that method also static. And that means that we can then access the method without having to use a classed instance to do so at all. So what we're going to do is we'll go back and change the class, the static test class, and we'll change get num instances to static. So we'll put static there. So it's now public static int get num instances, still returning the same variable num instances. But what that means is by doing that, we can go back to our main class, and instead of having this instance name, we can do something like this. We can put static test, static test, static test, like so. And it makes it clear now, because you're seeing that it's the class name, it's not using the instance name in your first instance, that this is a static method. And incidentally, you have used static methods before. When we use the integer.parseInt method from the interfaces challenge, for example, parseInt is a static method of the integer class, and as a result, we can use that without having a particular integer to call it from. So just as a recap, static methods and fields belong to the class, not to instances of the class, and as a result can be called by referencing the class name, as you see here, rather than a class instance. And this explains why the main method we've used throughout the course has to be static. This is written on line 5. Because when we want to run a Java program, there has to be an entry point. In other words, a method that's executed when the program runs. However, until the program runs, there's no classed instances to call methods on. So Java has to use a static method that can be called from the class name rather than from a class instance. So that's the reason, again, why the main method is marked as static. So when we run our sample program in IntelliJ, what IntelliJ does is it invokes a Java executable and passes to it the name of the class that contains the public static void main. So provided you've actually built the project, you can run the program from the command line by changing it into the project production directory and then typing something like, from a command line, you could type java com.company.static.main. So Java would then expect main to have a static method called main with the exact signature that we've been using throughout the course. Now the main method doesn't have to be a class called main. It can exist in any of our classes, but the convention is to put it in a class called main. Now if we're given a project containing hundreds of classes to work on, you would at least know where the program starts by looking for the main class rather than having to check every other one to find the main method, and that's why it's sort of a standard convention. So again, this example would be just running it from the command line. We're not going to do that now, but that's how you would invoke it if you wanted to do it from the command line. So now that we understand static methods and fields, and these are sometimes referred to as class methods and class variables, we can work out why all the methods we've created in main have also been static. So what we're going to do is use another example to discuss what's happening and why. So let's go ahead now and change this code. I'm going to comment this code out for now. And let's come down here and we'll put public int multiplier equals 7. Actually, we'll make that a field in this class. So I'll put this at the top, like so. And then we'll create a method called multiply. So public int multiply and it accepts a parameter of a number and returns the number times the multiplier. So this is a slightly contrived example that doesn't really do anything useful, but what it will do is help you to show what we can and can't do with static methods. So as you can see, the public method multiply takes a number and returns the result of multiplying it with the public multiplier field that we defined on line 5. Now we've made multiplier public so that there's no confusion stemming from its visibility. So let's call the method now in main here and see what 6 times 7 is. So we're going to do something like int answer equals multiply 6 and print out a message, the answer. Now in theory that code looks good, but IntelliJ is showing an error, and if we look at and we'll highlight the error, non-static method multiply int can't be referenced from a static context. And we get a similar error if we try and do something like this. Similar error, non-static field multiplier can't be referenced from a static context. So if multiply is public, then why can't we access it from our main method? Well, as we've seen, normal class fields require an instance of the class. They don't actually exist until an instance has been created. Now the main method is static, as we can see, and it can be called with a class instance. So as a result, Java can't allow a static method to access non-static fields or methods because, frankly, they don't exist when the static method's called. So in many of our examples in earlier lectures, what we did was we created methods for main to call, and in order for that to work, we had to make the method static. And we're going to do that here now so the program can actually work. So the way we would get around that, first we would make our variable, our field, static, and also down here, we can make our method static as well. So now that we've done that, we're calling a static method and accessing a static field, everything should work fine. And when we run it, we correctly get the answer 42, and we can see we're now able to access multiply because we've set it as static as well. Now note that the reverse is not true, and there's no reason why it should be. So there's no problem at all with a non-static constructor of the static test class back here. There's no problem with that accessing the static numinstances field, and we can also call static methods from non-static ones with no problems. Now note that there's nothing to prevent a static method from accessing non-static fields and methods in another class because it creates an instance of the class in order to do so. Now the restriction is purely on a static method accessing non-static methods and fields in its own class. So there's one more aspect of static that we need to look at, and that's static initializers. Now the discussion of these also need to consider final fields. So we'll come back to static initializers in the next lecture after we've discussed the final keyword. So we'll see you in that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
So another useful Java keyword is final. We use that generally to define constant values. So strictly speaking, final fields are not actually constants because they can be modified, but only once, and any modification must be performed before the class constructor finishes. So what that means is that we can assign a final field its value either when we first declare it or in the constructor. So as an example, we'll create a test class here. We'll just call it some class. So we can create a final variable here, and we can create the final field. So private final int instance number equals 1. So I can do it in there. Let's tidy that up a bit. We can also do it in the constructor like so. We could put something like instant number equals 1. Now both these examples obviously do the same thing. The field instance number is set to 1, and because it was marked final, its value can't be changed anywhere else in the class, or if we made it public from anywhere outside the class either. But in this case, it's usual to assign the value when declaring the field, but if you prefer, you can use a constructor instead. Now one reason why you might want or might need to initialize the variable in the constructor would be if its value is a result of some calculation, or perhaps relies on some other code, such as a method from another class. As an example, when reading a record from a database, you might want to store the class instance's unique database key, which wouldn't be available until you'd read the record from the database and were then ready to create the class instance from the database field. So we haven't created databases yet, so as a mechanism to show how this would work, what we'll do is we'll create a mechanism for ensuring that every instance of a class has a unique instance number or ID. What this will require is for us to track a variable each time a new class instance is created. So this is an ideal candidate for using a class variable, as we saw in the previous lecture. So what we'll do is we'll make instance number public to make it easy to demonstrate that it can't be changed, but normally when doing this you'd make it private. So I'm going to change this now, this public final int instance number. I'm going to remove the initialization, and as I mentioned, I'm going to change it to public. So what we'll also do is we'll have a static variable, call it class counter, set that equal to 0. We need a string for a name, so private final string name. So in our constructor, we're now going to accept a parameter, and that's just IntelliJ complaining that it may not have been initialized, but we'll fix that in our code shortly. So we'll use a parameter for the constructor. This dot name is equal to name, and now IntelliJ is happy on line 10. And we'll increment the class counter because we're instantiating a new version of this class, and we'll set instance number equal to class counter. Then what we'll do is we'll output name created instance is plus instance number. So that's our constructor, and we just want to put a getter there as well. So we're going to put a getter for our instance number, like so. So let's go back now to main and create some instances of this class. So we'll put some class 1 equals new, some class 1, some class 2 equals new, some class 2, and some class 3 equals new, some class 3. So if we run that, you can see, unlike in the discussion of static, where we had a getter for the static field and we always got the same value, whichever class instance we called it on, here we're actually storing the incremented static value in a class field. And so each instance of the class will maintain its own value for instance number, as we can see. So just to demonstrate that, what I mean is we can put one.getInstanceNumber, 2.getInstanceNumber, and 3.getInstanceNumber. So if we run that, and notice how they're all maintaining their own value for instance number now. So by making instance number final, the value, its value can't be changed once the class instance has been created. So attempting to do so will give an error and the code won't even compile. As an example, bearing in mind we set the instance number to a public, one.instanceNumber equal 4, we actually get an error immediately. Cannot assign a value to final variable instance number. So it's actually a good idea to mark variables as final whenever you know that the value shouldn't be changed once the initial value has been set, and a constant value would be an ideal candidate for that. That said though, now you may be used to seeing constant values in Java if you've done some coding before, declared using static final, and that's more normal for constants. So our instance number here, going back to the code, was not being treated as a constant because we did want to assign its value, but we only wanted to assign it once, and then we didn't want it to change after that point. And that's also why we didn't use uppercase for the variable name. If you remember from the discussion on naming conventions, constant variable names should be in uppercase. So why are constants declared a static final? Well, the reason is if the value really is a constant and won't change, then it doesn't make sense to store a copy of that in every single class instance. They'd all hold the same value, so it makes sense to store it only once at the class level. So hence values that are constant are usually declared using static final. Now we can see examples of this right throughout the Java framework. One example is in the math package. So if we go back to our main method, and I'll just comment out that error. we could do something like print out math using the Java math library.py. Notice pi in uppercase there. And if we just hover over that and have a look, public static final double pi, you can see there, and then it's obviously got the value of pi. So it's declared as a public static final double. So it's usual to assign the value of static field variables at the time they are declared, but again, they can be done afterwards in a similar manner to non-static final fields, and we'll see that shortly. First though, we'll stay with the math class because we want to have a look at another use of final. So what we'll do is we're going to just make a little bit of a change here to create an instance of math so we can do some sums. So we're going to type after that line, math m equals new math. Oh dear, unfortunately that doesn't work and we get the error, math has private access in java.lang.math, so we just hover over that. So if we right click on that now to go to the class declaration, you can see there's actually a comment above the code and it says don't let anyone instantiate this class. And so the reason we're getting that error is the constructor has been marked private, and that's to prevent, as you saw in our code, instances of it being created. And the reason they've done that in the math class is that all the math class methods are static, fields as well, and they're all available without requiring an instance. So to make that clear and to actually enforce it, the creators of this class, the math class, made the constructor private, and that prevents any instances from being created. Now, you might think I can get around that by creating a subclass of math, which I can instantiate. Unfortunately, or actually fortunately, creators have thought of this as well, and they stop you from wasting your time by declaring the math class up here as final. So by marking a class as final, applying that to a class, it prevents the class from being subclassed. So any attempt to extend math will fail because it's been marked final. So just to confirm that, try extends math, we're going to get an error. There's no default constructor available. And that's also got to do with the fact that it's currently only got a private constructor. So I'm just going to undo that. The bottom line is though anyway, by marking a class as final, you can prevent your class from being subclassed. Now it's possible that you might want to, or you might wish that a class you're creating to be extended or subclassed, but you might have one or more methods that are crucial to the correct operation of your class that you don't want just those to be overridden. So in that case, marking the methods as final will prevent them from being overridden, even if you do allow the class itself to be subclassed. So just to demonstrate that, I'll close down this math.java now, and we'll create a new class. We'll call it public. We'll call it password. I'll just close down the run window. So let's firstly create a static final int key. Key equals 748576362. Could be any number. Private final int encrypted password. We'll create a constructor and we'll pass the password in. But what we'll do is we'll also have an encrypt function. So the password would come in just as a password, unencrypted, and we would write a function to encrypt the password. So we'll write a generic function that would encrypt or decrypt, and then save it into the encrypted password, which is encrypted at that point. And we'll just do something really simple there with the encrypt decrypt. This is just an example. Private int encrypt decrypt, accepting a parameter of the password, and we'll just return password key like so. And that's using an XOR to XOR the values there. Okay, and then we'll store the password, so we need another one. We'll public void store password. Saving password as this dot encrypted password, encrypted password. And then we'll test in to confirm or to check whether the password is valid. So we're going to type public boolean let me in, which accepts the password as a parameter. Then we'll put if encrypt decrypt password is equal to the password on file. Then we'll print some sort of welcome message, welcome return true. Else, nope, you cannot come in. Return false. And that should be up there. I didn't change that. That should be just password. We're passing the unencrypted password to the encrypt decrypt method. So the encryption, as I mentioned, is a very basic XOR, which just checks the bits in the two values and returns a 1 in any position where there is a 1 in only one of the values. So if you apply the XOR operation to the result, you get back your original value. It does have applications in the field of cryptography, although used in a much more complex manner than what I've done there. So in main, we'll go back to main now, and I'll get rid of the other error. I'm going to create a new password instance and then call store password. So we're going to put password equals 674312. And we'll put password equals new password, PW. Then we'll put password.store password. So if we run that, saving password as 747992050, and of course that's completely different to the number that we passed to it. Now this is an example of why you'd want to prevent one of your methods from being overridden, not as an example of how to encrypt passwords for storing in a database. So cryptography is a very complex subject, and I would strongly advise you to use an existing cryptography library if you ever really needed to encrypt passwords or anything else for that matter. By all means, write your own cryptography library once you've completed a PhD in the subject, but until then, don't be tempted. Trust me on this one. So anyway, getting back to our example, the constructor, going back to our code. So the constructor takes a password and encrypts it, as you can see, and encrypts it, setting a field to store the encrypted value so that it can be checked when the user attempts to log in. So let's call the let me in method with a few passwords to check to see whether it's working. So going back down here, now main. So we stored the password, but now let's see if we can get in. So password dot let me in 1, password dot let me in 523266. And just to make this a bit easier for copying, we'll try another one. 9773. Try another one, maybe 0, -1. Then we'll do our correct one at the end, 674312. So if we run that, we should get an error on all of them other than the last one. Nope, you cannot come into the first 5, and then the last one, welcome. We're able to get in because we specified the right password. So you can see that worked, and the last example correctly logged us in. The first 5 entries, first 5 passwords we tried all failed. But the problem actually comes if someone overrides the stored password method in a subclass. So I'm going to end the video here, but in the next video we'll extend on from that and talk about the problems, and we'll actually create a new class that extends from this one and show you how to get around the issues that will come up. So see you in the next video. So continuing on from the last video when we're talking about final, we've created this base class, and we've created some base code to store a password and to encrypt it. So far so good, but the problem could exist if someone overrides the store password method in a subclass. So what could potentially happen, I'll just go back to that class. So as you can see in the store password method, we've got just a message saying saving password as this.encrypted password, and obviously encrypted password was encrypted when we call the encrypt decrypt, but we're actually just quoting that. We're just using the this.encrypted password variable. But what would prevent us for someone from extending this class and then changing that method itself? So to show you how to do that, I'm going to create a new class. I'm going to call it extended password. And what we're going to do with that is we're going to extend from password. And we're going to do something like private int decrypted password. And then we're going to create the constructor. And the constructor is going to, actually we'll select none from that. Then we'll add one manually. So int password, it's going to do a super password, but then we're going to do this.decrypted password equals password. Noting what I'm saving password and not the encrypted one. Then just to show that, we're going to override the store password method, and then instead of calling super, what we're going to do, which of course we can do in any method that we override, we're going to print out saving password as plus this dot decrypted password, like so. So you can see what we've done there, and we can then run that, going back to our main class. We'll just change the reference there from password, we'll make that extended password. Extended password. We'll leave all the same settings there other than that. And when we run it, then we get the same results as in all the options fail when we're trying to get access. So the let me in method still fails and then succeeds the last time. But the important point now is saving password as 674312, which of course was the original password that we passed to this method on line 18, as you can see there. So consequently, you can see how this has completely changed the security of the original password class, and it's compromised it effectively because we've now got a decrypted password that's potentially out in the wild. Now, this is where something like Finder would be really, really useful. We could just close down the run window. We go back to password, and all we'd need to do there is put a final on store password, so public final void password. And once we do that, if we have a look in extended password, suddenly we've got an error there, so you can see. And the error, if we highlight it, so looking at the error, cannot override stored password because method is final, overridden method is final. So you can see how it's very useful to selectively make some methods final in your classes if you know they're going to be overridden or there's a chance they're going to be overridden. And that's really also a reminder for you when you're looking at the code that you've made it final for a reason. And in this particular case with the method that would normally store the password, what we're saying is it's important that this is the final method and all our code for saving is going to be at that point, and we're not allowing that to be overridden. Now, so at the end of the previous lecture, I said that there's more than one aspect of static that we needed to look at, and we needed to understand final to do so. So now that we've looked at final, we want to look at the static equivalent of constructors. So we've obviously got a standard constructor that you've seen throughout the course quite a few times. But what I'm talking about now again is the static equivalent of those constructors, and they're called static initialization blocks. So constructors, as you probably know, because we've used them so much through this course, are instance constructors. So they're not static. So they'd be executed every time we create a new instance of a class. And we've seen that in operation, as I mentioned, countless times. Now, the static equivalent of that is a static initialization block, as I said. Now, the difference there is that block is only executed once when the class is first loaded into the project. So it's not often at all that you need to create a class constructor, which is sort of what a static initialization block is, even though that's not really the correct term for it. Now, the reason that I mention them is because a static final variable must be initialized by the time all static initialization blocks terminate. So in the same way that we can set the value of a final field in the constructor, we can also assign the value of a static final variable in the static initialization block. Now, just wanted to confirm that static initialization blocks are an advanced feature, and there's rarely a case for you to use them. So for an example, I'm not going to create a program that uses them in Anger. What we'll do is we'll just print out some text showing the program flow so you can see that when each part of the program is executed. So what I'll also do is assign a value to the static final variable using an initialization block, and we'll just see how this all works. So what I'm going to do first is just come back here to this class, and I'll just comment that out so we haven't got any errors in our code anymore. We're going to create a new class. We're going to call it SIB for static initialization block test. Okay, and we're going to do a public static final string, and we'll call that owner. Now we're going to type this weird syntax that you probably haven't seen before. Static owner equals Tim. We're going to print out SIB test static initialization block called, like so. And we can also create a constructor, and that's going to be, SIB constructor called. And down here, static, I'll put 2 equals there for some reason. Okay, and it's static. We'll print out second initialization block called, and public, we'll just create a method, call it some method, and we'll put some method called, like so. Now notice that the static initialization blocks are declared using the static keyword and followed by the actual code block, as you can see there. So there can be as many static initialization blocks as you like, and I've got 2 in this test class to show you. And they're called in the order they're declared in the class. So as you can see, I've put one before the constructor and one after it, but that's not really good practice because it could lead people to expect the constructor to be called before the second block, which isn't the case as I'm about to show you. So let's go back to main now. Let's just comment out this class, this other class code, which we don't need anymore. I'll uncomment the last line, the last brace, which we do need though. And so let's do write some code here. So we'll start with main method called. Then we'll do sob test equals new sob test test.submethod. Then we can put owner is plus sob test dot owner. You can see what we're doing there. So now if we run this, so I can see that the SOB static initialization block was called first, then the second initialization block was called, then the constructor was called, then some method was called, and then obviously the last line was the system.out SOB test.owner. The owner is Tim, output was actually called. So, and again, unsurprisingly, main was called first, but the interesting thing here is that both static initialization blocks were called before the constructor, and in fact they're called before any non-static methods, including the constructor, are called to be correct. And finally, you saw that when we checked that the string owner does have the expected value Tim, that was set in the initialization block on line 10, so you can see that that static code was executed. So although you've seen, again, static and final before in this course, I didn't really discuss what they meant in the past. So look out for their use now in all the subsequent examples as you work through the course. And now that you've been through this section, you'll have a much better idea of what they are, why they're used, and what the implications of using them actually are. So that's it. That's the end of the final videos. And it's also the end of this section. So we'll move on to a new section in the next video. So back in section 9, we looked at 3 of Java's list types. That was the list interface, the array list, and also the linked list classes. Now those form part of the Java collections framework, and that framework also includes things like sets, maps, trees, and queues. So at the top level of the collections framework is the collections class. Now this exposes static methods that either operate on collections, such as the sort method that we've used previously, or they also return collections objects, such as the list method. Now the interfaces in the collection framework, what they do is they allow the framework to be extended. And they actually define methods for all the fundamental operations that really are required for the various collection types. Now one of the design goals of the collections framework was that there should be good interoperability amongst various collections. So not just the ones included in the framework, but literally anything that may also be created in the future that is a reasonable representation of a collection. Now that also includes arrays. Now arrays themselves couldn't be made part of the collection framework without changing the Java language. However, the framework does include methods that enable collections to be moved into arrays and vice versa, and additionally methods to allow arrays to be viewed as collections. So the main components or the core elements of the collections framework are interfaces. Now these are the abstract types that represent collections, including the list interface that we've already seen as mentioned previously, and we will be looking at the interface hierarchy of the collections framework. Also included is aggregate operations. Now although we've seen iterators in earlier videos, we'll cover them in much more detail here in this section. In addition, another core element is implementations. Now this is the concrete implementations of the interface, including the array list and linked list classes. That's 2 good examples of an implementation. But also algorithms. Now the Java JDK provides a range of polymorphic algorithms that work on collections objects, technically speaking on objects that implement the collection interface, and they provide reusable functionality. So I'll be looking at all these elements in this section, although I'll do so by working with the framework rather than producing a video on each element. So to start with, what I'm going to do is review the array list and linked list objects as well as the list interface that we've covered previously, and consider them within the context of the collections framework. What I'll do is use a simple seat booking system in theatre to see how these classes that we've used earlier fit into the Java collections framework. So theatre seats will be numbered with a row letter and then a seat number within each row. I'll keep it simple and not have different numbers of seats in the stalls and that type of thing. So we're going to start off by creating our theatre class, and that's going to contain an inner seat class. So we're going to go over as always and go into our package, right click it, new class, and we'll call this first one theatre. And we're going to start by creating a list for the seats. So actually what we'll do first is we'll add the name. So it's going to be private, final, string, theatre name. Then we're going to create a private list of seat objects. So list, seat of seats. And seats we're going to define shortly. That's going to be an inner class. And make that a new array list. Like so. And incidentally, that error on the first line is going to go away once we initialize it. And if you were paying attention and watching the section, previous section where I talked about final and so forth, you'll understand why that error is coming up, and that it'll be fixed once we update our constructor. And we're getting this error here, most likely because this is weird. I think it's a bug in IntelliJ. For some reason, even though I've selected project structure or project language level 8 in my default settings, it's set it to 6. So if I go back now and change that to 8, the error should go away. And obviously we still need to define that inner class, which we'll be doing shortly. So moving on, let's create a constructor. So the constructor is going to consist of theatre. So once I do that, that should fix that other error. You can see that error's gone away now because we've now initialized that object. And we're going to have a couple of other parameters. Let's also have the number of rows in this theatre, int num rows, and int seats per row. And then what we're going to do is we're going to allocate, as I mentioned, there's going to be a seat number, consists of a row letter and a seat number. Well, theatre seats will be numbered with a row letter and a seat number, I should say. So first of all, we're going to create the last row. So we'll do int last row equals a plus num rows take 1. Then what we're going to do is cycle through and create a seat for each one of these theatre seats. So we're going to do for char row equals a row is less than or equal to last row plus plus. So it's going through all the rows from A to Z effectively. Okay, then for each, we've got the row, then for each row we now need to go through and allocate the seats for that section. So we need to put for int seat num starting on 1, because obviously we can't have a seat starting with 0. And the seat num needs to be less than or equal to seats per row, which again was passed to the constructor, and seat num plus plus to increment through each seat in the row. Then we're going to create a seat object row plus string format. So oops, lowercase row, the row that we've defined that we're currently processing plus string.format. That's going to be %o2d seat num. So we're formatting it so it looks correct. Seat num, and then we're going to add it to our array list that we've defined on line 10. So seats.add seat. There's a basic constructor, as you can see, that's created now. And before we fix this seat error up, we'll just create a few other things. What we'll do is we'll add a getter for our theatre name. So we're just adding the getter there, and actually I'll move that. Below the constructor is probably a better spot for that. Clean the code up a bit and put it there. And the next one we want, what we'll do is we'll create a few more. We'll create a reserve seat where it does just as you think it would. It reserves a particular seat for our theatre. And we'll also add a get seats where we can return or print out the list of seats. And we'll do the reserve seat first. And that's going to be public boolean reserve seat string seat number. Then we start off with seat requested seat is equal to null for seat in seats We're going to go through all the seats and we're going to do a test to see whether we can find our particular one. Seat.get seat number equals seat number requested seat equals seat, and then we'll break out of it because we've found the seat. Then outside of that loop we're going to put if requested seat is equal to null, we're going to put there is no seat number in case there's been an invalid seat sent to this method effectively. Return false in that situation because there's no other processing we can do because we've got an invalid seat. Otherwise what we're going to do is return requested seat dot reserve, and again we haven't written the seat class yet. That will all be revealed once we get to that. So that's how we go about reserving a seat. And then the last method we're going to, or next method we're going to create is the get seats, which is just really for testing purposes. And it's going to be public void get seats, and we're just going to go for seats, and print them out. So it'll be seat dot get seat number, like so. Okay, so that's the basic code for the theatre. What we'll do now is we'll add our private class, which has got some of these other functions, and we'll fix up a lot of these errors that are showing on the screen. So we're going to go ahead and do that. So private class seat, and it's going to have a private final string seat number, and we'll get an error until we initialize that. Private boolean reserved equals false. Obviously we want to indicate whether this particular seat has been reserved or not. So we'll do our constructor now, and we're just going to get the seat number passed to this method, and you can see we've now set that and fixed the error that was showing on line 53. That's all our constructor needs to do. And next we need to fix up some of these. Requested seat, that should be requested seat. So we need to basically we just need to import this error, and probably the easiest way of doing that would just be to put a star there. That fixes that. We could have done a Java util list and just imported it like that. That fixes that and fixes up some of these other ones. So we've still got the couple other things to fix here, just typos. We've got the get seat number method and the reserve method that still need to be written in this inner class. So I'll do that. First we'll do the reserve. So I'm going to do a public boolean reserve, and the code for that will be if not this.reserved equals true. So obviously if it's already reserved, we're not going to retry and process it, and if that's the case, we were able to reserve it, we're just going to put a message to the effect seat plus seat number plus reserved, and then return true. Our job is done in that case. If it gets down to here, well, actually what we'll do is we'll put an else in there. We'll put else return false, because obviously there was a problem reserving it because it was already reserved. We also want a cancel function. We haven't used that code yet, but we'll want that. So public boolean cancel, and it does things the other way around. It goes if this.reserved, so then it tries to cancel if at the seat number has already been reserved, or this particular seat has been reserved. So if this.reserved, then we put this.reserved is equal to false. So we're going to unreserve it, free it up so it can be allocated again. And reservation of seat plus seat number cancelled. Return true because we successfully cancelled. Else return false. We weren't able to cancel because the seat wasn't already reserved. Then the last one to fix up is this get seat number, which is just a getter. So we're just going to do a getter for the seat number. We should fix that. And that should be all the errors that are now fixed in this class, in our first theatre class with the inner class of being seat. And again, just as a recap, looking back up here, At the top, the constructor takes the theatre name together with the number of rows and the number of seats per row, and it uses these to create seats, which it currently stores, as you can see, in the array list on line 10, which is this, the seats field. And you can see that we've defined a couple of other methods as well, the reserve seat, and also we've created an inner class for seat and got the ability to reserve or cancel a particular seat. So let's go ahead now and create the main method, and that's just going to create a new theatre, then attempt to reserve the same seat twice just to confirm that things are working. So we'll go back to our main, and here we're going to create a new reference. So it's going to be theatre equals new theatre. We'll call it the Olympian. And again, the parameters here, you go back and just to confirm those, the parameters we're looking for here is the number of rows available in the theatre and then the seats per row. So we're going to start with 8 rows and 12 seats per row. Then we'll do a theatre.getSeats. We'll call that method just to print it out to see that it's working. So let's try running that first. And you can see that we've got our various seats there, starting from row A, A01 to 012, and we use that formatting class, which I mentioned here, strings.format, to make sure they're all allocated with a leading 0 if necessary. And we've gone from row A to row H. And of course, that's a total of 8 rows. So that part's working okay, which is good. So let's go back to our main. So let's now try doing a reservation. So if we put something like, if theatre dot reserve seat H11, please pay. The seat's been reserved. Else, sorry, seat is already, or seat is taken. So the first time we run this, this should work. We run this. Seat H11 reserved. So you can see that's working fine. There's an extra space there that I should probably look at fixing that. I think I must have added 2 spaces there, so I'll fix that. And go back and run it again just to confirm. Okay, seat H11 reserved. Now if we do try and do the same thing again, if I just copy and paste the same code, we should get an error the second time because of course the previous call to it should have reserved the seat. So let's just try running that. Sorry, seat is taken. So the first time it reserved it, and the second time you can see that the seat's taken. So that's good, that's working fine. And the other thing we'll do now is we'll comment out line 7 because we can confirm that the code's working all right and the seats are being created correctly. So I'll comment that out. So I'm going to pause the video now, and in the next video we'll continue on, and we're going to look at changing our data structure, which is defined in theatre.java on line 10, the seats using the array list. We're going to start changing that to a few different formats, the list, and then also look at changing it to a collection by making it more generic and seeing how that all works. So see you in that next video. So continuing on with collections with our theatre class. So looking at the top of it, up here we've set on line 10 private list seat, and we're using an array list. So we can easily now change that format to a linked list. Linked list, and the code would still work. We can still run that. And everything still works as it did before. You can see the first time it was reserved, the second time you need to pay because it's already been reserved. So clearly the implementation is still working. But we can be even more generic than that because we can change list to a collection. So we could do something like this. We can change the list there to collection. And that's really using just that. It's making it really generic by making it of type collection. So the advantage of doing that is that it enables us to use any of the collection classes to hold our seats. Now before we go ahead and do that, what I want you to do is have a look at this interface hierarchy of the collections framework. And the Java docs are pretty good here. So I'm going to take a copy of this link off the screen. Okay, so I'm just going to fire up a browser and we'll paste the link in. And the link will also be in the resources section. So you can see here this little diagram. It gives you a little good overview of the collections classes. So the interfaces set, list, queue, and dequeue all extend the collection interface. And there's also a sorted set, as you can see there, and that extends set. Now, incidentally, the framework also contains a separate hierarchy for maps, and I'll be discussing those later. So when we declare seats to be of type collection, we can implement the list of seats in a theatre using any concrete class that implements one of the interfaces that extend collection, as you can see on the screen there. Now, we've already used array list and linked list that implement the list interface previously, and we could also use a hash set or a linked hash set that implements set if we want to. And as it turns out, I'm going to use each in turn and verify that the program still runs. So let's try it first with a hash set. So I'm going to go back to my code. Now that we've set it as collection, we can change it over here from linked list to a hash set. Hash set, and we can go back and run this. Still works, as you can see there. We can get rid of the the commented out code. So in other words, we can see the seats and rows. You can see they're all still there. Noting they're now in a different order, but they are still there, and that's because we're using sets. But we can also go back and use the linked hash set. So linked hash set, as you can see there. We can run that. And notice how that returns in order this time. Now we're going to be looking at sets in more detail shortly, but at the moment, hopefully this should really demonstrate how array list and linked list fit into the collections framework, and that they can be replaced with other data structures if that structure provides benefit for a particular task. Now note, however, with that said, you must remain on the same level of the hierarchy. So going back to our little diagram. So although we can use any concrete class that implements set, list, queue, or dequeue, what we can't do is drop down a level and still expect things to work. So the collections framework also includes a tree set, which you don't see on the screen there, but that implements sorted set, so it's sort of one level down. But if we go ahead and try and use that, tree set, we try and run that, we actually get an error. And the error there is it's a class cast exception, and it's having trouble casting to the comparable because we're using tree set, which again is one level down. So tree set would be below sorted set. So any of these you can use, but you can't use the ones below that directly. So I'm just going to close that, or move this over a bit, close it down, and just undo that change. Go to a linked hash set. Now tree set, as it turns out, that we tried to use implement sorted set, and actually what it does, it's navigable set, which extends sorted set. And it's got an additional requirement that elements in it must contain or must be comparable. Then that's how the set is sorted. And because we didn't make the seat class comparable, that's why we got that class cast exception if we tried to add it to a tree set. Now, as we move down the hierarchy, the interfaces become more specialized, so we can only replace classes with other classes that implement one of the core collection interfaces at the same level. So the diagram that we've seen a few times is that we looked at, and I'll just go back to it again. And you can see below that it's actually got the text, a set is a special kind of collection, a sorted set is a special kind of set, and so on. And that's why we've got that issue with making sure things are at the same level when we're trying to replace and use them. Now, before we move on to look at what other classes are and why we might want to prefer to use one instead of our lists, let's talk about some of the remaining methods provided by the collections framework to work with lists. Now, although there's not really that many seats in our theatre, going back to our code, the reserved seat method isn't really efficient the way we've written it. To see how many seats it has to check in order to find H2, I'm going to make a little bit of a change here to print a full stop every time the loop goes around, and I'm going to do that on line 31. So I'm going to change that and to a print system out message, print a dot, and that's going to be a print instead of a print lin. So it's going to print a dot on the screen, so we'll know that how many seats it's had to check to find the relevant seat. And what we'll also do is we'll go back and change this to an array list, which is what we started with. So if we go back and run that, and the other thing I'll do is I'll comment out this get seats method again so we don't see all the seats on the screen. So if we run this, now you can see that there was a lot of dots there on the screen, a heck of a lot of dots before it found seat 11. So it's very inefficient the way it's been designed at the moment. And you can more or less say it's referred to as a brute force search in that it scans every element until it finds the one we want. Now, the collections class provides a binary search method that performs much better, so that as a result we can improve the reserved seat method and its performance. Now, in order to get that to work, we need to implement the comparable interface in our seats class, and that's so that Java knows how to compare two seats. So what we need to do is go back to theatre again, and we need to change our definition. We've got public class seat down here. Class seat, we want to change that to implements comparable comparable, and we're going to compare it on seat, of course, which is this object. And then what we need to do is add the comparable code so that, again, Java knows how to compare two seats. What we're going to do is just below here is we're going to override the compare to, and we need that, of course, so that the comparison will work. So we're going to override the compare to down here. Actually, it's an interface, so we're implementing it. So compare to, you can see as the parameter is the seat. I'm going to change it. It's got O to seat, so that makes more sense for us. And what we can do to figure out the comparison, it's actually a one-liner we can do here. Instead of returning 0, we're going to return this dot seat number dot compare to, ignore case, seat dot get seat number. So that's going to return the 0, number less than 0, a number 0 if they're equal, and of course a number greater than 0 if it's greater than. And we saw that before. We've used comparable, I know, previously in the course. So by doing it this way now, what we've got is a comparison that fulfills the interface, and it means that we can now be able to use a different type of set for our searching, which is a lot more efficient. So now that we've done this, it's now a lot more efficient. We've added a compare to, and we can start implementing this binary list, binary search I should say, and it's going to be a lot more efficient. And as you can see with the compare to method, we're really just using the compare to method that's built into the string class. And it's not really anything specialized other than that, but the important thing here is that the seat class could contain more than one field, and if that was the case, Java wouldn't have any idea which one would be used for the comparison. So if you did have a more complex class, and this is where you'd put your code in for testing that using the comparable interface, and then you then provide a compare to method that the framework can use, which we've done here now. So now that we've done that, if we go back up and check our reserve seat, we can change this a little bit now. So we can go back to the top. So the first bit is we're going to create a requested seat. So instead of making that null, that's going to be equal to new seat, because we're going to be using comparison now. Seat, and it's going to be seat number, the number that's passed off. So that's going to give us the object for comparison purposes. So, and what we want to do is change this completely. So I'm going to put int found seat equals collections dot binary search, and the search is going to be on seats, which is our list of seats, and on the seat that we want to search it against, which is the requested seat we've just created on line 29, and then we're passing null because we're going to use the inbuilt comparison operator there. So once we do that, we're going to get a number back. And the other thing I'll need to do to avoid this error here is we need to change this collection back to a list, because that's what we were working on initially. And that error should then go away. So that's going to use the comparable interface, and it's going to use the method that we implemented to check using the string compare to operator, or compare to ignore case method, to do the comparison for us. So then all we need to do after that is just check for a number that's greater than or equal to 0. So if found seat is greater than or equal to 0, return seats.get found seat dot reserve, and then we'll put an else in here, else there is no seat plus seat number, return false. Unless we've got all this extra code here now that we don't need, which I'll comment out. That's all been replaced now with the collections binary search, which is a lot more efficient. Now the reason that the binary search is more efficient, it's really the fastest way to find an item in a sorted list, and it works by checking the element in the midpoint of the list. So the method basically plays higher or lower with the list. So if the middle element is greater than the item we're looking for, then it knows the one we want must be in the first part of the list. So what it does then, it performs a binary search on that half of the list in the same way. So the list of elements is reduced to half each time. So as a result, it will take no more than 10 checks to find an item or decide it's not present. In a list of 1,024 elements, 2 to the power of 10 is 1,024. So over 1 million items, it's actually 1,048,576 can be checked in no more than 20 comparisons, and 64 comparisons are all that's required to search a list with an absolutely huge number. So 1.844 to 10 to the 19th element. So a number like this, in other words. So that would only take 64 comparisons. So it's blindingly fast compared to the brute force approach that we took earlier, where we were just going through each and every record. So you're not really going to be able to see too much in terms of performance. If we actually run this, just to confirm that it does work, you can see that it does certainly work as it did before. But what I'm going to do is paste some code in, which is the code from the actual binary search Java source code that comes with Java. And I'm going to paste that into our theater method. Now, we could go ahead and make a change to the Java source files, but that wouldn't be a good idea in this case because we'd be changing the official Java source code. So it's easier to just convert or just to copy the code in there. But it's really a useful exercise to see how that works. And one of the reasons we want to do that is so that we can see the full stop. We can put some full stops in to see the progress and how many times it takes compared to our previous attempt as to how many seats it needed to search for. Because obviously when we use collections.binary search, we haven't directly got a way of getting access to seeing that. But if we change the code, we can do it. So what we're going to do is copy and paste this code to replace our method, and then we'll be able to see it working in action. So I'm going to come here and I'll copy all this commented out code, or overwrite it I should say, so there's nothing there. I'll paste that in. This is the source code that is part of the binary search that comes with Java. So you can see what it's doing. It's and obviously it's been adapted for our particular purposes, but essentially all the code is exactly the same. So we're accepting a seat number, and you can see it's using the low-high approach. It's starting with the low is the number 0 and the high is the last element minus 1. And it's using this high element to determine the comparison, and it's sort of splitting it in half each two there, finding the midpoint as I talked about, and it's going through and returning the relevant comparison operator depending on the result. And I'll just fix that little error up there. So consequently now we should be able to run this and see how many dots it are printed compared to the last attempt of our code. So if we run that, you can see that in this case seat 11 was found in only, 6 dots, significantly faster than the last case. So let's try booking a few other things just to see the different results here. So we could try booking D12. That's probably going to give us one of the best cases. So if we try D12, and what I'll do is I'll just take this second part out now because we don't need that anymore. We want to just run to see how fast it is. So if we try that, obviously there was significantly, it was only the second time, it went through once, and then on the second time through it found D12, so it's much, much faster. H12 or B11 are two of the worst. And also to try one that doesn't exist, let's try something like, say, B13. If we run that, you can see that it didn't go through all the elements. It's still only, 1, 2, 3, 4, 5, 6, 7 iterations, including the last one, that there's no seat B13. So it's significantly faster than our other attempt at searching. Now, obviously, in this particular case, with only 96 seats in our theatre, it's not really an issue. But when you start talking thousands of records, using features like this, in this case, the binary search, which is part of the collections framework, makes a lot more sense. Now, the other thing I want to point out is going back to this code. Normally, we wouldn't copy the collection methods like this. We just call them like we did with the binary search earlier before I copy and pasted over it. But it's just really interesting to see how efficient the binary search algorithm is. And we did that by adding the dot to show us how many iterations it took to get to where we wanted to go to. And it's also good to know that we don't have to write our own versions of the algorithms that are included in the collections class. So I'm going to end the video here now. In the next video, we'll go on and talk some more about the binary search and how it works, and we'll move on to the next step. So I'll see you in the next video. So continuing on with our discussions of collections and specifically binary search. You saw in the last video we ended up with this binary search code that came straight out of the Java collections sort of source code. It comes with Java itself. So I just wanted to reinforce that it's interesting how this does work, and you saw how efficient it was when we put this little dot in there to see how many iterations were required compared to our version, and it was obviously significantly more efficient. So essentially the code, the algorithms in general that come with Java are very efficient. They've spent a lot of time on it. They've worked hard on it. And it's good to know as a result that we don't have to write our own versions of these algorithms that are included. Rather, we can take use of that functionality that's included. And just to recap, that a binary search relies on the list that we're searching being sorted. And we saw in an earlier lecture how to use the collections.sort method to sort a list, but that was providing the items in that list implement the comparable interface. Now we generated our seat numbers in a sorted order, so there's no need to sort it before performing the search, but with that said, the collections.sort method is available if needed. And interestingly enough, it uses a very efficient merge sort. This is the collection sort, and that performs much better than the bubble sort we used in an earlier challenge. Now, as we've already used the sort method, we're going to have a look at the reverse sort method that the collection class provides to sort a list in reverse order. Now, so that we don't mess up our seats list for our theatre, we have to really look at a way to use the lists or a lists constructor to copy one list into another. Now, the collections framework does provide a method to copy lists and other collections objects, but doesn't really work as you may expect. In fact, it'll only copy a list into an existing one of at least the same size. Now, we're going to demonstrate the problem after the next few examples. Now, so that we can look at these methods easily in the main method, what we're going to do is change the theatre class so that the seats field is public and the seat class itself is also public. So let's go and make that change. So I'm going to change this to public. So again, you wouldn't normally do this with a real program, but it's just going to make our testing of these concepts come through a bit easier. So I've made that public, and also our seats, we're going to create that and convert that, I should say, to public instead of it being private. So it's now an array list as well. So let's go back now to our main method, and we're just going to delete this content out for now. And let's add some code. So we're going to put for. Actually, what we'll do is we'll write the print list method first. So we're going to create a method that does just that, prints out the list. So it's going to be public static void print list, and list, and it's theatre.seat. We're going to accept the import for Java util list. That's going to be list, and then we'll have a simple for each loop. So theatre.seat list. I'm going to print out without a space plus seat dot get number, like so. Then we're going to print a line, go to the next line, and then we're going to also put some equal signs there to end the line, like so. So what we can now do is create a new array of seat objects, and if we pass in the existing seats from our theatre object, we're going to get a new list containing all the seats. So the way to do that is we're going to type list theatre.seat seat copy equals new array list, and then we do theatre.seats, and just to confirm that, we now do a print list seat copy. That should confirm that we've got a new list. So let's try running that to confirm it does work. And you can see that we've now successfully managed to get our copy, and we've got all our seats. I won't scroll right over to the right hand side, but clearly it's going to go through and list all the ones or the entries, the seats in our array list. So the seat copy list contains all the elements that were in the original. Now the method that we use to create seat copy and populate it in all the elements of theatre.seats is called a shallow copy. So what that does is creates an array list containing all the elements from the list that were passed to the constructor, as you can see on this line up here, on line 10. Now note, it's very important here to note that these aren't copied, hence the term shallow copy. Now if we modify one of the seats, say by reserving it, for example, then that seat will be reserved whichever list we check for it. So we may have a new list, but the contents are the same objects as exists in the theatre seat. So we're taking a copy, a shallow copy of the same data, if you will, and putting that into another array list, but they are effectively the same shared objects. And just to demonstrate that is the case, what we're going to do is we'll add a reservation after here. So we're going to, after the print, we'll do something like seat copy dot get, and we'll just get the second element from the array, dot reserve, and we'll just reserve that. And obviously that should be the second seat. AO1 is the first one, AO2 would be the second one. So we can then do if theatre dot reserve seat AO2, please pay for AO2, else seat already reserved. So you can see what we've done there. We've used our copy of the array list on line 13 to reserve the seat, the second entry in the array list, which should be seat A02, and then we're going back reserving the seat from the other array list, which ordinarily, if they were distinct and separate versions of the objects, that should also work. But let's just run it and confirm what happens. You can see it's come up and said seat already reserved. So clearly, the fact that even though we've got two separate array lists, it's very clear that we're sharing the same data, because otherwise, of course, the second reservation would also have worked on the other array list. This is an important concept which was also covered when we discussed linked lists, which was, of course, earlier in the course. So the two separate lists here, each containing references to the same 96 seat object. So that's the important thing there. Same separate references, but same objects effectively. So two separate array lists, but the references are to the same 96 seat objects that we initially created when we created the theatre object on line 9. And just to prove that they are separate lists, if you haven't already proved that with what we've done, let's sort one with reverse order and then print the other array list out and see what happens. So down here, we can do collections to reverse, and that reverses the order of any list. So we'll do that for the seat copy. And now if I print a message to say we're printing seat copy. We do print list seat copy. And then we'll do another one, printing theatre.seats, the other one. And for that one, we'll do print list theatre.seats. So clearly there's two separate array lists that we've got working there. So let's just run that and confirm what happens. And you can see here what's happened is we've got the seat copy, we've reversed that. And we can see now that the seat copy is in reverse order. We're starting from what was the last seat that we created is now in the first position, but theatre.seat has still got the original order that was set. So again, clearly they are separate array lists, and the only thing is that they refer to the same objects that were initially created on line 10. There's also a shuffle method in the collections class, and that shuffles the elements of the list in a random or sort of pseudo-random order. So we could go back and try that. We could close down the run window. Instead of reverse here, we can change that to shuffle. Shuffle. And if we run that, you can see we've got a seemingly random order there. G07, E02. Run that again. AF4, F08, F11. So that's a good way of pseudo randomization of a list using the shuffle method. A method that's part of the collections framework. Now there's obviously there's lots of other useful methods that form part of the collections class. A couple of other useful ones are min and max, and what they do is return the smallest and highest elements according to their natural sort order. In other words, the sort order that the compare to method maintains. So we could do something along those lines. Theatre.seat min seat equals collections.min seat copy. Then we could do theatre.seat max seat equals collections.max seat copy. We could print out a message then, min seat number is plus min seat dot get seat number, noting it's returning a seat. And the other one is max seat number is plus max seat dot get seat number. So if we run this code now, and predictably the minimum seat is A01, which was the first element, and H12 is the max, which of course is the last element in the sorted list. And obviously it's taking into account that's not necessarily the last element, it's the one with the highest sort order, and again it uses the compare to method to determine that sort order, basing the results on that natural order from the compare to method for a given list. And incidentally, these work even if the list hasn't been sorted, so we could go about changing that. So we could change the reference here to theatre.seat copy, and just running that again. So you can see that is still working, even though, as you saw with seat copy, it wasn't sorted, we used the shuffle method, but it's still going through that entire list and determining the minimum and the maximum based on the compare to sort order, because that, of course, will still work out the natural order. It's just that we haven't sorted the list at this time. We've used the shuffle method. So min and max will always work, which is pretty handy if you want to quickly find the minimum and the maximum elements using their natural sort order based on the compare to method. Now, if you want to implement your own sort, or for any other reason, the collections class provides a swap method to swap two elements in a list. So we pass the name of a list and the index position of the two elements that we want to swap, and what happens is the swap method swaps their positions in a list. So what we'll do is we'll create a variation on the bubble sort method from the arrays challenge, but this time we're going to use nested for loops, and the reason for that is that we had a student in the course ask if that was also acceptable. Now notice when we start typing this code, but actually I'll type it in first and we'll talk about it a little bit more. So let's just put the code in, we'll type the code in. So it's going to be public, static, void, sort list. It's going to be list, extends theatre, dot seat, list. Then we start with a for loop, for int I equals 0, I less than this dot size, I take 1, sorry, and I'll explain this shortly, I plus plus, and we put another loop. The next inner loop is going to be int j equals I plus 1, j less than list dot size, j plus plus, and then we put if list dot get I dot compare to, so we're using the compare to method to determine or to get a result in integer, but back depending whether the entries are less than, the same, or sort of greater than in the sort order. So compared to list dot get j, so we're comparing the two elements, and if the result of that is greater than 0, that means we can swap them. We want to swap them to be able to sort it. So it'll be collections dot swap. This is how we use that swap method list. Then we need to pass the two elements we want to swap and their element positions, which is I and j. Now, just to confirm what we've done there, and again, it's a variation of the bubble sort method that we wrote in the arrays challenge. But we're using nested for loops, and that's because we had a student ask whether that was also acceptable. I want you to first notice that the inner loop doesn't start at 0, but it actually starts after the current position that the outer loop has reached. So in other words, the inner loop is checking fewer and fewer elements each time around. Now it's still very much slower than the built-in merge sort, but this could be useful in situations where, for example, speed wasn't so important, but memory was at a premium. So merge sort requires far more memory than a bubble sort, and this could be an issue with extremely large lists. Even so, with that said, it'd probably be very rare that you want to use your own sort routine rather than the ones that are built into the collections framework. Now, like the print list method, which was the one on the method directly above it, starting on line 34, that had to access the get number seat getter and therefore only works on seat lists. What we've done on line 42 is we've made the method generic, the sort list method generic, so that it can sort any kind of list of theatre seats so long as they implement the comparable interface. And obviously that should be pretty familiar from the lectures on generics where we went through that concept in great detail. So to call this sort list method so that we can see swap in action, we're going to add some code now to our main method. And bearing in mind, we're going to sort the seat copy method. And if you recall, on line 21, we've shuffled it, so we know that it's out of order. But let's now try and sort it again. So we'll do a sort list, and it's going to be seat copy. Then we'll do a print out, printing, sorted seat copy, and print list, seat copy. So we've sorted it. We've sent the list to this method to line 46, and we're printing it out, the actual results, and they should then be ordered again. So let's go and run that and see. So you can see that on this line here, below printing copy at the top, they were out of order, but then down the bottom, printing sorted order, you can see clearly now they're actually sorted correctly. So our little mini sort method worked fine on it. I'm going to finish this video with a look at a rather odd copy method that's provided by the collections class. And what that does, it takes two parameters, the destination and the source list. Now the destination has to be of a generic type, that is a superset of the original of the source list, I should say, and that basically means it can be a collection, an iterable, or a list, and the source must be a list. Now, the problem that tends to arise with the collections copy method is that people either expect to use it as we just did when we used the list constructor to create our copy of our seats, and we did that all the way up here on line 11, or what happens, or people may expect to create a deep copy of a list. Now, as opposed to a shallow copy, a deep copy is a copy where the elements are not just references to the same elements as in the original list, but are themselves copied. And of course, that's unlike the shallow copy that we produced earlier, because we determined when we printed out the results that it was the same elements in the array list that were being effectively duplicated in the second array list. Now, the collections copy method is going to fail unless the destination is big enough to hold all the elements to be copied into it. So that actually leads to a problem. So it's pretty typical to see people try to do something like this. So knowing that you need to have the same amount of elements, people will actually type something like list theatre.seat new list equals new array list. And they'll do something like theatre.seats.size. And then collections.copy new list theatre.seats. So in theory, you'd look at that and think, it's very common for people to look at it and think, well, I've allocated the amount of size for the array list, so I should be able to run that. But what actually happens is you get an error. Source does not fit into destination. And the reason that's failed is the code on line 37, what that does, it only sets the capacity of the array list, giving it the potential to hold that many elements, but initially containing none. So it still doesn't actually create the number of elements. So to get this to work, get the copy to work, you actually need to have 96 seed objects in that new list, in that list that we created on line 37, before we can attempt the copy. So with that said, it's really hard to think of an actual use for the collections copy method, although it would allow all the elements of a list to be copied into another collections object, providing the object had been initialized with enough elements first, and I guess that's probably why it was included. Okay, so I'm going to finish the video here now because we've covered most of the collections methods that can be used on lists. So in the next video, what I'm going to do is take a look at the other collections types. So see you in that video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
Before we continue looking at the interfaces and classes in the collections framework, it's worth covering the comparable and comparator interfaces, or comparator interfaces. Now, the collections framework includes classes that sort their elements, so to really use those properly, we need to understand how that works in order to create our own classes that we can use or we can store in sorted collections. Now, in the previous videos, we implemented the comparable interface so that we could experiment with the collections.sort and reverse methods. So you've already seen how easy it is to create the one required method of the interface, which of course was the compare to method. So we'll continue using the theatre example because the seats give us a reasonably sized data set to play with. And secondly, because it's generated for us by the theatre's class constructor, so it's actually less typing. Now, we've left a lot of unnecessary code in there, though. So what we'll do is we'll start cleaning things up a little bit to make things a little bit tidier. And I have to say that I've been guilty of bad practice in the past. So we've made the seat collections object public. We talked about the reasons. I talked about the reasons why we did that in the previous video. And of course, that was because it's easier to see what we were dealing with, whether the actual seats collection without confusing things by having to get a getter, return the list of seats, etc. But that's really bad practice. So for the remaining examples, we'll set it back to private. We'll use a proper get seats method to do so. So we can go back to the theatre class now. And firstly, we're going to make sure that the seats variable is private. So down here, we're going to change, or up here, the public definition back to private. And we should still be using an array list, which we are. And the other thing we could do, if you remember, we copied and pasted the code from the Java sort method itself, from the collections framework. We're going to take it back and put back in our original binary search code again that we originally came up with, even though it wasn't terribly efficient. But we'll put that back in, replacing this code there. And what it did was I introduced another variable here, so consequently that constructor is not working. So what we're going to do is introduce a field called price, and we'll modify the constructor to allow that to work as well. So we're going to go down to our seat definition, and we'll make that a private as well. Remember, we set that to public in the previous video. So we're going to also add the variable for price, so private double price. Then we'll change the constructor as well. So the constructor accepts that as a parameter as well. So double price. Oops, wrong method. Of course, it's the constructor I was trying to do. So double price. And then we'll do this dot price equals price, like so. The other thing we're going to do is add that getter we talked about, the getter for the seats, because we haven't got that public anymore. So we'll do a getter. Now we've already got one, of course, because we called this get seats, which was for our testing. So what we'll do is we'll change this definition now. We'll change it to a collection seat. And then we're going to just return, instead of going through that loop, we'll do a return seats. Seats, like so. And down the bottom, we've also, this is of the inner class, the seat class, we've got a getter for seat number. Let's also add a getter for our price, which we've just added, like so. And I'll just clean that code up down the bottom a little bit, remove all those extra spaces now. Okay, so finally, let's go back and look at the theatre class again, which is the constructor, because we've got an error there, as you can see there. Now the constructor at the moment doesn't deal with price at all, so let's look at changing that. So what we're going to do is we've got the same code in there that does the generation. So the first bit of code here, we're going to charge a different price depending on what level. So we're going to set a price of $12 for the seats, but if the seats are near the middle of the first 3 rows, the price increases to $14, and seats in the back 2 rows or on the edges of the theatre, I should say, only cost $7. So let's go ahead and change that code. So we're going to go through our for loop like we've done there, but then we need to put a few tests in here. So we're going to start off with a price of 12, so double price equals $12, 12.00. Then we'll put an if test in there. So we'll put if row is less than D, and remember the first 3 rows, so that's A, B, and C, we're going to charge a separate price of 14 for. We're going to put and seat num is greater than or equal to 4, and seat num is less than or equal to 9. Less than or equal to 9. We're going to make price equals 14. So that's those first 3 rows, and obviously ignoring the 3 seats on the edges. If you're in those first 3 rows and you're not on the edges, then you're going to pay $14 because that's considered a premium sort of seat. And otherwise, if we're getting towards the back, so if row is greater than F, the F row, or the seat num is less than 4, so again we're on an edge, or seat num is greater than 9. So in those cases, you're going to get a discount. The price is going to be $7. And then what we need to do then is for our constructor, because we changed the constructor for seat, we need to add the price to it and pass that through, which ultimately is going to be saved in the seat object. So you can see what we've done there. What we've done is we've set the base price of $12 for the seats, as you can see that on line 18. But if a seat's near the middle of the first 3 rows, the price increases to 14, and you can see that we started doing that on line 20. However, seats in the back 2 rows or on the edges of the theatre only cost 7. So edges is defined as the first 3 seats, actually the first 3 seats on the left-hand side, remembering that they're numbered to 0, 1, 2, and the last 3 seats on the right-hand side. If that's the case, you pay only $7 for it. So now that we've done all that, we should be able to start experimenting with our changes. So what I'm going to do, we've got a lot of code in here. The main class does contain a lot from our earlier experimentation. So what I'm going to do is delete all but the initial reservations part, and then the print list method itself is going to stay there. Okay, so I'm going to delete the sort list, which we don't need. I'm also going to delete the some of this extra code up here. Really the only things we want to keep is the initial reservations. And we'll change this reference for the array list. We're not going to be using that anymore. And we're going to change this seat copy, because that doesn't exist anymore. Instead we're going to do theatre, or if. Actually, we'll delete that entire line, because the other code is actually already there. And I'll change that to private. I should really go back and change that, because we're going to still be using that print list to public again. That's the seat in a class. So I'll change that to a public, but not the seat objects or list of objects in the array list. That's still going to be private. So this one's going to be public, so we can access that class from main, like so. And just to be different, we'll do another seat number, D12. D12, and we'll put another one in there as well. And let's just do, say, B13. Confirm it's going to give us an error, B13. Okay, so that's our basic code now. So let's also now change the price. So for the print list method, what we'll do is we'll add a price in there. So at the moment we've got it printing the seat number. Let's also print out the price. We'll put plus, space, plus, and it will be seat.get price. So let's just run a couple of these scenarios and just check that the price is going to be correct. And I've got an extra bracket in there, probably from some of the code I was deleting, and I'll just clean it up a little bit. Okay, so we can just run that just to confirm that it's working. Please pay for D12, there's no seat B13. And obviously if we run this again, we copy that again. The second time we should come up and say that it's already reserved. Seat already reserved. So it's working back again how it should have worked in the past. And in terms of how it works, because the seat class itself implements comparable, we have to override the compare to method. And that's often a very simple thing to do. So a compare to method should return a number less than 0 if the object should sort less than the object that it's been compared to. And if we have a look back at our theta code, looking at the compare to method there on line 63, it's seat in our example, which was passed to this method. And then it should return a number greater than 0 if we should sort greater than the object that's been compared to. And of course, if the two objects are equal, the method needs to return 0. Now, because this is exactly what the string.compareTo function method does, and string.compareTo ignore case methods does as well, because that's just the same, but it's just ignoring the case in letters of the alphabet, we can use that to implement our comparison. Now, if you were creating a compare to method for a class that's got more than one key field, such as people's names, for example, where you probably want to sort first on surname and then on first name when people share the same surname, you just perform a test of surnames and return a negative or positive number as appropriate. Then if the surnames are equal, instead of returning 0, you then test the first name and return negative, 0 or positive, depending on how the first name is compared. So in other words, as long as the compare to method works as we've described, the objects implementing it can be sorted as we saw. And again, if we go back to our code, just to verify that, we can put list. It's going to be theta.seats, or seat I should say, reverse seats. New array list, our theta.get seats. Remember we did this previously. And then do collections.reverse seats. Then we were able to do a print list reverse seats. And by doing that, we can obviously see now, and I've got the pricing there as well, we can obviously see now that the sort is working. Because in this case, it's starting now from basically the opposite of the standard sort. We've done a reverse sort, starting at the highest element first and working down. So clearly what I'm saying is that the compare to method that's been implemented currently is working just fine. Now, with that said, there's also another way to use the sort method, and that's to pass it a comparator, or comparator, depending on how you pronounce it. So it's similar to a comparable. The comparator interface defines a single method called compare. Unlike comparable, the objects to be sorted don't have to implement comparator. Instead, an object of type comparator can be created with a compare method that can sort the objects we're interested in. In this case, it's seats, of course. And more than one comparator can be created, and it allows for objects to be sorted in different ways, which is pretty cool. So we can either create a comparator object within an existing class, or we could create a new class that implements the comparator interface. So let's have a go at the first way, using an anonymous inner class within Theta. So I'm going to go back to our Theta class, which we're already on, and just up here, right at the top, I'm going to add a static final comparator. It's going to be seat, and price underscore order is what we're going to call it, and equals new comparator. And you can see that's automatically come up and told us, or shown us which field we need to override. And what we're going to do is change the references there from O1 to S1. It's a little bit more readable. We know it's seat 1. Let's actually call it the fully thing that it should be. Seat 1, seat 2. And instead of returning 0, we need to actually add this to check a particular field. So what we're going to do in this one is we're going to check the price. So we want to sort, in other words, by the price of the tickets or the seats. So we're going to put if S1.getPrice is less than S2.getPrice, seat 2 I should say, and then we're going to return -1. Else if S1.getPrice is greater than S2 or seat 2.getPrice, we're going to return 1. Otherwise, of course, they're equal, so we're going to return 0. So that's how simple that compare method can be. Now, just to be clear what we're doing on line 12, it may look like we're instantiating the comparator interface, but remember from section 10 that it's an anonymous inner class implementing a comparator, and it's providing an implementation of the single compare method. And as you saw, the compare method itself is fairly straightforward. It has to return the same results as the compare to method does, as we previously discussed. In other words, negative if seat 1 is less than seat 2, 0 if they're equal, and of course positive if seat 1 is greater than seat 2. Now, with that said, note there's a serious problem with this method, and if you intend to use comparator, please make sure you finish this lecture first, because I'm going to be discussing the problem soon, because there is something major you need to be aware of. So to see this in action, what we'll need to do is create a new array list of seats. We need to add a couple of seats to the list, and then we need to sort in order of price with the cheapest seats first by passing our new comparator to the collections.sort method. So let's go and do that. So I'll go back to main and just down here. So what we'll do is we'll add a new list here, a new list of seats. So new list theatre.seat, and it's going to be, we'll call this one price seats, equals new array list, and it's going to be theatre.getSeats, which we've done before. So we've got a copy of our elements now. So what we're going to do is actually add a couple of seats. We're going to do price seats.add. You'll see why in a minute. Theatre.new seat. And remember the weird syntax to instantiate an inner class. B00. We'll call it 1300 for the price. And then price seats.add. Theatre.new, and again it's seat, using that weird inner class syntax to create a constructor, A00 and 13 as well. Next we'll do the sort. So we can do that by typing collections.sort, and it's going to be price seats, which is obviously the list we want to sort on, and it's going to be theatre.price order. So we're passing, and again, just to go back to make sure that it was clear, comparator as well, and that's our comparator now, which we created, which of course was price order. And now if we print the list after that, price seats, we can see what's happened. And just to make this a little bit clearer, the readability, I'll put a $sign there just so we know that that is a price. Let's now try running that. And we've actually got an error there. It was just a typo. I wasn't really paying attention, so we'll try that again. And obviously another problem here. And actually that should have been a semicolon, because we've got our comparator and needed to have a semicolon to finish off that definition. So third time lucky, we'll try running that again now. And you can see that's a little bit better now. And we'll just give ourselves a bit of space, looking at the last entry. Now the seats are listed in price order, and it's worth noting that the sort routine used is guaranteed to be stable. What that means is that the elements won't be swapped if they don't need to be, so that all seats with the same price appear in seat number order, and that's because that's how they were entered. Now the two new seats also appear in the original order, so B00 becomes before A00, because that's the order they were added to the list. So if we just go back and have a look, again this is in price order, so we need to go right to the end to see those entries. To the price of 13, and then you can see B, then A, 13. And again, B00 comes before A00 because that's the order they were added to in the list. So going back to the code, we added that entry first, line 36, B before A. And again, the way that this sort routine works, the elements aren't swapped if they don't need to be. So in this case, we're looking at the comparator was purely based on price. If we go back and check that out again, we're just doing a comparison just on price, which of course is why it's not looking at the seat number to determine any sort of sort criteria. And again, the way it works is if they are equal, the price was equal, they don't get moved. Of course, that helps performance by not moving things unless you really have to. So we've still got a lot to talk about. Now we can add as many comparators as we want, and so we could include one to list the highest price seats first, for argument's sake. So the comparator doesn't have to be static, but it makes it easy to use if we don't need a class instance in order to use it. And in this example, as you can see on line 38, we made the comparator a static variable of the theatre class, and that's because the theatre class is controlling all access to the seats. But thinking about it, it could have made more sense to include it in the seat class itself instead, especially if seat was not an inner class. But had we done that, there would have been no seat instance available in main to call on, so static would, for that reason, would be a lot more convenient. And just as a digression, before we look at the problem with our comparator's compare method, there's an interesting suggestion IntelliJ makes about the comparator. So clicking on its definition in the theatre class, IntelliJ will show you a suggested light bulb. So we go back and do that. So if we click the definition, you can see that IntelliJ is coming up with a couple of ideas. The one here that is interesting is split into declaration and initialization. So we'll go ahead and accept that suggestion just to see what happens. So I'm going to click on that, and you can see what's happened there. The declaration of price order becomes a standard static final declaration, but IntelliJ then inserts a static initialization block into the code that initializes the price order comparator. Now, we only recently discussed static initialization blocks, so it's quite good to see a practical use for it, as you can see this scenario here. Okay, so I'm going to end the video here. I was going to talk about the final issue with the compare method, but we'll leave that to the next video, given how long this video has gone for. So we'll see you in the next video. So just before we move forward and start talking about maps and the map interface and hash maps, I did allude to a potential problem that could come up when you're using the compare to function, or the compare method I should say. And I just want to go through that briefly before we actually move on, as I said, to the map issue. So if you actually go ahead and read the Java documentation on the collections framework, you'll find that there's a lot of talk about it, and they use words like and ordering being consistent with equals. That's sort of their phrase. And much of the discussion doesn't do a great deal to shed light on what that phrase actually means. And again, the phrase is and ordering being consistent with equals. But it really comes out to be quite simple. A method that produces ordering that is consistent with equals will only return 0 if the elements being compared actually are equal. Now, our compare to method behaves well in this respect. So looking at our compare to method, so our compare to method here behaves well in this respect, as you can see on the screen there. So if two seat objects have the same seat number, then they are the same seat effectively, and the string.compare to method will return 0, and that's quite correct. But looking at our comparator's compare method though, go back up to the top here. This is the compare method here I'm talking about. This is definitely not consistent with equals. So comparing any of the seats with the same price will return 0 when they are quite obviously not the same seat, because of course we can have multiple seats with the same price. So this causes problems with sorted sets and maps actually. If they're sorted using comparators such as ours, then that's inconsistent with equals. Now it actually turns out to be quite easy to fix. All you would need to do is do a further test on the seat number whenever the price is equal, just as I described for last and first names in the previous video. But I'm going to leave it as it is for now, so that we can see the problems that can arise with sorted sets and sorted maps later in this video. So the bottom line is you can't use the compare method as we've got here without more work using the price, because it's going to be more than one seat that would return an equals, returning a 0 because the price is the same. We need to break it down a little bit further. So anyway, let's move on now and start talking about the map interface. And again, you'll see an example of what I mean by this error a little bit later on. So right now we're going to leave the collections side of the Java collections framework for now, and we're going to have a look at the map interface and also some of the Java classes that implement it. Now the map interface is part of the collections framework, even though it's not a true collection as in the true sense of the word, as we've talked about in the various images and so forth in previous videos. And just to show you what I mean, let's just open a browser and paste in this link, which will also be available for you. So you can see obviously a map is out here on its own. It's not part of the collection exactly like a set, a list, a queue and a dequeue is. Now the map interface replaces the now obsolete dictionaries abstract class, and like the class that it replaces, it maps keys to values. So a language dictionary is a classic example of a map, with the keys being the words in the dictionaries and the values being, of course, the definitions of the words. Now unfortunately, the analogy falls down a bit with the English language, and the reason for that is many English words have the same meanings. So the word put, for example, has 4 definitions, 2 as a verb and 2 as a noun. Now a Java map cannot contain duplicate keys, and each key can only map to a single value. So in the next few lectures we're going to have a look at 2 of the Java classes that implement the map interface, and they are HashMap as well as linked HashMap, and as well as going and looking at TreeMap that implements the sorted map interface. Now maps, like all the core collection interfaces, are generic. They take 2 types, one for the key and one for the value. Now it is possible to use raw maps where the types aren't specified, but as we've seen in the lectures on generics, this isn't a good idea. So what I'm going to do is we're going to start with an example of using HashMap to store descriptions of a few computer languages. So I'm going to I'll go back to IntelliJ, and we're going to create a new class name. And notice I've still got the collections code open. So for now we're going to be using the same project, but we're just going to create a new file in here. So new Java class, and we're just going to call this map. And what we're going to do is we're going to add a public static void main so we can actually run our code. So we can do psvm and press tab, and that creates the definition for us automatically, as you can see on the screen there. So let's go ahead and type some code in now. So we're going to start with creating our map object. So it's going to be map. I'm using generics. It's going to be string for the key and string for the value. That's our definition. And we're getting an error there because I think I need to change my language level, but we'll see how we go. Languages equals new HashMap, like so. And just looking at the error. And okay, I see what the problem is here now. And what I was going to do was restart the video, but I think it might be a better idea just to show you, if you ever get into this scenario, how to get out of it. So what I've done there is I've used the name map to be the name of the class, and I'm trying to add a variable called map as well. So what we can do there to get out of that, well, there's 2 ways. Firstly, we could just refactor it. We could just click on that refactor, rename. That's probably going to be the quickest way to rename the class to get out of it. But the other thing we could also do is we could do something like java.util.map, and then we could put string languages equals new HashMap. We can do something like that, and that will actually fix the problem. So if you do run into a situation again where you've used a reserved word for a class name, this is a way to get around it by actually typing in the actual name, and by typing in the the complete declaration. If you happen to know what the package name is, you can fix that. But with that said, I'm going to change this anyway because it's just going to save a bit of typing. I'm going to refactor and rename. I'm going to call this map program. Press enter, and then I can actually remove this definition here. At this point, we can just delete that, and Java will then come up and say, oh, did you mean this import? Java.util, yes, that's the one. Okay, so moving on. So we've defined our map. We've just set with the 2 generic parameters there, string, that's the key and the value. So that's the types of the objects we're going to be using. And then to add something, we just do languages.put. And we could start with good old Java. And we could say something like a compiled, high level, object oriented, platform independent language, like so. Okay, and let's add a few more. So I'm going to do languages.put, and again the first parameter there is the key, so you can see if I leave that there. So, and the second is the value that we want associated with it. So we'll type Python for another one, and interpreted, object oriented, high level programming language with dynamic semantics. Okay, and languages.put algol and algorithmic language. Spell it be good, algorithmic language. And we'll do a couple more. The first language I ever used, basic. Yes, I'm not too proud to admit that. And of course that's beginners, all-purpose, symbolic, instruction code. That's what it basically stands for. And one more, let's do Lisp. And we'll say Lisp. And let's say therein lies madness. Okay, so that's our languages. And that's now stored, each one of those references, a key and value pair into the map object. And I made a typo there, let's just fix that up as well. So how do we get access to those? How do we retrieve them? Well, we obviously inserted them using the put. We retrieve them using a get. So we could type in something like languages.get, and we type in our key. So let's start with Java. And if we run that, I need to right click this first and run it so that we run the new program. So it will give us an option up here to run it. So I'm going to run that first. And you can see that we've got a compiled high-level object-oriented platform-independent language, which was clearly the setting, the value, I should say, that we defined for Java. So that's good. And obviously, if you wanted to get access to the other ones, you'd have to do the same thing. You'd specify that as the key, and by default, .get returns the value associated with that key. So that's good. But one important feature of maps is that the keys are unique. So in other words, if you try and use a value again, what happens is the new value gets overwritten. Now you don't get an error, but the old value, I should say, gets rewritten or sort of overwritten, I should say. So we could do something like this. We can put languages.put. Let's put Java again. Java. And put this course is about Java. And now if we reprint that again after doing that change, if we run that, you can see what happened there. We didn't get an error, didn't come up and sort of say already exists or anything, but clearly what's happened is it's overwritten the value. So that's the important thing to remember, is that for a particular key there can only be one value, and if you try and insert more than once using the put more than once, then the value gets overwritten. Now the put method itself can be used to tell if a value is being added for the first time, and it can be useful in certain circumstances to know that, and the reason for that, it returns the previous value if there was one. So we can change these lines here to show you what I mean. Let's change these two here, and instead of just putting the language.put, we'll put a system.out there. We'll surround that in that, like that. We'll do the same for the Lisp as well. So we're now surrounding that in brackets, and if we just comment out these briefly and run this again, now you can see we've got the answer, the return object was null for both cases, and what that essentially means is that this was a brand new reference, so a brand new key value pair that was added to the dictionary. But again, if we now uncomment this again and run this again, and actually what I should have done is also, what I'll do is I'll comment these out. We don't need to know that. That's just a printout. But what I wanted to show you was this line here. So system out, we'll print out results of running that. You should find that because we've already added Java the first time on line 13, when we do it again on line 20, we should get a different response. So we run this, and you can see what happens there with that printout. We actually get the version, the value that already existed prior to this being added. So the line still gets processed. So on line 20, language.put, if we actually leave this line out so we can print it, we will find, of course, that the value has been changed. So it's changed, as you can see there, but it has returned what the previous value was. So that's just a way for you to determine whether, if you need to know that a value is being added for the first time, that's how you go about doing it. So that's obviously helpful to tell you what the previous value was, but it didn't prevent you from adding it. In other words, it still got added whether or not you wanted it to or not. So if you do want to determine and then pragmatically only add a key if it's not already there, we can do that as well. The way we'd go around about that is we can use the contains key method to check to see whether it exists. So we could do something like this. I'll just delete that line now. And up here we can put something like if languages dot contains key Java. I can print Java is already in the map. Else, and that's there where we could put something like our languages.put in there again and fix it up like that. So that would be a way to pragmatically ensure that you're only adding an item once, and it's never going to be overwritten by adding it a second time. And just to check that that works when we run it, Java is already in the map. It's come up successfully and told us that. And just to be really 100% sure, we could also put something here. If languages.contains key Java. Java already exists. Else. And we can just put the Java line in there. And obviously it's pretty clear that that should return the normal message, the else here, because we've just created the map on line 12. But just to confirm that it does work anyway. And I didn't put a message there, did I? So I need to actually put a message there to say Java added successfully. Because of course we added the code there on line 16 to add it, but we didn't put any message on the screen. So we run that again. Java added successfully. We've got the two nulls which are relating to basic and Lisp, and then we've got Java is already in the map down the bottom on the line that's on line 25. So that's how you go about doing that. Now there's also another command, another method called put if absent, and that's only going to add to the map if the key is not already present. But that's really intended to prevent concurrency issues so that one thread does not add to the map only for that entry to be overwritten by another thread. So it doesn't help in the null case because it will happily overwrite keys with null values. Now the other thing we can do is we can also remove items from the map, but before doing that it would be really useful to print out our map's contents so that we can check that items are gone when we remove them. Now one way to do that is to loop through all the keys in the map using the key set method, and that returns a set of all the keys. And we're going to be covering sets in detail later in this section. So all we're going to be doing here in this code I'm about to write is looping through the contents of the set of keys. So what I'm going to do is just add some code, and we're just going to go right down to here, and we're going to print out there, and let's just add some equal signs just to separate our code, like so. And let's go and use the key set method. So to access that, to print out all our keys and the values, we can put for string key. That's languages dot, and it's key set. And that, you can see that returns a set there. Again, we'll be talking about those, what sets are and how to use them in this section. And then we can do something like print out key plus colon there to separate it. And then we just do a languages.get and we pass the key. And that's going to loop through the map and return all the values. So let's just run that to confirm that it does work. And you can see we got through and they all work fine. And just in case you're wondering, with the code down here on line 25, we didn't actually redo Java. So Java has only been added once, and that's why we've got that result there showing the original interpretation of Java, because we've added some code to pragmatically check to see whether Java exists, and then we only printed a message. We didn't actually update it. So that's why that's still showing the original one. But as you can see, that's gone right through the list of objects, printing out the key and also the associated values. Now, if you looked at that, you'll notice that there's no specific order there. Obviously, the order doesn't relate really to how we've entered them for the first time, because we started off with Java, which it still does in this case, but basic obviously wasn't at the top of the list, it was towards the bottom. And basically it's just like there's no guaranteed ordering, I guess is what I'm saying with a hash map. So the keys haven't appeared either in the order we added them, nor in alphabetical order. And that's the thing to point out with that default hash map, is that you can't presume that the records are going to be returned to you, or the objects are going to be returned to you in the correct order. So I'm going to finish this video here. In the next video, we're going to continue on. We're going to talk about ways to remove items from maps and look at some other bits and pieces relating to getting the most out of maps. So see you in that next video. So continuing on with our discussion about using maps. So what we're going to do now is use the remove method to remove a specific key from a map. And to use it, it's probably, as you're thinking now, the way to remove it is logical. There's actually two ways of doing it. So the first way we can do it is we can do something like, and what we'll do is we'll leave the printout down the bottom there so we can confirm that our changes have actually worked. So down here we can put languages.remove. We can put Lisp, and that's going to remove that. That's going to remove the Lisp entry. But we can also do something else. We can remove a key only if it's mapped to a certain value. So for example, we could do something like this. We can put if languages.remove our goal, and put a family of algorithmic languages. Argyle removed. What's the typo there? I can put something like else. Argyle not removed. Key value pair not found. So if we now run this code again, so we can see now from our list, first we got this message that Argyle not removed, key value pair not found, but you can see that Lisp has been successfully removed. So just confirming again that on line 34, we're checking to see whether Argyle, the key Argyle, and also the value of a family of algorithmic languages was there and only removed it under those circumstances. And obviously on line 21, when we define it, we didn't actually define it like that. And as a result, it didn't remove it for that reason. Now, the other thing to note is that the remove method does return true or false. So it's good to know if you do want to check that something was removed, you could actually put an if then and just check for true or false to indicate if the key existed in the map and it was removed. And you can see that that on line 34, because we used that functionality because we did an if language.remove and passed the parameter, and obviously that returned true, and then we're able to use that in our if then else. And just to confirm that works, if I go back here now and copy the original definition from line 21 and paste it into here on line 34 in the second parameter, and if we run this time you can see we've got the message Argyle was removed, and we've now only got 3 items left. Both Lisp and Argyle got removed from our list of languages. Okay, so let's just clean up a few things because I want to talk now about a few other methods. So what I'm going to do first is I'm going to comment out this removal of Lisp, and then down here, just before our for loop, what we're going to do is print out a message here, we're going to use the .replace method, and what replace does is it's used to replace the entry for a specified key if it's already mapped to a value. So to see what I mean by that, we can do something along the lines of here, and we'll print out the results. Languages .replace Lisp. We'll do something like a functional programming language with imperative features. The first one, but also we'll add another entry as well just to show you, confirm the results we get out of this. And we'll do something like system.println languages .replace, and we'll try scalar. This will not be added, obviously, because scalar doesn't exist, and we're replacing on the assumption that the key already exists. So if we run this, so you can see what's happened. We've got therein lies madness. When the first one replaced on line 43, when that code was executed, it returned the previous entry, which of course was therein lies madness, which we configured on line 23. The next entry there returned null, which was its way of saying it didn't already exist on file. And it's not added, as you can see, because it doesn't come up with a list there because it wasn't already in existence in the map. So it doesn't get added, unlike a put, which does that and then replaces it if it's already there. And just like remove, we can also specify the existing value so that a mapping is only updated if the key was mapped to the old value we did, that we originally specified, or that we can specify. To do this, we provide the expected old value before the new one. Now what we'll do is we'll just do it wrong the first time, just so you've got an idea on what I mean. So on this line here, instead of just printing it out, we'll change this code a little bit. We'll put an if there. If languages.replace, whoops, Lisp, and notice how it's binding there's 3 options there. There's key, string old value, and string new value, or we can just do as we did in the past. So in this case, if we put something like the old value of this will not work, and specify the new value like so, Lisp replaced, else Lisp was not replaced. Okay, and I'll just comment out the scalar one for now. So if we run that, we should find it doesn't get replaced. So Lisp was not replaced, and Lisp is therein lies madness. It's still set to the original value, which of course we configured on line 23. So again, just as a recap on that particular function, so what we're doing is we're passing a third parameter, we're passing the key, we're passing what the old value was, and we're passing what the new value was. So that's just a way for you to check that you're really only updating if the value, this particular value already existed. And just to confirm that, we can come back up to here and copy that. And change this will not work. Paste that in there like so. Then we run it. We can see that Lisp was replaced, and Lisp is now a functional programming language with imperative features. So it's obviously worked through and updated, which is what we wanted to do. Now you might be wondering, well, why is that useful? Well, one good use for it would be, say, for example, if you're updating someone's name after they got married, you could ensure that the correct person is updated, or if changing an address. So you're just checking to make sure that that exact entry, you're at that exact right entry before you update it, so there's no chance of accidentally overwriting the wrong information. Now for these examples of the methods defined by the map interface, we've used a map that uses a string type for both the key and the value. Now, in fact, both the key and the values can be any object. We could even use a map type as the values in another map. In actual fact, you could add a map as a value to itself, although it's probably not a good idea to do that. It's important to point out that unlike other languages, such as Python, for example, there's no requirement that the keys of a map be immutable. And just as a recap, immutable objects are things like strings and integers whose value can't change. Now, if that sounds strange, when we assign a new string value to a string variable, what we're doing is we're changing the value that the variable holds. We're not changing the string. So our goal, for example, that we used for one of the keys earlier, that's on line 21, can't be changed. On the other hand, an array list can change by having new items added or new values assigned to existing entries. Now, with that said, the Java documentation does warn that great care must be exercised if immutable objects are used as map keys. So they give you that warning, but they're not prohibited. Now, the reason for the warning is that a map object can behave unpredictably if the key objects change in such a way that equals comparisons are affected. Remember, we talked about those equal comparisons in the last video, and actually earlier in this video. So it's worth being aware of this warning, but you'll probably have to do something fairly advanced before it affects you. So using classes as keys is in itself fairly advanced. Now, one thing that's not permitted is for a map to contain itself as a key. And it would be a very bizarre program that attempted to do such a thing. Now, to demonstrate some probably more interesting uses of maps, what I'm going to do is model a small part of the original adventure game, Colossal Cave, which allows a player to move around the various locations by typing in compass directions. So what we're going to do is create a new project. We're going to call that adventure, and then we're going to create a new class. So let's go ahead and do that. So file, new, project. I'm just going to choose the standard things that you've probably seen me do a million times now. We're just going to create the project from template, and we're going to call this one adventure. Finish it. And we're going to say this window, which will close off the other code because we don't need that for now. I'm going to move this over a little bit to give it more space. And we're going to go ahead in the package and we're going to create a new class, and we're going to call that location. Like so. So let's start by defining some basic information about this location. And again, this is the location in an adventure game based on the original Colossal Cave adventure, which is one of the first adventure games that came out years and years ago. And feel free to Google that if you want to find out more information about that. So let's start. We're going to need a location ID first. We're going to have a private final int location ID. Let's also have a description. So private final string description. This is the description of the location. And we're getting that error most likely because they haven't been initialized, but you can see that, but we're going to initialize those in a constructor shortly. We also want our map, which is going to be a map of exits. So private final map string integer, and we'll call that exits like so. And we'll use the Java util map. Let's add a constructor. And the constructor is going to take just the two parameters. So we're going to take the location ID and the description. We're not going to do the exits because we're going to initialize that. So we're going to do that. And you notice those two errors have gone away now because we've initialized it. And let's set our exits up. This.exits equals, we'll just initialize it to a new hash map, like so. Then what we want to do is add a couple of methods. We want to add the ability to add an exit to our location. We want to get it for the location, get it for a description, then we want to get it also for our list of exits. So let's go ahead and do that as well. So getters are going to be easy enough. Let's add those first. Getters. We want location, the description, and the exits all as getters, so we can get access to those from another class. And actually, let's put it up here. So what we want to do is we want to add the ability to add an exit. So to do that, we're going to do public void public add exit. And we'll do string direction. And be int location. Then we'll put exits.put, and our direction is going to be the key, and the location is going to be our value. So that's a very basic location, and so it's containing, just to recap, the location contains a location ID and a description, as well as a map that we defined on line 12, which is used to store the available exits from a location. And we've added a method to allow directions to be added to this map so that we can define the details from the main program. Now, one thing about this class is that we're programming defensively. What I mean by that is that anything that doesn't need to be exposed to the outside isn't exposed. And our fields are marked final so that they can't be changed once the constructor has finished creating a location instance. So one useful technique that we've used is in the getter for the exits map. And with the get exits, what I did with it there, I actually need to change it. I want to show you what I'm going to do there, then I'll explain why I'm doing this. So what we're going to do there is we're going to return new hash map of exits. I'm putting exits in the constructor. So the reason that we're doing that is that instead of just returning the exits map, I'm creating a new hash map and passing our exits in the constructor, as you can see there on line 32. Now we've seen that use of the constructor before with lists, and it does the same thing here. So in other words, a new map is created that has all the mappings from the exits map. Now the reasons that this would be useful, a useful technique, doing that here, is that nothing outside of our class can change exits. So the getter returns a copy of exits, so that if the calling program wants to add or remove mappings from it, then the exits mapping field won't be affected. That's really important there. So although we won't be using the location class as a key in the map, we'll use it later to show some ways to make your classes immutable, and returning mutable objects from a getter in this way is one of the techniques here to make sure that that works. So let's go back to our main method and write some code to add some locations. And what I'm going to do is start by putting a scanner in there. Scanner equals new scanner system.in. We'll just accept that input. And what I'm going to do is I'm going to copy and paste some of these locations just to save a bit of time. We're going to have 6 locations to start with. These are going to be locations in the game. And I also need to define the map here. So it's going to be private static map. It's going to be integer location being our class. I'm going to accept the import I should say. We'll call it locations equals new hash map, like so. That's initializing, and then obviously from lines 13 through 18 we're adding new locations. You can see we're adding a number. We're putting the original key there, which is the integer 0, 1, 2, 3, 4, 5, which gets converted to an integer object via auto boxing. And then you can see that we're creating a new location object using the same technique. We're passing the number, which is going to be sort of our location ID, then a description of what the particular location is all about. So let's now add some code that allows us to type in a number and then prints the location description that it's retrieving from the map. So to do that, we're going to do something like this. We're going to put int lock equals 1. We'll put while true. We'll system.out. We're going to do locations.get lock.get description. So we're going to get the description of the current room. And then we're going to put if lock is equal to 0. We're going to break out of this while. Otherwise, we're going to do lock equals scanner dot next int. Retrieve the number. Then we're going to put if not locations dot contains key lock. I'm going to print out a message. You cannot go in that direction. So we just run this, and then what we'll have to do is finish this video and wait for the next one to continue running the code. But now you can see we started out because we defined location to be equal to 1. The default room is going to be that object. So we're going to put something like, we know that the second location 2, is you're on top of a hill. So I'd go into there and I type 2, you're on top of a hill. If I type in 3, you should be inside a building. 5, you're in the forest. And 4, let's try the other one as well, you're in a valley. And if I type 0, you're sitting in front of a computer learning Java, which was the exit, or the way to sort of break out of it. So that's a very simple program there. Now in the next video, what we're going to do is we're going to enhance this and we're going to build the exits. So we're going to set it up so that when you're at a particular location, you've got a list of exits and you can only use those exits that are valid for that particular location. So let's look at doing that in the next video. In the previous video, we started off on our adventure game and we had a very simple mechanism that when we ran it, we were able to type in a number corresponding to a location, and it would actually, the program would print out the location's description by retrieving it from our map, which we defined on line 8. And of course, entering 0 would break out of the loop and ultimately quit the program. And the other thing, we had some very basic validation in there on line 28. Line 27, we accepted the input for the particular location. On line 28, we did a check to see whether that key existed in our map, which of course the key was just the number at this case, at this stage for our location. And we'd get an error message saying you cannot go in that direction if ultimately we couldn't, if we couldn't find that location in the map. But we have got a problem there still, and this is what happens. If we actually run it, what I'm going to do is just clear off a bit of space to the left there, like so. So we'll only open up the project window if we need to. And you can see that we've got to start here now. We can enter a valid location. 2, that's all working nicely. But if we enter something like 25, we actually get an exception. So it does quite helpfully tell us you can't go in that direction. But then what happens is it loops back and then it tries to retrieve that location, and obviously gets itself into difficulty on line 22 when it's trying to print out the location based on our get for that particular location. Now, we won't fix that bug, and the reason for that is we're going to extend the program anyway. And if you look back at the locations class again, remember that on line 12, we defined an exits field, and that's also a map, and that also contains a string for the key and an integer value, so it's sort of other way around. So on getting back to our main, of course we had integer and location, but in location, for the map, it's string and an integer. So the idea here is that the key is going to be a direction, although we'll start by using the initial letters north, south, or N, S, E, W to signify north, south, east, and west, and Q to quit. And the value will be the number of the location we will get to if we go in that direction, which will be sort of the location ID. And just to help you understand what we're trying to do here, I'm going to open up a little image on the screen. Here's the little image on the screen here now. And you can see that the various locations are indicated, as you can see on the screen. And there's also the valid directions, the valid exits, in other words, you can go to from each particular location. So this is a map, but an adventure game map, not a Java map of the locations that are going to be valid for our game. And just to confirm, starting from location 1, which is the road, you can see that from there we can go in all 4 compass directions, and the arrows show how the locations are linked, as you can see there. So some links only go one way. For example, from the valley, you can only go one way, going west to the hill. You can't go back directly from the hill back to the valley. That's the way that this mapping works in our adventure game. And so consequently what we're going to do is, for example, with valley, what we'll do is for our map, we'll add an entry, W, standing for west, and then the room number in this case 2. So that would indicate that room 4, or location 4, room 4, so I'll say location because it makes more sense. Its only exit in this case is to the west, which is going to go to location 2. So let's go ahead and put some of that code in there now. And we're going to go back to our main to do that. And what we're going to do here is just below this initial set of locations, you can see that we've added the locations, but what we want to do now is add the exits for each location. And unfortunately, map literals are still not available in Java, which is a bit annoying. There was talk of including them in Java 8, but it didn't happen. So as a result, we really have to use repeated calls to add exits for each location, which is a little painful, but it does get the job done. So we're going to type locations.get 1. So we're getting room, I keep saying room, but location 1. And location 1, if we go back and have a look again, location 1 is the road. So now we're going to map out the available exits. And you can see that we've got west, north, east, and south as valid directions from location 1. So what we're going to do is add exits. or add exit, I should say, use that method. And we're going to add the key W and the value 2, meaning room 2. And what I'll do is I'll just copy that 3 times. 1, 2, 3. So to the west, we went to room 2. East, of course, we went to room 3. South was room 4. South 4. And north went to room 5. North 5. Oops, sorry, 5. And we need one more, and that's quit, going to room 0. So Q was our sort of quit keyword. So just to refresh that now so you can understand what we're doing here. So from room 1, west 2 on line 20, we're going west goes to room 2. On line 21, east goes to room 3. South goes to room 4. And finally, north goes to room 5. And of course, Q is our quit, which goes to location 0, which is the special location to sort of indicate that we're finishing the game. So that's what we're trying to do. We're mapping out each room. So let's go ahead now and map the rest of the rooms out, and we can continue on. So I'm going to do the next one, for room 2. And for that one, the 2 options were to go north to room 5. Then the only other one was to quit. 0. So that's the 2 locations. And the next one we're going to do is 3. And 3 only had a west, which went to room 1. West to room 1. Then we have to add a quit as well. Quit, which goes to room 0. Next for room 4, we've got a north and a west for that option. So 4, and that's going to be a north, which goes to room 1, which happens to be correct. And the next one is still room 4. We're going to go west. We're going to go to room 2. And of course we need our quit as always, which goes to room 0. Okay, so we're getting through them now. We've just got room 5 to do now. And room 5 has got south, went to room 1. And 2 more for south, 2 more for location 5. West is going to go to room 2. And then quit is going to go to room 0. So that should be it. So again, just very briefly, going back and looking at our image again. For example, location for room 4, which is the valley down here, you can see north goes up to location 1 correct, which is road, and west for location 4 on line 33 goes to the hill for version 2, and the hill for location 2. And from the hill's perspective, you can see location 2. Notice that there's 2 exits from 1 to 4, but there's no way to go back to them. We've got these arrows going multiple ways if there's a case to go back that way. So in other words, you can only get to the hill from the road. You can't go back from the hill to the road, and likewise you can't go back from the hill to the valley. And that's why for location 2, the only exit is to go north to the forest. Okay, so we've mapped out our exits now for each location. And to get this working so that we can actually use those indicators, those directions for our program, it doesn't really need a lot of changes. So what we do is instead of reading an integer, we're going to read a character, which we're going to convert to uppercase to match the keys in the maps. And then we'll also print out the keys in a location's exits map using the key set that we saw earlier. And finally, what we need to do is look up the new location matching the chosen direction and set the lock variable if the direction exists in the map. And if the direction isn't a key in the exits, then the location's not changed, and consequently it's not going to be a bug. And that's the reason why we didn't bother fixing this bug that came up previously, because we're going to fix it in this version of the code anyway. So the code that we need to change, we're going to leave this code here after the while that prints out the description. That's still valid. And the if location equals 0 to exit, if that's been entered, that's still correct. Where we are going to change it though is just after that we're going to indicate the directions. So we're going to put our map in there. So it's going to be map string integer exits equals locations dot get and the lock dot get exit. So we're getting the exits that are valid for this particular location. And we're going to print out available exits are, and what I'll do is I'll get rid of the print line for that. So it's just a print. And then we're going to use a for loop using the key set as I mentioned to go through all the keys which indicate the directions that are valid for this particular location. And we're going to use exits.keyset. I'm going to print out exit plus and a comma, so we can actually show the different locations if that's different exits, if there's multiple ones. Then after all of that, we need to do a print line, and there actually shouldn't have been a print line because we want to print that all on the same line. So the printing of the line afterwards, so it does go to a new line. So what we then need to do is we need to change our scanner, and we need to grab a character instead of a number. So we're going to do string direction equals scanner dot next line now, so we're not using an integer, dot to uppercase, so you can type in the different directions in either upper or lowercase. And then what we're going to do is we're still going to update the lock variable, but we're going to put a test in there first. So if exits dot contains key, and it's going to be direction that's been entered, then and only then do we set the lock variable, and that's no longer going to be a scanner anymore. What that's going to be is a exits.get direction. So we're getting the integer corresponding to the valid direction that's been entered based on the key that has been typed in. And then we put an else in there. You cannot go in that direction. Go in that direction. Like so. And this last test down here no longer needs to be in there either. And just to confirm, on line 47, we're using our getExits method to retrieve the map of valid exits from the current location. And as getExits returns a copy, if we did make any changes to that map, it wouldn't affect the map field in the location instance. So now if we run this, we should be able to do walk around a little bit. So there we are. We're starting off now. We're standing at the end of a road before a small brick building, and that's this location. So we're in location 1. So valid exits are to quit, obviously, the south, east, north, and west. We can go to any of them. So let's go north, which should take us to the forest. I'll type in north. You're in the forest. And just to confirm the forest now, available options quit, or we can go south back to the road, or we can go west back to the hill. So let's just go back west first. Take us to the hill. And you're at the top of the hill, and the available exits for the hill are obviously back north again. And north should take us back to the forest. So we'll go back to the forest again. And obviously if we enter a location that's not there, east, you cannot go in that direction when you're at the top of a hill again. So we'll go back north. And now if I go back south, it should take us back to the road again. And then let's just go east. You're inside a building, a wheel house for a small spring. Okay, and just to confirm that that worked, there's our building again. And maybe let's just go, just to make sure we've done all the locations, we'll go back west now and then south. So west and south. South takes us to a valley. We can go north or west from there, and that again equates to north back to the road or west to the hill. So let's go back to the hill again, west, and Q to quit. Okay, so you can see that our very basic game is working, and obviously it's got very little functionality, but we were able to navigate and successfully add the valid exits for each location, and it didn't really take much code, as you saw there. The majority of the code here was the initialization aspect, setting up the locations and then setting up the valid exits for each location as well. Now, one observation that I'll make here is that we need to make is that the entry Q and 0, in other words, line 24, line 27, line 30, etc., appears in every location's exit map. So what we could do is we can remove it from main and add it to the location constructor, and that would probably be a better way of doing it. So we could go back here and just remove this. I'm going to comment those out, because if we know that there's going to be a location that's added each time, it's best not to put it in there because it's just redundant coding essentially. So I'm commenting all those out. Then what we'll do is we'll go back now to the location, and because the location class has got a constructor and we're defining this new hash map for the particular exits that are valid for this location, we could actually put that in there. So we could type in this.exits.put Q0. And it's a good idea to do that because that means for each location that's added, we're automatically adding the ability to quit out of the program. And that just saves a bit of code, obviously. Those 5 lines that were there now have been replaced with 1 in the location constructor. And just to confirm, that should still work. We've still got our quit there. We can go sort of south. Oops, we can go south if we wanted to. And we can quit still. So obviously the quit is still working. Let's fix that typo. Okay, so we are now using some of the same map methods that we discussed earlier in the previous video. The main difference now is that the locations.get method returns an instance of the location class rather than a string. So in other words, just to be clear, when we're using locations.get, this method here, that's returning the actual object, the location object that has been set up, that we've defined here when we created the new class for each one of our map entries. So that's the beauty there. We've got a key now, which is the location ID, and the value for our locations map is a location class, and from there we can then get the appropriate information, which you can see there on line 47. We're using .getExits, which gets a copy of the map of available exits for that particular location. Now we've got a pretty basic interface, as you can see now. At the moment you've got to type N, just like single letter abbreviations. We can make an improvement to the user interface to allow the player to type the full words, like north, south, east and west if they wish. And we can even do short phrases such as go west. And interestingly enough, a user interface that allowed you to type go west and have the computer understand was literally state of the art back in 1976 when the Colossal Cave Adventure game, which this is based on, was actually written initially. Now the only thing you need over and above what we've been discussing in order to implement such an interface, as I've just mentioned, is the string class split method. And if that sounds like this task is going to be your next challenge, you are spot on. But first, let's just briefly talk about the split method and how to use it, and then we'll move into the next video when we'll start talking about the challenge. So what we're going to do is temporarily comment out the entire while loop. So I'm just going to go through this entire while loop, comment that out, because I want to actually demonstrate the split method so you've got an understanding of it. I'm going to copy and paste some code in to save a bit of time because this video is getting a bit long. I'm pasting in the code there, and I'll just close the run window so you can see it. So the first use of split on line 64, it creates a string with 14 items containing each of the 14 words in the location string. So the split method breaks up the string into individual items separated by the string we pass as a parameter to split, which of course is this text here. Probably easier if I run this rather than explain it. So you can see what's happened there with that first code on line 64. It's gone through and split up each word based on a delimiter, which was the space. So if I just close that down again, and you can see there we've got a little space character. So essentially let's use that as a delimiter. So each word that is separated by a space has been added and available to you now as in the string array that again on line 64. And the second example, it does something very similar, but it's using the comma followed by a space. And as a consequence, we end up with something that's containing only 2 entries this time. You're inside a house and a well house for a small spring. And that's because if we look up here, we look at the delimiter, it's using that delimiter there, which is the comma and the space. So you can see that the split method is very useful for splitting down content, splitting down a large string into smaller pieces. So I'm going to end the video here. In the next video, we're going to go through a challenge to enhance our application. So we'll talk about that challenge in the next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
This video is over. Go to starfreelance.eu to download these videos, materials, and sources. Watch more videos to get premium videos and ebooks. We'll be a star freelancer.